Okay, Professor Yang, and welcome.
Hello.
Good morning.
Good morning. Everything's ready, right? Everything's good?
Yes. I just wait for a couple more minutes. I'll just briefly open the session and then we'll invite you to give the
very first session in
keynote lecture. Yang, your sound is a bit soft.
Oh, okay. Maybe I should use earphone. Yeah. Let me try. Okay, it's better now? Yeah, you can hear. Han, can you hear me now?
No, it's still very soft.
Still very soft.
Maybe you can turn up the volume. Is there a volume setting for this, for the mic?
Yeah, I think it's all right. Well, it's this mic.
Yeah, so you need to set the source of the mic from the Zoom to your earpiece. Okay, good morning, everyone. Welcome to our international workshop on federated and transfer learning for data sparsity and confidentiality, which is held in conjunction with the Ijcai 2021 conference. Okay, so over the years, we have seen rapid development of these two fields. Both of them are making it to the hype cycle for data science and machine learning from Gartner's. Okay, so I think this is a very opportune time for us to start looking at both of these fields together with some advanced exploration of advanced ideas and synergy through a workshop like this. Okay. So for our workshop, this time we have received 31 very high quality submissions, and each paper have received at least 2 reviews from our program committee And eventually we accepted 11 papers for oral presentation and 8 for poster presentation. And today we have a very exciting program starting from Professor Qiang Yang's keynote on transfer and federated learning, followed by another 10 exciting invited talks from our industry partners, as well as academia research experts from various universities. So I think it's going to be a very exciting program for today. We want to express our heartfelt gratitude to our program committee members, as well as our organizing committee consisting of multiple industry leaders, as well as universities working in related areas. Finally, here I wish to give everyone a heads up. We have an upcoming book also edited by Professor Yang Jiang and his team on federated and transfer learning. The information for submitting book chapters are listed here, and you can also find the information from our website of the workshop. So everyone, if you are interested, please look out, prepare your submission, and submit it through the link as listed here. Okay, so I think this is a very brief opening from me, and hope everyone enjoyed today's program. And now I will move on to the program proper. Is Professor Heng Huang here? Our general co-chair, Professor Heng Huang, are you here? Maybe while we are waiting for Professor Heng Huang to join us, let me first introduce hello. Oh. Okay. So while we are waiting, let me first introduce our distinguished keynote lecturer for today, Professor Qiang Yang. So Professor Yang is the head of the AI department at WeBank as the chief AI officer, as well as a chair professor at the Computer Science and Engineering Department of Hong Kong UST, where he's a former leader, head of the CSE department and founding director of the Big Data Institute from 2015 to 2018. So his research interests include AI, machine learning, data mining, especially in transfer learning, as well as federated learning. So he's a fellow of several international societies, including ACM, AAAI, IEEE, IAPR, and AAAS. He received his PhD in computer science in 1989, and his Master of Science in Astrophysics in 1985, both from the University of Maryland, College Park. He obtained his Bachelor of Science in Astrophysics from Peking University in 1982, incidentally, the year I was born. He had been a faculty member at the University of Waterloo and Simon Fraser University. So he was the founding editor-in-chief of the ACM TEAST journal, as well as the IEEE Transactions on Big Data. He served as the president of the Ijcai from 2017 to 2019, and an executive council member of AAAI from 2016 to 2020. Professor Qiang Yang is a recipient of several awards, including the 2004-2005 ACM KDD Cup Championship, the ACM SC KDD Distinguished Service Award, AAAI Innovative Applications of AI Award. He was the founding director of Huawei's Noah's Ark Lab and the co-founder of 4Paradigm, an AI platform company. So he's an author of several books, including Intelligent Planning, Crafting Your Research Future, and Constraint-Based Design Recovery for Software Engineering, of course, also federated learning. So let us now invite Professor Qiang Yang for his speech. Professor Yang, please. Professor Yang, you are still muted.
Okay, can you hear?
Yes, yes, please.
Okay, excellent. Okay, so let me share my slides. Okay, so my talk is a journey from transfer learning to federated learning. So in this brief time, I wish to connect these two fields, although very closely connected. Okay, so let me start by talking about research methodology and why I work in these fields. So I was very impressed by two role models in my career. One is Jim Gray, the famous Turing Award winner and the founder of relational database. And so in his one of his talks, he was talking about research methodology. And this research methodology, okay, sorry, I have some problem with yeah, okay. So I hope my voice is okay. Yeah, so he laid out some guidelines for finding a good research topic. And he asked the following questions. Why is a problem important? And how do you describe it in a simple manner? And describe also in simple manner how why the problem is challenging. And as important is the problem must be decomposable into small steps that people can solve. And on top of this, I wish to add whether there's data, because today's research mostly rely on empirical research. And so in finding a research topic in the vast areas of AI, for example, there are many, many topics. It's important not to follow the crowd, but instead finding a problem that people have not yet considered important, but will be important in the future. Another role model is Richard Feynman, a physicist, a Nobel Prize winner. He also was very highly achieved in physics, discovered many phenomena in particle physics, theoretical physics, but he also discussed research methodology or life methodology in other way. One of his books, which I highly recommend, is what do you care what other people think? That is how you can follow your own way instead of following the crowd. So I'm saying this is because when when my students and I started working in these fields, transfer learning and federated learning, it's indeed a very small crowd, very small number of people interested. But gradually, it takes years to grow and finally grow into something important. Okay, so so my own career followed these principles, and so after I graduated in 1989, became a faculty member. Starting in 1990, some of my work started appearing in textbooks, and that's how I know I'm working on important topics. So for example, some of the popular textbooks in AI include the artificial intelligence, a modern approach, and two of my planning theorems appeared in these books. And starting in 2007, the work on transfer learning started bearing fruit, and some of the popular textbooks in data mining started adopt sections on this topic. And federated learning, as Professor Yu mentioned, started making its way into Gartner's hype cycle, which is an indication of important adoption by industry. And so these research methodologies I summarized with my friend, Charles Lin, into a book advising graduate students. It's called Crafting Your Research Future. So people can easily pick it up because it's a widely available document. Okay, so to summarize, when we started working on transfer learning, we asked the problem how to transfer between domains. Really, we are asking how to solve a small data problem because, as we know, data is becoming more important, and without data, you can hardly engineer, build any models in AI. Okay, and so how do you build based on one or two examples? This has been the central research topic for case-based reasoning, which very few people probably have heard of. But case-based reasoning started from cognitive science, including planning, inferencing, from very early on, from 1970s. And so this question of how to solve problem like a human does, and how to solve one example learning, how to solve few example learning has been the central problem there. It's not something that's invented in machine learning. So then we can break this problem down into the following questions. That is, what to transfer, how to transfer, when to transfer, and of course, where to transfer, and so on. So the difficulty in engineering is how to solve a cold start problem in recommendation, for example, how to solve the data scarcity problem when we don't have much data, either because we don't have much samples or features, feature space is limited. Okay, so with my students, and thanks to them, very talented students, we broke down the transfer learning problem into different styles. For example, instance-based, feature-based, model-based, transitive transfer, and automatic transfer learning, to name a few. So this, we also mobilized many of my students into a book, and this book was published last year called Transfer Learning. It's published by Cambridge University Press. Now on to the next topic, federated learning. We took the question of small data even one step further. We noticed that many organizations hold data, but they cannot collaborate, either because of privacy or because of their central interest lies in the data. Okay, so we asked the question whether we can achieve this slogan called results, not data. Okay, so we don't really care about data, but we care about results. So how do we obtain the results? But we don't have to see the data. And so this really belongs to the problem of decentralized data sources. But it's very different also from distributed AI, which has been around for years. Distributed AI belongs to one owner who can engineer the data sources across different servers so as to improve the efficiency. But decentralized data is entirely different. The data sources belong to different owners, and they have different interests. In fact, they may or may not want to collaborate. They may leave this ecosystem. And also, there may be bad guys out there who pretend to be good guys, participants. And data can be distributed differently. So it's heterogeneous data and non-IID data. Okay, so with all this complexity, the situation is entirely different from distributed learning. So now we care about privacy preserving, high efficiency, and encouragement for collaboration. And the difficulty lies in incomplete and inaccurate data, and incompatible data even, and non-IID data, which is a hot topic now. So again, with many talented students and colleagues, we broke the problem down into different styles, different categories, such as horizontal, vertical and transfer federated learning, where we care about safety in robustness in federated learning, autonomous federated learning, incentive mechanism, ecosystem building, and standards building. Okay, and this is still a very active field in its infancy. It's just starting. Okay, so let me go into a little details on each of these topics. Okay, so in transfer learning, we ask the question, what if we have only small data? Okay, so in this case, our methodology is very much like today's pre-trained model, which is in transfer learning, we first pre-train a model in the source domain, and then we use adaptation to, we can say, personalize or adapt it to special purpose, specialized target. Okay, so from left to right, and we can either transfer the model or the source or the tasks. Based on each of these, we can come up with entirely different algorithms, but their methodology is the same, is like on the right, where we have a pre-trained model, such as BERT, GPT-3, Wudao, and so on. And then we use adaptation to specialize this pre-trained model on tasks, okay? In deep learning area, the pre-trained model has been very hot, but the adaptation part has not yet started. So people can pay attention there if you are looking for new topics, that is adapt what we have learned from transfer learning to this pre-trained model area. So here are a few examples. Transfer learning has found its path in many different AI areas, and one of them is dialogue systems, where we can model a dialogue system as a reinforcement learning system. Reinforcement learning consists of states and transition between states, and the transition is governed by the reinforcement learning state transition policy, okay, which can be a single agent or multi-agent. So dialogue system consists of conversational actions which can take you from belief state to belief state. And in this way, it's so like the example shows, it takes you from one state to another by asking questions and getting answers. And you can have multiple like RNN, LSTM, and so on and so forth to help you with this kind of state embedding. So in this area, one of the challenging problems is how to adapt a mature dialogue system or dialogue policy into a new area. And at WeBank, we face a massive customer service problem, including serving 300 million people over the internet, 24 hours a day. And we use robots, and robots handle about 98% and above of these conversations with high satisfaction. And the real human powered customer service, the humans number is only several hundred, serving several hundred million people. And so robotic soft robots are very important. And here, transfer learning plays a very important role because there are new tasks appearing all the time. And so we face the problem of cold start almost every day. And so transfer learning is key. Another important area is recommender systems, which is again modeled as a bandit problem or contextual bandit, which is a variant of reinforcement learning. That is, in this area, when we want to recommend, say, short videos or news items to people, especially specializing for personalized recommendation, we face the problem of cold start. And so to solve the problem, people use transfer learning as well. And here we use this for cross-domain recommender systems very successfully in order to improve the click-through rate. Okay, so the problem is contextual bandit, and so we introduced the topic new area of transferable contextual bandit to solve this problem. Another interesting area is transfer learning is not just in one step from A to B, but can be in a series of steps from A to B to C to D and so on. And we call this transitive transfer learning. So for example, in World Bank and Stanford University used satellite images to identify the economic status of different regions on Earth. And to do this, they have to make sense of the images, 2D images of a daylight satellite. So they use a sequence of transfer, first understanding the segmentation and semantics of the image using ImageNet. Then using night satellite images to get a basic idea of economic development by means of light. And use these two in a sequence of transfer in order to obtain the final classification result, which is pretty good compared to the human result. But they gain by having a fully autonomous system, which is very low cost. Okay. Transfer learning has also been used together with GAN. And in a very interesting application, my student put this on the application of sentiment analysis. In sentiment analysis, we have to label a lot of text, especially important keywords that are indicative of sentiments. Okay, and then when we face a new domain, let's say in a new movie review or book review or product review on Amazon and so on, we have to come in again and label these keywords. Okay, in order to avoid this relabeling, one of the key ways is to use transfer learning. And in using transfer learning, we have to find the so-called pivot, that is the bridge words, which give similar semantics in both domains as a bridge. And traditionally, these bridge words are found by human, and they are very slow and labor intensive. And so using a GAN, we can do it like this. We can use one part of the system, the generative process, to generate the model. And the model's aim is to minimize the error rate in the source domain. And we can use a discriminator to try to minimize the differences between the two domains in order to find the keywords that are pivots across domains. And when these two are working together, we can automatically find the bridge words. And this has been a new milestone in the sentiment analysis direction. I should also mention that there's a growing field which has been very, very successful in using deep learning for transfer learning. And this was initiated by Professor Long from Tsinghua University. And there has been a lot of research on the theoretical analysis as well, which gives the sense of science to transfer learning. In transfer learning, the science question is, when can systems transfer and how well can they transfer? And so because we have a deep learning model that are divided by layers. So we can break down this scientific question into which layer can enable better transfer across domains. Okay, in order to answer this question, there was a research by Yusinski and colleagues, which actually break down the layers and individually ask how well they can transfer. And the result is shown on the right-hand side figure. And as you can see, the closer to the bottom of the deep network, the easier it is to transfer, because the domain knowledge there is mostly common knowledge. Whereas close to the task layer, the knowledge is more specialized to the task, and therefore it is harder to transfer. I wish to see further development in this area in the future into some more theoretical analysis, and so graduate students can take note here. One of the exciting works is also autonomous transfer. We know AutoML has been put into practice in massive scale in the company called For Paradigm, which allow them to reduce the cost when applying AI to different areas. And so we asked the question whether AutoML can be applied to transfer learning as well into something called AutoTL. And indeed, this can be done. And Professor Ying Wei from City University has started a research direction on this. The idea is when we have done enough transfer learning, if we record all the experiences, then we can have a different training data. This training data consists of a number of items, including pairs of tasks and transferable features that are characterized by model parameters. And we can also remember the performance improvement, which is a label on the pair of tasks. When we have this, we have a space in which is shown on the right. In this space, it's spanned by the error rate, parameter space, and task pair space. Okay, we can find the best point in order to maximize our potential transfer learning experience. We can find the best transfer learning methodology, including finding the best algorithm, finding the best source data, and finding the best set of parameters to enable the transfer. And this is shown on the bottom here into an objective function. And we can experiment with different type of losses, which corresponds to different distances, such as the mean distance, such as the variance in the distance, and discriminative ability as the distance measure. And so when put to experiment, we can take entirely different tasks as potential source and targets, and we can experiment with a great number of published transfer learning algorithms, and show on the right that experiment shows that AutoTL can always maintain the best performance. Now we turn our attention to the next topic on federated learning. And so the central question here we asked is, what if the data are decentralized and therefore we don't have control over all the data? The traditional way of fusing the data by copying them to a central location will not work. And we know that in countries and regions across the world, the law is tightening. In GDPR in Europe, the GDPR in US, the CCPA in China, the data security laws are all put into effect. The society is demanding more and more privacy. We know many scandals from the giants, and the news are populated by these events. So
perhaps Professor Yang is experiencing some network problem, some delay there. Okay. So let's
be found many B2B applications, which is very, very popular. It's estimated that most of the federated learning applications here we know in China are vertical version between organizations. Under vertical and horizontal federated learning methodology. Okay, and we can combine transfer learning and federated learning. In fact, combine federated learning with transfer learning in two styles. One is if we want to transfer knowledge from a resource-rich domain, party A, into a resource-poor domain, party B. When we want to do this, we can protect privacy of party A while doing this transfer. And federated transfer learning allows you to do this. Another is when we face a heterogeneous federated learning domain where we have non-IID data. And in such cases, we can first transfer each domain into a common area where we can compare and collaborate between the transferred data. Okay, and so this allows us to handle non-ID data more effectively. I should mention that in another area, multi-agent incentive mechanism and market mechanism, a very rich area, already very mature, is incentive mechanism design, which can be used in federated learning to build ecosystems, where if we have several ecosystems, then a new data source will decide which ecosystem to join. And in this case, it's important to have a fair mechanism and transparent mechanism for the data owner to evaluate its utility. Okay, so this utility question, whether it's better to join one ecosystem rather than another, can be answered using economic theory, incentive mechanism design, and game theory. And Professor Han Yu has a lot of work in this area. I should also mention a collective effort in defining federated learning in a recent publication, and it's also an open source publication authored by many people and initiated by Google. In application, it's already very widespread. In our applications, we have applied federated learning in building a credit rating system for small and medium enterprises. When we evaluate an enterprise for credit assessment, we cannot use human investigation because there are too many of them. Currently, we are serving about 2 million of these small enterprises. So we have to use big data to do this. But we have data from different sources that cannot be copied and moved. They include internet companies, transaction receipt companies, taxation companies, banking companies, finance, and so on and so forth. And federated learning here plays an important role. And using federated learning allows us to raise the usability level to a very high level. In computer vision, we use federated learning to build a collective model for safety recognition based on surveillance cameras. And this has been put to use in Shenzhen area. And in federated recommender systems area, we put federated learning and matrix factorization together to allow better personalization of recommender systems that can be used for advertisement and product recommendation. And we use federated learning for speech recognition to integrate different language models together. So in China, we use a pre-trained model together with some local model with accents to obtain a transferred model which can speak and understand language with accent. And we apply this to hospital medical applications. So in one application, we use this for a stroke prediction based on a patient long history of checkups. But these checkup data are scattered across different hospitals. Now, of course, federated learning also comes with many challenges, and one challenge is safety, and this is still a very active research area. So just from these titles of these reference papers, you can see how serious it is. So this paper is titled, How to Backdoor Federated Learning. Okay, it's authored by Eugene et al. And another one says deep models under the gun, information leakage from collaborative deep learning. So if a client tries to steal other people's data, and by using a GAN to mimic the performance of other participants, how this can happen and how to prevent this from happening. And a new direction spearheaded by two groups. One is Professor Liu Yang from Tsinghua University, and another one is Dr. He from University of Southern California, on putting AutoML and federated learning together in order to lower the barrier of federated learning, just like AutoTL. And as important as research on algorithm design, it's important to publish standards so people from different organizations can better communicate with each other. And we have a safety categorization on whether a platform is safe. And so IEEE standard on framework and application of federated learning has been successfully published in March. And IEEE is working on different other standards. Also in China, there's a new communication standards by Ministry of Science and Technology. And in finance industry in China, there are communications being designed as well, standards. And open source software is also very, very active. For example, our software is called FATE, a federated AI enabler, has been used by many organizations and enterprises. As shown on the right, we have many patents, enterprise and universities using this, and many members contributing in different societies. As Professor Yu mentioned, we finally made into Gartner hype cycle. And as you can see, it's together with differential privacy, it's on the rise in this privacy preserving computing area. In China, the Ministry of Science and Technology just published a white paper which states that about 55% of the privacy computing products are based on FATE, this open source software. So we feel very proud we made contribution to the community. Finally, Nature, the very famous magazine from science and technology, put swarm learning on its front page, which brings federated learning once again into all science area, not just computer science, but all science. In fact, we have been communicating with the author of swarm learning. Swarm learning idea is a decentralized, that is a serverless. So there's no coordinator, but it's peer-to-peer, fully decentralized federated learning. So as such, it's a special case of federated learning. And we all agree that federated learning actually do not have to use a central coordinator, which can become a leakage point. And so therefore, it makes a lot of sense to work on fully peer-to-peer. And in fact, peer-to-peer federated learning has been active for some time. So in this paper called Peer-to-Peer Federated Learning on Graphs, in another called PyGrid, a peer-to-peer platform for private data science and federated learning by OpenMind, this open source software, are examples of peer-to-peer algorithm. And so swarm learning, in fact, is a special case of federated learning, and we are very happy that it appeared on Nature, and also serves European medical science society. So finally, let me summarize by saying that transfer learning and federated learning both try to solve the problem in today's machine learning, which is shortage of data. Transfer learning tries to borrow the knowledge from a pre-trained model, and federated learning tries to allow collaboration among decentralized data sources. And these all move from a small research community to a full-scale industrial community. And there are many new research areas, and we hope to see more results, more participation by our young people. So that's my talk. Thank you. Thank you very much.
Thank you very much, Professor Yang. It's always very enlightening to listen to your talks. We have some time for the audience to interact with Professor Yang. I think we can start from some of the questions typed into the chat by our audiences first. Professor Yang, one of our audience is asking, in federated learning, is the local model has to be a neural network?
No, the local model can actually be any machine learning model. It can be a decision tree, decision forest, logistic regression, or any other model that you can think of. In fact, this kind of heterogeneous model based federated learning is a very interesting question. How do you allow them to communicate while maintaining their own model? This is a very interesting question. So you asked a very good question.
Okay, thank you, Professor Yang. Another of our audience from the Edge Cloud Innovative Lab in Huawei is asking, what do you think people in the industry can do to bring transfer learning and federated learning into practice?
Yes, very good question. I think industry people can do a lot. There are several things industry people can do. One is industry people usually have a lot of resources. And so a smart way of using this resource is open source. So one an industry organization has already mastered some engineering platform. A very good way to expand impact is to open source some of the part of this platform, so everybody, including students, can use it. Another way is open the data. By desensitize the data, the industry people can make the data into a benchmark data, so students and researchers can use them. And yet another area is publish your best practice so other people can learn how you have used and what challenges you have met and how you have solved it. So these are very valuable. Only from industry. University people cannot dream of these things because they are short of resource and short of scenario.
Okay, thank you, Professor Yang. Another question from the audience. What is the most key problem in the future development of federated learning? Is it insecurity, privacy, or efficiency, or something else?
Yes, I would say. Yes, I would say you hit all the important points. Efficiency is a very important point. We know the traditional multi-party computation is a very beautiful theory, but the direct textbook application is very slow. How slow? Compared to the explicit data computation, it can be as slow as 1,000,000 times. So therefore, it cannot be directly applied to large-scale industrial application. So, so therefore, efficiency is something that people have looked into. In federated learning, a key component is homomorphic encryption. Homomorphic encryption itself is very nice, but a direct application can be 100 times slower than explicit data computation. And so how to close this gap becomes a central issue. So today, using the best algorithm and best hardware, the gap is narrowed to 20 times slower, but there's still a large gap. So efficiency is an issue. Safety or security is definitely an issue because, as I mentioned, when two parties communicate long enough, there are one way or another for the other party to rebuild either the model or the data of the other party just by observing the behavior. How do we prevent this from happening, either from theory or from practice, is an open problem. Another question is incentive mechanism, how to design the best mechanism so that our ecosystem can snowball. So these are, yes, very interesting central question. And yet another one is from machine learning perspective is how do we solve non-ID data? So when the data are heterogeneous in distribution and features, in sizes, and how do we solve them?
Okay, thank you, Professor Yang. Another follow-up question from the previous one on whether the model has to be a neural network. The participant is asking, does it have to be a gradient-based machine learning method, or other sort of model can also be used in federated learning?
Right. No, it does not have to be a gradient-based model. So, for example, in a random forest, the communication is based on encrypted weights of the individual decision trees in the forest. There are many other examples so, for example, if you can even use support vector machines by identifying your support vectors and communicate the kernel parameters.
Okay, thank you, Professor Yang. We have a lot of questions popping up now in the chat. Another one is asking, for the robustness perspective of federated learning, which one is more vulnerable? Is the server more vulnerable or the client is more vulnerable?
In horizontal federated learning, if you follow Fed average, then the server can be very vulnerable because we can never guarantee that there's no bad guy who's working in the organization of the server. Also, the client can be vulnerable, but comparing the two, I would say the server is more vulnerable than a client because the client, after all, can be avoided by not sampling it.
Okay, thank you. We got to pick some of the questions since there are so many. One is asking, in federated learning, is there a good way to improve the robustness of federated learning? I think it's also partially related to another one, which is asking about the addressing data confidentiality and the integrity issue with techniques such as homomorphic encryption and MPC. And they also see the emergence of blockchain being mentioned in this field. So what are your thoughts on these multiple different types of techniques used to improve the robustness of federated learning?
Yes, correct. Federated learning is, after all, is using machine learning algorithm. So machine learning algorithm, by definition, is a approximation algorithm. By that, I mean it outputs a probability-based result rather than an exact result like database querying. And so therefore, a robustness for machine learning is a big question. Robustness appears in different formats. So one is, what if the future data is different from the training data? Can the system performance be guaranteed? So this is one issue of robustness. Another one is when the training data itself is incomplete or inaccurate, can your model be guaranteed. So in federated learning, the same question appears. So in federated average, for example, if some of the clients you use provide their data are inaccurate, their data are incomplete, or their data are polluted by poison. So for example, some people may engineer the data so that they can gain some benefit. How do we prevent the global model from being poisoned? So this is also a robustness question. So robustness, both in horizontal and in vertical federated learning are both very, very important question from a security and data completeness perspective. Now, this question asks about, currently, I find several schemes utilizing homomorphic encryption and PC methods for ensuring confidentiality, and blockchain for ensuring integrity. And yes, indeed, this is very, very good. Blockchain allows an auditing mechanism. That is, when multiple parties are working together, blockchain keeps track of the performance and the contribution of each party, so that when they finally share the utility of the global model, they can give a fair sharing of this model. The policy can be more fair, because nobody can modify the record, and the record is transparent. So this, in a way, ensures the robustness of integrity of the data model. Yes.
Okay, thank you, Professor Yang. Maybe one last question from the audience. One is asking, why is there more paper on horizontal federated learning and less vertical ones? What's your thoughts on this? So,
I think it's I think the problem is affected by the availability of data. That is, in horizontal federated learning, there are already benchmark data out there, and the algorithm baseline is very easy to compare to. For example, federated average is what everybody uses today. But in vertical federated learning, there's a lack of benchmark data. And so this, we hope to remedy in the future by publishing more benchmark data for vertical federated learning, as well as benchmark models. There's a lack of. And so as a result, I think, for example, when ImageNet appeared, there's a tremendous growth in deep learning because of ImageNet. And so the same situation is here. Yeah, so we hope to gain more in this area.
thank you very much again, Professor Yang, for your enlightening talk for today. And I'm sure all the audience have benefited tremendously from your talk. Thank you. Have a great weekend.
Thank you, Professor Yu. Thank you all.
Thank you. And everyone, we can now move on to the rest of our programs. So we will kickstart the morning session with the 3 invited talks. Our first invited speaker is Professor Fei Wang from Cornell University. So he is associate professor in the Division of Health Informatics, Department of Population Health Sciences, Weill Cornell Medicine, Cornell University. He got his PhD from the Department of Automation, Tsinghua University in 2008. His major research interest is in machine learning, AI in health data science. He extensively published on top venues of machine learning, such as ICML, KDD, NeurIPS, CDPR, AAA, and Ijcai, bioinformatics venues such as JAMIA and bioinformatics, as well as clinical medical venues such as JAMA and the Lancet series. His papers have received over 15,000 citations so far, with an H-index of 61. His and his students' papers have won 6 Best Paper awards and nominations at top international conferences on data mining and medical informatics. His team won the championship of the NeurIPS Kaggle Challenge on classification of clinical actionable genetic mutations in 2017 and Parkinson's progression markers initiative data challenge organized by Michael J. Fox Foundation in 2016. Dr. Wang is the recipient of the NSF Career Award in 2018, as well as the inaugural Research Leadership Award in IEEE International Conference on Health Informatics in 2019. Dr. Wang's research has been supported by NSF, NIH, ONR, PCORI, MDFF, AHA, Amazon, etc. And he is a fellow of AMIA. Dr. Wang, please.
Thank you. Thanks, Dr. Yu, for the nice introduction. So first, I want to make sure, can people see my screen?
Yes, we can see.
Okay, great. It's my great pleasure to have this opportunity of presenting some of the recent works from my team on federated learning in large clinical research networks. And it is great to hear that Dr. Yang's team also has some federated learning work on stroke prediction, and also to see the swarm learning page in Dr. Yang's slides, because I'm also going to show that. So I think to start, I mean, machine learning now is becoming very important, and it has changed a lot of things. And like from the AlphaGo to autonomous driving to Amazon Echo, that's a speech recognition system, and GPT-3, it can do a lot of things. And so people are also, I mean, getting excited about machine learning in medicine as well. So perhaps you can imagine some medicine is compared to other fields, it's kind of like a conservative field, but recently, because of the advancement of machine learning and AI, the clinicians and also the domain specialists are also interested in whether machine learning can be helpful in improving healthcare. So, I mean, we also have a large amount of heterogeneous data in medicine. Like I just showed here, we have electronic health records, we have the clinical notes, we have the physiological signals, videos, dialogues, medical literatures, images, medical images, and pharmaceutical research and development data. And with the rapid development of the software and hardware, so these data are accumulated more and more, so which provide a unprecedented opportunity for us to mine insights from those data to better understand the disease and improve the quality of care delivery. And perhaps a lot of you have heard of this word, precision medicine. So when Francis Collins, who is the director of NIH, proposed this term, so he particularly, I mean, he had this perspective in New England Journal of Medicine, and this is a particular sentence mentioning that in the precision medicine, we really want to develop approaches that can perform integrative analysis on various kinds of healthcare-related data, including molecular, genomic, cellular, clinical, behavioral, physiological, and environmental factors. So really from the microscope to macroscope, all things related to healthcare and a disease. So why do we want to do that? Is because diseases are so complicated, and for most of the diseases, we still don't understand them. So that's why we need those data to help us to better understand them and give people a healthier life. So of course, so when we talk about traditionally, I mean, competition in medicine is not new. I mean, but it's just traditionally, it's mostly the biostatistics people. So, I mean, we know for statistical approaches, so typically there are strong assumptions on the prior and all the theorems and then the analysis. And when we have this scale and this heterogeneity, so a lot of those assumptions, statistical assumptions, can be violated And clearly we need new tools. So that's why machine learning algorithms are promising and caught the eyes of a lot of clinicians. And there are, just to give you some examples on machine learning algorithms used in clinical medicine in the case of fighting with COVID-19. So these are three representative papers. The first one is using the survival analysis type of model to derive severity score for predicting the status of hospitalized patient because of COVID-19. The second paper is published by my team in collaboration with our hospital's laboratory medicine. So we built a machine learning model based on gradient boosting tree to predict the SARS-CoV-2 infection status based on the routine blood test profiles. And the third one is published by Mount Sinai and in collaboration with Zhejiang University, where they develop deep learning models to also predict the severity of SARS-CoV-2 infection based on CT scans. So these are all promising examples. But is that really straightforward as we thought? Like we apply like whatever sophisticated deep learning models to complicated medical data, we can get improvement magically. I mean, compared to those statistical approaches, actually it's usually not like that. So I wrote a piece in JAMA Internal Medicine like 2 years ago. And I pointed out in order to like successfully apply those sophisticated machine learning models like deep learning in clinical medicine. So there are lots of factors we need to consider, like number one is the data quantity. So compared to other application areas, so medical data is typically number one, difficult to access, and number two, I mean, the clinical problems are super complicated. Most of the time people don't understand, and you have limited sample size. Let's say typically just to have access to the patient record, I mean the records of patients within one hospital. So in that sense, you have really small sample size compared to a very complicated problem. So how to enlarge the sample size, that's one important factor when you want to train sophisticated machine learning model. Number two is data quality. So clinical data are typically very noisy with a lot of missings and other challenges. So how can you handle that? That's also important. Otherwise, it can easily be in a situation like garbage in, garbage out. Number three is fairness. So, I mean, this is a concept that got discussed a lot in different areas, but especially in medicine. So a lot of times we hear like we train a model that get different performance over different groups, race, ethnicity. This may cause a big problem when you want to apply it in actual like patient management or policy making and the security. So now it's of course the medical data are typically very sensitive, but when it is in the stage of sophisticated machine learning models, the model security is also important, which is I think Dr. Yang also mentioned in his slides. So how can we effectively protect the model? And lastly is regulation. So that's, I mean, all these factors makes actually federated learning a promising direction in clinical medicine. I mean, it can securely, perform integrated analysis over the data across, let's say, different hospitals. People ask about vertical and horizontal. Yes, vertical and horizontal. Let's assume here we talk about horizontal federated learning. I mean, it can effectively enlarge the sample size without sacrificing the privacy or security. So it is definitely a promising solution, and I mean, caught a lot of attentions from clinical medicine, especially since COVID-19. And but one important step before we can, let's say we have a large clinical research network. Let's say this is one which is called ODSI. So it is an international clinical collaboration network. I mean, you can see all those markers are the place where you have hospitals enrolled in this ODSI network. ODSI stands for Observational Health Data Science and Informatics. So different countries speak different language. Let's say if you have hospital in US and in China, how can you guarantee you know, let's say they talk about diagnosis, if they are referring to the same diagnosis or no, and also medications. So before we can do anything, it seems the first step is to like make sure everybody speaks the same language. So that's the data standardization or harmonization process. So that's why we need these large clinical research network or consortium to make a unified vocabulary. Like ODSI, we have ODSI China. So people are doing translating stuff to like translate the Chinese version of electronic health records to this standard vocabulary so that the analytics tools available on ODSI, you can also apply it in your local hospital. But the thing for ODSI is, although they have a very good notion, so I mean, of course, they also care a lot about security, so they make all the analysis locally. So only a local hospital gonna do analysis on your own. But they don't do federated learning. So what they do is, let's say you build a prediction model, you got your result on your local hospital, and then you report your result to ODSI. And on ODSI level, they only do meta-analysis on the results. So they never touch the actual data across different institutions. So this is not, if you compare with federated learning, they are not really leveraged cross-institution patient data, but really you just do local analysis and then summarize the result. So that's why federated learning is more promising than this meta-analysis strategy. And this is a work where we did try on Mount Sinai's data. Mount Sinai is a hospital system including 5 different hospitals, and we tried using simple federated average on like linear model Lasso and also deep learning model multi-layer perceptron to predict the mortality risk of COVID-19 patients. And we compared like, for example, I mean, on the bottom right, you see the local, the pooled, and also the federated performance in terms of prediction AUC and 95% confidence interval. You see federated learning performs pretty well in this case. But if you look at the discrepancies, we also mentioned a lot. I mean, after Dr. Yang's talk about this non-IIDness, about the distribution of data over different local institutions. As you can see in the clinical medicine case, this thing is becoming more severe. Like in these 5 different hospitals within the Sinai system, you can see the distribution of the gender, the distribution of the age, ethnicity, and race are very different, and the p-value is pretty significant. So that means that these non-IIDness for clinical medicine is typically more severe, or maybe the situation is more severe compared to other situations. And this is a comparison of the model. Because of the distribution discrepancy, so the federated model is not always, it is not guaranteed that if you do federated learning, in this case, of course, it's federated average, you can get better performance than you just do your local training, right? In that case, then there is a problem. So when we do federated learning, our assumption is that all the local institutions, they are willing to participate in this exercise, right? So, I mean, doesn't matter you use whatever algorithm, but at least your local institution needs to be willing to participate. But this is not an easy case in clinical medicine. Let's say I am a hospital, I have 1 million patients, okay, the records. And if you tell me, if I participate in this federated learning exercise, there is no guarantee I can get benefit. Like my whatever I care about this local risk prediction models, then why do I participate? Because although you tell me this is secure, there is still a risk because I'm going to, somehow implicitly contribute my data. Okay, so then this comes to a interesting notion I'm going to mention later. I mean, that's about incentives. So why do I contribute? Another thing is, of course, about the security. Like Dr. Yang mentioned, I mean, federated learning, most of the cases we talk about the centralized version where there is a coordinator, but there's also the decentralized version. So this is one recent work we have done on how we tested about what if we add differential privacy on the decentralized version? I mean, asynchronous parallel decentralized stochastic gradient descent. We make an algorithm and show it, I mean, the balance between the noise we added and also the performance it can get. And this actually, this Nature paper is also about this warm learning. So it's really, you put a blockchain on top of this model parameters. When you want to communicate the model parameters, I mean, you have a kind of like what you do in the Bitcoin type of scenario, so make it more secure. But as I said, another interesting, important consideration is incentive. So if you ask me to participate in this federated learning, so why do I do that? So I mean, if you can tell me there is a guarantee that I can get benefit from this collaboration, because federated learning is essentially a collaboration with other institutions, then I mean, it will make this scenario more attractive. So we are thinking of this problem. So how can we handle the non-IID-ness or the distribution discrepancy among those different local institutions? And we first form some coalitions so that the nodes or the local institutions within the same coalition or union, so they can benefit when you do federated learning among a small group compared to collaborate with everybody. So we first, I mean, derive those local groups or coalitions, and then we do federated learning within the local groups rather than just simply collaborate with everybody. So this is one recent work we have done. And we can show in this case, I mean, we can, you know, a lot of times get better performance than just like a federated average, just, you know, require everybody to collaborate with everybody. And another thing is, so in conventional federated learning, we typically talk about, I mean, the thing we care about is mostly the model utility or the accuracy or the model performance. But as I said, so in medicine, so model utility is not just the single criteria we are looking at. So this a bias or disparity is also important. This famous science paper talks about you build a computational model to set up a score, and we build based on that score, you determine if this person is eligible for a particular healthcare management program or no. And through some investigation, they find that in order to make the person eligible, so for Black patient, they have to be much more ill compared to the white people. This is because some of the independent variables they make is implicitly correlate with the race. So this is gonna cause a huge social problem. So same thing in, I mean, another work we have done recently is when we do federated learning. So we do not just care about the model utility, but we also want for all the local institutions, the model is fair. So I mean, we don't care about the overall fairness, because when you deploy the model, it's going to be at local institutions, and at different local institutions, the population composition could be very different. So in this case, so we define some multi-client fairness. We essentially measure, quantify, quantitatively measures this model disparity locally, and then we set up some threshold, and we require the model to be able to achieve both fairness constraint as well as achieve the maximum utility. And we compared with some competitive baselines. We find that if you set up a disparity budget, so our algorithm can achieve a good, I mean very low disparity value, while at the same time maintains a high model utility performance. And this is another work we have done recently. So to summarize, first, so clinical problems are typically complicated with limited sample size, and the data are sensitive. So that makes federated learning with high potential and important. And before we can apply federated learning on clinical data, so typically we need to do data standardization or harmonization due to the heterogeneity and complexity of clinical data. Third, incentives or benefits are important to consider for participating in federated learning. We cannot naively assume everybody is willing to participate in federated learning exercise. Number 4 is, in addition to model accuracy, other objectives like model fairness could be important as well. That's all I want to talk about. I don't know if we have time for questions, but this is my email. Thank you.
Thank you very much, Professor Wang. You have really touched on a lot of important issues here. We have some time for simple questions. Maybe I can get started with one. We also work with healthcare data through our collaborators in China. We also need to convince the hospitals to want to participate. I'm wondering what kind of things that your medical collaborators find important as the kind of benefit they can derive that are important to them from federated learning. So what's your thought?
I think in order to let them buy in your idea, right? So you have to think in their way. So essentially to the clinicians, I think the important thing is, of course, like through federated learning, we can get better performance, because now I think a lot of clinicians know machine learning models are good and they need more data. With more data, they can potentially get a better performance. So that's what they need. But they typically have concerns about the privacy. So you tell them federated learning can have good privacy guarantees. So that will make them, very interested in this technology. But another thing is, as I said, so typically they want to make sure they have benefits. So if we tell them because of the distribution discrepancy, there's no guarantee that if you participate, you're going to get improvement, then they're going to get upset. So that's why we study this problem. We think it's pretty fundamental to encourage people to participate in federated learning exercise.
Okay, thank you. Any other questions from the audience? Well, if not, in the interest of time, we shall move on. Oh, I think there's one from the chat here. There is not a lot of work about federated learning on brain health. So what do you think about this area? Is any specific challenge compared to other medical applications?
Yeah, I don't know what you're referring to. I bet you are referring to neuroimage analysis. So I think for image and omics data, multi-omics data, like genomics, transcriptomics, metabolomics, so they have a natural advantage compared to clinical data to fit into federated learning framework, because they are relatively homogeneous. So like image, although you may have different device, but all the brain image looks like a brain, right? It cannot be like other things. And omics is the same. All the genes are with the same name. So you can think of they are more standardized or less noisy. So when you apply federated learning, it's more natural, or a lot of times maybe less heterogeneous. So there is a higher likelihood you will see the success. While in clinical data, as I introduced, so there are lots of other factors you have to consider before you can appropriately apply federated learning and observe the expected improvement you get. So I think that's part of the reason why we see a lot of research on brain health. It's not because of the brain health problem, it's really because of the neuroimage. Yeah.
Okay, thank you very much for your enlightening talk and
your
answers to these important questions. Thank you very much, Professor Wang. Okay, and next we shall move on to our second invited speaker of the day, which is Dr. Wang Shiqiang from IBM. So Shiqiang received his PhD from the Department of Electrical and Electronic Engineering from Imperial College London in the UK. So he is a research staff member at IBM T.J. Watson Research Center in New York City, and where he was also a graduate level co-op in the summers of 2014 to 2013. So in the fall of 2012, he was at NEC Lab Europe, Heidelberg in Germany. His current research focuses on the interdisciplinary areas in machine learning, distributed systems, optimization, networking, and signal processing. Dr. Wang served as a technical program committee member of several international conferences, including ICML, ICDCS, AISTES, Ijcai, WWW, IFIP networking, and so on. And he is also an associate editor of the IEEE Transactions on Mobile Computing. He received the IBM Outstanding Technical Achievement Award in 2019, multiple Invention Achievement Awards from IBM since 2016, Best Paper finalist of the IEEE International Conference on Image Processing, and Best Student Paper Award of the Network and Information Sciences International Technology Alliance in 2015. Dr. Wang, please.
Okay, can you see my screen?
Yes, yes.
Yeah, thank you very much for the introduction, and I'm very glad to be here. It was also very nice to hear both the previous talks. So I'm going to talk a bit more about robustness and efficiency in federated learning. To just set the stage, and also just I think to address a little bit of some of the questions we had before. I'm going to start with a comparison between cross-device and cross-silo federated learning. So cross-device federated learning is basically the case where mobile devices serve as the participants in federated learning, whereas cross-silo federated learning is usually where the participants are organizational servers. For example, in the case of a hospital where each hospital has its own server, we can consider that as a cross-silo federated learning. And the reason of doing this kind of a comparison is because I think really the major challenges in each of these are slightly different. Like, I mean, of course, we have common issues like security and privacy and so on, but I think one major challenge in cross-device federated learning is really the fact that you may have a very large-scale system, because everyone who owns a mobile phone would be a potential participant in the federated learning algorithm or the federated learning system. Whereas in cross-silo federated learning, we still may have a very large number of participants, but the scale is much smaller than in the case of cross-device federated learning. But there are also some things that are in cross-device federated learning that are not that challenging. For example, in cross-device federated learning, usually the underlying application is a mobile app. For example, it's a Google keyboard or some Facebook app and so on. So all the data stored in this app, they are usually more controllable, right? So you may have same or similar data structure across all the different participants. And also, it's really about refining some existing models, because, for example, you talk about network prediction in keyboards. It's like you may already have a model pre-trained on data that you have, but you want to improve the model. So you want to do federated learning in order to involve all the individual user inputs while preserving their privacy, and at the same time improve the prediction model that you use for that particular application. So in cross-silo federated learning, the data structure is one major challenge. I think some of us mentioned vertical federated learning. So the data could be vertically partitioned, meaning that you might have different parts of one data sample located on different servers, and you may have missing entries. Sometimes you may not have a certain entry of the data point, and you may have data that are relevant or irrelevant because just because of the heterogeneous nature of all the different organizations. And you may also want to train entirely new models. I think, as Professor Wang just mentioned about a clinical case, it's like you may not have any kind of a model to do some sort of prediction of, let's say, some disease, you may want to train an entirely new model. So that also raises the problems such as, for example, what kind of model you should choose and how to make the model efficient in training and also for inference in the future. So there are other things, for example, in cross-device, maybe the participants are usually the ones who really benefit from the model because they are the ones who are really using the application. In the cross-silo setting, it depends on the specific applications. And in some cases, maybe it's really a third party who wants to use the model instead of the ones who are participating in training. And there are common challenges and open problems such as efficiency, because in all these cases, the learning process is like a background task. So you don't really want to spend too much resource doing learning because you have other more important things in either cases that are happening on these federated learning participants. So what I'm going to talk about today are basically two specific technologies that we developed to address the robustness to diverse data sets and also to address the efficient communication and computation. And these are mostly motivated by the case of cross-silo federated learning because like this is, for example, what IBM and WeBank and other companies are more interested in. So in each of these two technologies, I will start with a motivational scenario, and then I'll talk about the challenge and also how to solve the problems. Like in the first case, we mainly want to find ways to filter out irrelevant data so that they don't participate in training. And in the second case, basically, we develop a model pruning technique to improve both communication and computation efficiency. So in the first case, so let's start with this kind of a use case for federated learning. This is a little bit from a more standard use case where you may have seen before, like everyone owns their own data and everyone wants to use the model. That's more like in the cross-device setting. So in the cross-silo setting, there could exist this kind of a use case where essentially you have multiple entities, which might be different organizations. And you have a server that could act as a broker. And you have someone who wants to train a model using data from these entities, but these entities may not want to reveal their data, but still they want to provide the model through the broker to the model requester, maybe because they can gain some profit based on that. So this idea is also related to this concept called data broker, which is essentially a business that aggregates information from many sources. It might not share the raw data directly. It might share some aggregated variant of that data, which in our case is the model in the federated learning. So one problem in this setting is because all these entities may have a lot of different types of data, right? As a very simple, although a little bit non-realistic example here is like, for example, you may have images of dogs and cats, but just for some reason, the data can be very noisy because maybe you didn't label all of them. Some of them might have been labeled using some pre-trained models and so on, so they may not be correct. And maybe in other cases, you just have, it's not showing this picture here, but you might have other classes that the model requester is not really interested in. Right, so in this case, what we want to do is, so we would like to find out which subset of data is relevant to the task requested by the model requester. Or in other words, we would like to filter out the irrelevant data, which could be out of scope data samples, mislabeled data, or just, I mean, they may have the same labels, but maybe the system is not able to interpret them in the same way. So the solution here that we have is relatively simple. It could be extended maybe to improve the performance, but basically the idea here is that we have a subset of benchmark data, which is provided by the model requester. But this benchmark data could be very small, could be just some very basic example saying, like, see, I want you to be able to classify these kind of images. For example, someone says, I want you to be able to classify cats and dogs, but I only have 2 cats and 3 dogs, right? But we cannot train a good model using the 2 cats and 3 dogs, but we can use the 5 images in this case, let's say, as the benchmark data, and use that to train what we call a benchmark model. And based on this, we can identify or basically apply this model to all the individual data samples that each entity has, and to evaluate their losses. And if we think that the loss is too large, then maybe this particular data sample is not really relevant to what we want to train. And if the loss is small, then we are more confident that it's relevant. So essentially what we do is we exchange all the losses. Of course, there could be a privacy issue here, although we might be able to solve them using some homomorphic encryption techniques, which is not covered in this particular talk. But once you have some ways to receive the losses by the server, you can calculate the threshold, which is based on the KS distance. And based on this threshold, you can select the data that is relevant, and then only using the relevant data for further training. So the results are shown here. So basically, we consider different types of noises. One is it's more like a balanced noise. It's like I have my target data samples, and also I have irrelevant data samples, but the amount of those two sets of data samples are almost the same. And there's also a strong noise case where we say most of the data samples that the clients have, they are irrelevant to what I want to train on. Right, so that's a more challenging case. But in both cases, what we can see is that if we use the simple data filtering approach, we can achieve almost the same accuracy compared to the case if you know what is the exact subset of data that you want to train on, which is usually not the case in practice, because you may not know which data samples are mislabeled just because you don't know the ground truth labels. Right, so and also the amount of data in a benchmark subset or the benchmark data set that the model requester provides, you can see even if it's only providing like a very small amount of samples, like 1% out of all the data samples that all the participants have, then we can still get a reasonably good performance. So that was mostly how to address the issue with irrelevant data. And the next topic that's sort of maybe related or independent is it's related in a way that if you filter out irrelevant data, you can also improve the efficiency because you just train the model faster. But just talking about the efficiency, what we would like to consider here is like, so basically this kind of maybe a multi-tier federated learning system, where in the first case, you could have a cloud server, an edge server. Edge server could be, for example, the servers in a hospital, or maybe, we have been looking a lot into different kinds of factories. Like you might have a server in the factory, and you may have different kinds of sensors, or maybe people working in those factories carrying their devices to measure what is going on in the actual plot, like some manufacturing and so on. So in this case, basically, if the server is trusted, then you could actually upload all the data to the server, because the server might be belonging to the same organization as the sensors and the devices. So in this case, it becomes similar to a standard federated learning setup. Although there's still a challenge, at least compared to the case where you have a pre-trained model, is we don't know what kind of model we want to use. Right. In the second case, it's more like a hierarchical federated learning setting, where you may have edge servers, but these edge servers could be those provided by 5G communication technologies. For example, in these days, if you can deploy some functionalities at the edge, which is close to the user, so that you don't have to send all the information through the whole network. And in this case, in the same way as standard federated learning, the data is kept on the devices because they cannot be shared with others. So for both of these settings, there's a general problem of how to improve computation and communication efficiency. And this is something that existed maybe since federated learning started. The other question here is related to the fact that we may not know what is the best size of the model that we would like to train. So how to generate a small enough model for efficient inference at either the edge servers or on the devices. So I think this part is also important, but probably hasn't been looked at as much as the communication efficiency problem. Right, so to solve this, there are, of course, different ways to solve this problem, including like using AutoML techniques or doing some sort of architecture search. What we have done here is to use model pruning, which can be seen as a basic way of architecture search or a simple way of architecture search. The idea, as you probably know, is basically to remove the unimportant parameters from the parameter set. For example, usually people remove the parameters with a small magnitude. The nice thing about model pruning is that there's this phenomenon that people have found empirically, which is called the lottery ticket hypothesis, which means that if you have a small enough model that is pruned in the right way, you can still reach the optimal accuracy as if you have the big model, right? And this is very useful for us because we would like to improve the model accuracy for both training and inference, which means that we can prune the model during training or during some initial phases of training so that we can start with a small enough model that would improve the computation and communication efficiency of federated learning. And at the same time, this model that you get from federated learning in the end will be able to give you a very efficient inference performance as well. So this is the procedure of basic model pruning in a centralized setting. Basically, you can prune during training, can train the model for one iteration, remove certain amount of parameters, and repeat the procedure. But in the federated learning setting, and also not just federated learning, so if we want to use pruning to speed up the training in general, there's this problem of basically we don't know how much we should prune. Right, and this figure is showing if we prune down by different levels, each level corresponds to this specific percentage of pruning. If we prune down, in this case, for example, up to 15 levels, the training is actually the fastest. And if you prune too little or too much, then the training will be worse. So the challenge here is how to find the best model size during training, because we cannot train a model and then see whether the training is fast or slow, because once you have trained a model, you have trained a model. Right, and then if you train the model again, that's not useful for improving the training efficiency. So we need to somehow find the best model size during training, and preferably during initial phases of the training. And also we need to do this kind of adaptation and also pruning in a federated setting. So how do we do this? What we have done is to use a two-stage pruning procedure. So first we prune at a single client, usually at a client that is, for example, more powerful than others, like you can do a lot of computation there. And after that, we do pruning together with federated learning in the same way as the centralized pruning is done, but basically you can only prune at the server. And we use an adaptive procedure to find the best size of the model. There are two objectives in this adaptation. First is to give a similar performance as the model before pruning, which is basically the same motivation as magnitude-based pruning. And it's essentially saying that the model gives a similar performance as justified by the loss functions here. But the second point is unique in this case of pruning for the benefit of speeding up training, right? So we want to maintain what we call the learnability in the future rounds. What it means is that you cannot prune the model too much. If you prune the model too much, then you cannot learn anymore. You might still converge to a certain accuracy, but the accuracy will be worse than the accuracy that you would be able to get using the original model. So we need to somehow maintain the learnability in the future. And to do that, we first approximate the loss reduction of a certain subset of parameters that we keep after pruning. And based on that, we formulate an optimization problem, which can be solved using this simple algorithm here. And the objective of this optimization essentially is saying, I would like to maximize my loss reduction or risk reduction per unit time in training. So for a given amount of physical time, I would like to maximize the reduction in the loss. Or in other words, it's intuitively equivalent to saying that you want to maximize the gain in accuracy, although it's not exactly the same. So here are some results, like we can improve both the training time and also the inference time. There's a little bit of jump here just because like if you have an unstructured pruned model, you would need to you would need to use sparse matrix multiplication that is less efficient than dense dense matrix multiplication. But if your sparsity is high enough, then it becomes more efficient than dense matrix multiplication. And just looking at the overall test accuracies, so basically this is the wall clock time, and if you use the prunefl approach that we have, you can see some degrees of gains in terms of the speed. Of course, depends on the architecture of the model and the complexity of the data set. Like in the ImageNet case, the gain is pretty small just because the model is already kind of small for this large data set. Okay, so in summary, we have discussed some characteristics of cross-silo federated learning, I think, and also motivated by some of those characteristics, we discussed some methods for filtering out irrelevant data and also to do adaptive pruning for both training and inference efficiency. And these are the two papers that related to this talk. We also had an earlier paper that recently won an Ijcai award, and also IBM has a platform of federated learning as well, maybe similar to some other companies. So I encourage every one of you to check out if you're interested. Okay, so that was my talk. Thank you very much.
Hey, thank you very much, Dr. Wang. It's always a pleasure to listen to your talk and learn about the latest happenings in IBM. So I'm wondering, since you mentioned that IBM has a platform to support federated learning research, can you tell us more about that? What kind of resources researchers from the universities can find there?
So basically, we have a commercial version and also a community version. The community version has open source interfaces. I don't think the algorithms are all open source, but at least you can basically use this platform and adjust it to your needs and I think read in your own data and so on. And you can call the different algorithms in that platform.
Okay, very interesting. Any other questions from the audience? Well, if not, thank you again, Dr. Wang. Also has been a pleasure to organize the federated learning ICML workshop with you.
Yeah, I think there are probably two questions.
Oh, okay. Some
so
in the chat.
I can quickly so in the progress of model pruning, it means that the proposed screen interprets federated learning model. Well, I would say interpretability is a separate question, right? Although you could, to some degree, you can say the pruned model might be somewhat more interpretable compared to the original model, just because you have less weights, like less connections between the different layers, and then maybe based on that you can derive the logic between different layers easier compared to the original model, which is basically like a very sophisticated representation, right? But I think how to use the pruned model to solve interpretability problems, that is probably a separate problem compared to our focus here of using the pruned model to improve the efficiency. So the next question is, how will prunefl be useful in cross-silo FL? I think I'm not exactly sure what exactly you're referring to cross-silo FL. I think the algorithm that I just described is still for the horizontal federated learning case. And if you want to do it in vertical federated learning, I think you can still do something similar. So basically, pruning is a very generic technique that you can apply to many different machine learning, well, basically different kinds of neural network models. But you would probably have to do it in a slightly different way, because in, let's say, vertical federated learning, you have these, basically the whole model is partitioned across different parties, and the local part of the model may represent some characteristics of each local party's data, and the global model would represent some other characteristics. So you would have to somehow consider this kind of split of the model across the different parties in the case of vertical federated learning, right? So the last question maybe to use pruning to improve training during federated learning instead of using a pre-trained model. I'm not exactly sure about the question, but in the experiments that I've shown, we are not using a pre-trained model. So we are essentially training a model from scratch.
Okay, thank you very much, Dr. Wang.
There's another question. Do we still have time, or I can also respond?
Yeah, we still have time, so please.
Okay, so can we combine pruning with other communication optimization techniques such as top case selection? Yes, I think that's a very good question. I think certainly you can combine these kind of different techniques for efficiency, including communication and computation efficiency. So you could potentially combine pruned models with I think I lost it, with the like top case classification in order to further improve the communication efficiency. Personalized FR, how to make use of information from related clients. That's again a very good question. I think you should be able, I mean, there could be ways to extend, like one basic approach for personalized federated learning is to train the model a bit further on the local data set after you have the global model, right? Or another similar way is to say you train the local model maybe and in a way that you enforce it to be similar to the global model. So in both cases, you can still continue to prune the model locally after you have the global model that is already pruned to some degree. How to represent robust in model pruning. I think this is a very good question, but I don't know the answer because I think by robustness, you can mean a lot of things. A lot of people talk about adversarial robustness. If you have attackers that tries to generate a different model from what you want to train on. And yeah, I don't have the answer to that. That case, I think, I mean, if you have attackers, in the case of model pruning, how would that affect the pruning result and how would that affect the final trained model? So I think that is probably an open problem that's worth investigating further.
Okay.
Thanks for all the questions.
A little hesitant to call it again. Okay, thank you again, Dr. Wang, for a wonderful talk.
Thank you very much.
Thank you. Have a nice weekend.
Thank you too.
Okay. So let's proceed to our invited talk number 3 from Professor Yin Wei. So she is an assistant professor in the Department of Computer Science at City University of Hong Kong since February this year. So prior to that, she was a senior researcher at the Machine Learning Center of Tencent AI Lab from November 2017 to January this year. So she works on machine learning and especially interested in solving challenges in transfer and meta learning, pushing the boundaries of both theories and applications. She received her PhD degree from Hong Kong UST in 2017 with the support of Hong Kong PhD Fellowship. Before that, she completed her bachelor's degree from Huazhong University of Science and Technology in 2012 with first-class honors. She has been invited as a senior PC member for AAAI and PC member for many other top-tier conferences such as ICML, NeurIPS, and SLR, and etc. Let me invite Dr. Wei to present.
Okay, thank Professor Yu for the kind introduction. Okay, could you see my screen?
Yes.
Okay, great.
Perfect.
Okay, great. So good morning, everyone. Today, I'm very pleased to share my recent works related to how to promote the generalization of a pre-trained model. So recently, I read a book called in Chinese, 暗时节 or Dark Time after translation. In this book, the author mentioned a very interesting experiment in psychology. So I looked up the literature and found that this experiment really tells us pretty much on how human beings generalize and some hints for successful generalization. So I use this example, this experiment to introduce my works, okay? So this is how the experiments was designed. We have a target problem called Dunker's radiation problem. In this problem, the college students are required to answer the question of how to kill the tumor without killing the healthy tissue. So the constraints include that array in high dosages will kill the tumor, but it will also kill healthy tissue in front of the tumor. And meanwhile, array in low dosages won't harm the healthy tissue, but it also won't kill the tumor. So to evaluate whether the students can successfully generalize, actually the students were told the Dunker's fortress problem and its solutions in previous courses. In the Dunker's fortress problem, the mines are set to let only small bodies of men to pass over safely. Therefore, in order to capture the fortress with the full army, the solution would be attacking in all directions. So in the road of each direction, there is only a small portion of the army passing through. So in psychology, the Dunker's radiation problem as the target problem and the Dunker's fortress problem as the source analog story. Okay, the left figure shows the results of this experiment in psychology. So without providing the have high intensity to kill the tumor. So surprisingly, even after the students were shown the fortress problem, there is only a 20% boost in terms of the students that gave correct answers. So the literature concluded that the spontaneous generalization actually is very challenging, right? So the authors conducted more experiments so that they identified the 3 factors that facilitate the generalization for students. The prominent one is actually hints. So by hint, we mean that students were explicitly told that the fortress problem can be helpful for solving the radiation problem. This significantly improved the success rate of generalization from the fortress problem for students from like 30% to 75%. The second one is the number and diversity of source analogs. In fact, researchers investigate whether 2 different source analogs improve the generalization compared to fortress only. We can see a further boost of the success rate from 30 to 39, and if no hint is provided, and from 75 to 79 with hints. So the diversity of source analogs also have influence on the generalization. As the fortress and the commander are both military stories, so that the rate is slower using fortress and Red Adele. So notice that the Red Adele is about how to put out a burning oil well, provided that enough water can't be delivered from any one direction. So the solution is to direct the streams of water and the well from many directions. So it is actually a different category of story than a fortress. The last one is to specify the principle of the fortress problem explicitly to students. This also boosts the success rate from 75 to 8 if hints are provided. So what can we learn from this experiment? Can similar ideas also work in generalizing a pre-trained model in machine learning? The answer is obvious yes. I guess everyone knows the answer, right? So consider a pre-trained model here, and our target task is to like predict the activity of drug molecule and against a target protein. Since like the high throughput screening of drug molecules is actually very expensive, so that the target task is definitely a few shot learning problem. So providing a hint in this case boils down to answering this question, that which pre-trained model should be used for the target task, supposing that you have a lot of pre-trained models accessible. We have proposed a frustratingly easy transferability estimation measure without any optimization to select among different pre-trained models, pre-trained on different source data sets, or to select a self-supervised pre-trained models, or to select the supervised pre-trained models in different architectures. So the x-axis is the testing accuracy after fine-tuning, and the y-axis is the source. It is a score of our proposed transferability measure before fine-tuning, actually. So this high correlation shown in this figure demonstrates the proposed measure is efficient to use even without optimization, and almost perfectly predicts the transfer learning performance after fine-tuning. So we can use it to inform the target task, which pre-trained model to use beforehand. So if you are interested, please kindly check our paper for more details. So in accordance with more diverse source tasks, so the question of interest is, can we involve more tasks that are used to pre-train this model? Before proceeding to detail how to augment as many tasks as possible to pre-train the model, we first of all introduce one representative training framework that uses episodes of tasks to pre-train. So it is more commonly known as gradient-based meta-learning. In this episodic pre-training framework, actually we have like many tasks from 1 to n to simulate the real scenario where many tasks are available to be learned from. Each task TI here consists of the support set and the cure set, which can be regarded as the training and the testing set in traditional machine learning. The pre-training is actually a bi-level optimization problem. First, the pre-trained model θ0 will be adapted to each task while several gradient steps on its own support set to obtain the task-specific model θi, for example, θ1 here. Second, the performance of the task-specific model is evaluated on the query set of all tasks to see whether the pre-trained model is on average a well-generalized starting point for all tasks. If the average loss of all specific models is large, the pre-trained model θ0 will be optimized with a large loss, actually. So in this episodic pre-training framework, there are indeed some bad consequences of insufficient task when generalizing the pre-trained model θ0 to our target task, for example, the T's task. We call the process of obtaining the pre-trained model from this previous n task as meta-training, and the process of generalizing the pre-trained model θ0 to our target task as meta-testing. Also, look at this figure shown in the right. The shallow green line represents the performance of θ0 on this one, on all meta-training tasks, and the dark green line shows the performance of task-specific models after adaptation on all meta-training tasks. Similarly, the shallow and the dark blue line represent the performance of θ0 and the adapted model on our target task. So from this figure, we can actually observe two types of severe meta overfitting. The first type of meta overfitting is learner overfitting. It is analogous to traditional overfitting, where actually θ0 only overfits to meta training task and cannot generalize to our targeted task. This is supported by the large gap between the shallow blue line and the shallow green line, indicating the consistent performance of θ0 on the meta training tasks and on our target task. The second type of overfitting, however, is more complicated and is specific to this episodic pre-training framework. We call it as memorization overfitting, where adaptation while the support set improves marginally compared to using the pre-trained model θ0 directly. So during meta training, we can see that the performance of the adapted models on all tasks indeed improve a lot compared to the performance of θ0, right? However, on the targeted task, the gap between the performance of θ0 and that of the adapted model seems like decreased a lot, right? This happens because the pre-trained model theta 0 is actually so powerful that it memorizes all tasks without the real task-specific adaptation. There has been like some preliminary work trying to augment meta training tasks in order to alleviate the meta overfitting. The label shift algorithm proposed in 2013, I think it's in Europe, augments a task by adding a random noise to the labels of both the support and the query set. For the ICE task, the features of both sets remain the same, but for labels of both sets, a random noise, randomly sampled from the Gaussian or uniform distribution is added. This indeed increases the uncertainty for inference, as the pre-trained model actually is updated according to the performance of adapted models on the query set. To address the learner overfitting and improve the generalization capability of theta 0, actually we expect the augmented task contribute extra knowledge or information, that is the mutual information between the pre-trained model theta 0 and the augmented task should be greater than 0. Unfortunately, it is not the case for the label shift algorithm, which means that the little extra knowledge has been introduced to theta 0. The empirical results also verify this. We can see that the gap between the shallow blue line and the shallow green line indicate of the gap between the performance of theta 0 on meta training tasks and on our targeted task actually does not decrease too much compared to without any task augmentation. So regarding the memorization overfitting, by introducing the same noise into both the support and the query set, the label shift algorithm expects the adapted model to depend on the support set more with more adaptation via this random noise. However, learning this constant actually is as easy as only modifying a bias, so that the improvement is quite marginal. As shown in the figure, the gap between the shallow blue line and the dark blue line representing the performance gap between theta 0 and the adapted model on our target task does not actually increase too much. Then we are motivated to ask what the criterion for an effective task augmentation strategy should be. We propose these two criteria to combat the two types of overfitting. The first criterion is that the augmented task should contribute additional knowledge to update the pre-trained model theta 0, as mentioned in the previous slide. In other words, the mutual information between theta 0 and the augmented task should be greater than 0, conditioning on the given original task. In this way, the augmented task can improve the generalization ability of the pre-trained model on the target task, so that the learner overfitting can be elevated. The second criterion is that the adapted model must rely on the support set to make predictions. Mathematically, we represent the criterion that the mutual information between the predictions of an adapted model on our augmented query set and the original and the augmented support set should be greater than the mutual information between the predictions and the original support set. By this, we said that the adapted model relies on more on the support set. So we have proved that actually conventional data augmentation techniques and the conventional regularization techniques and also the label shift algorithm proposed for meta learning actually do not meet both criteria. Therefore, we propose a new task augmentation strategy named MetaMix. As shown in the right figure, MetaMix does not actually alter the support set, but generates a new task by varying the query set. Specifically, the augmented query set is a mix-up of the support and the query set. the features of the augmented Curie set is a convex and a linear combination of the else layer features of the support and the Curie set, where the value of the lambda is actually randomly sampled from the beta distribution. The labels are correspondingly mixed up using the same value of lambda. For each task, we mixed up actually we can sample different values of a lambda from this beta distribution and the different layers of features so that we can create as many tasks as possible. With this augmented task, so the next question comes, how can we use them to improve our generalization ability? Recall that in the episodic pre-training, the theta 0 is updated according to the performance of or adapted models of all tasks on their Curie tasks, right? So we can use this augmented task by replacing the Curie set with the corresponding mixed version of it. More importantly, we have proved in our paper that the proposed meta mix satisfies both criteria and serves as a potentially effective task augmentation strategy. So how it performs empirically, and can the proposed meta mix empirically elevate these two types of overfitting? So we have evaluated on the drug activity prediction problem. We observe here that meta mix significantly reduces the gap between the performance of theta 0 on meta training tasks shown in the shallow blue line and the performance of theta 0 on our target task. Shown in this, yes, this is shown in the, this is green line shown actually indicate the performance of theta 0 on meta training task, sorry for that. And this is the performance of theta 0 on our target task. So that you can see the gap is significantly reduced because of the more consistent performance of theta 0 between on the meta training task and on our target task. This indicates that meta mix, as expected, is quite effective in alleviating the learner overfitting, first of all. So besides the learner overfitting, meta mix also significantly increases the gap between the performance of theta 0 on the target task, shown in this shallow blue line, and the performance of the adapted model on the target task, shown in this blue line, dark blue line, okay? So this indicates that meta mix can effectively alleviate also the memorization overfitting to learn a pre-trained model theta 0 that can generalize to our target task with sufficient adaptation guaranteed. And we would further compare the effectiveness of meta mix improving the generalization capability of the pre-trained model theta 0 against other baseline methods. We compare against the original mammal, the mammal with like weight decay, and the 3 meta regularization techniques, and also the labor shift we have introduced. So this results on the 3 different applications, including drug activity prediction, pulse regression, and mini ImageNet classification, show that the meta mix can consistently improve the generalization under few shot settings by a very large margin, okay? So we know that mammal is only one kind of episodic pre-training algorithm, but we have a lot of other meta-learning algorithms which can be regarded as different episodic pre-training algorithm, including meta-SGD, TNet, and ANIL++. So we want to investigate whether those augmented tasks by meta mix can also contribute to other pre-training algorithms and be compatible with them. So the results in these 3 figures show that MetaMix is indeed compatible with different pre-training algorithms. For either of them, MetaMix largely boosts their generalization ability on our target tasks. So far, we have empirical evidences to support the effectiveness of MetaMix, but we still have no idea why MetaMix can improve the generalization from a theoretical perspective. Here, we consider a simplified version of our problem so that we can conduct a theoretical analysis. They are here consist of both the support and the Curie set. consists of a total of km samples. Following the previous definition of metamix, X and Y are in a convex combination of their corresponding features and labels. What differs only in the theoretical analysis that now we consider a simplified neural network with only two layers. The first layer is parameterized by W here, followed by a sigmoid or other activity, nonlinear activity function. And the second layer is parameterized by this phi I. First of all, we conclude that metamix is actually imposing a quadratic regularization on the adaptive model phi I, as shown in this second term. Next, we show in the theorem that the generalization bound for the defined neural network consists of these four terms, while gamma is actually the upper bound of this regularization term. Therefore, we conclude that metamix actually achieves beta generalization by making the regularization term as well as the upper bound gamma as small as possible. So you are welcome to plug in the proposed metamix to all your meta learning algorithms, and you can kindly check our repository at GitHub shown here. And so far, we have introduced how to achieve beta generalization by introducing hints and by increasing the number and diversity of tags. We are still left with the last question. Can we specify the way we adapt a pre-trained model? So we propose the transfer example learning in this case, where we automatically learn a set of M transfer strategies. We introduce the total transferability, which measures the degree of knowledge transfer from the source to the target task. By sliding the value of total transferability from Cmax to Cmin, we are capable of obtaining a spectrum of transfer strategies and thereby different target models ranging from pure exploitation of the source domain to pure exploration on the target task. Or the target models serve as the base models, for example. As shown in the right figure, the proposed translator actually achieves better generalization performance compared to other fine-tuning baselines and the simple example baselines. Okay, so that brings us to the end of the presentation. I'd like to thank you for your time and attention. Any questions are welcome. Thank you.
Thank you very much, Professor Wei.
Okay.
Any questions from the audience? We still have some time to interact with the invited speaker. So Professor Wei, recently, one of my students is working on also working on the area of transfer learning. Maybe the participant a little bit need a little bit of heads up. This is a federated and transfer learning workshop, so we do have invited speakers from the transfer learning field. So we were working on projects involving quite a large company, and they have a lot of data coming in every day. And the training of a model just based on the data is very, very inefficient. And we were looking into whether we can leverage the technology of data distillation to try to reduce the size of the storage first, and then try to see if we can do transfer learning based on distilled representation of data. I don't know whether you have any thoughts on this.
Of course. Knowledge distillation is actually another pipeline of fine-tuning. Actually, we can think of as another version of the fine-tuning by like imposing some regularizations on the feature representations. So yeah, I think knowledge distillation is specifically effective in reducing the complexity of your models to do like the model compression. Yeah. But I think if you are preferring to like preserve the complexity of your model, I think knowledge distillation may be not that effective as expected. But I think it's more effective in like model compression. Yeah, but some other higher like a technique, more advanced techniques imposing the regularization between these two model, like the activations between besides the activation regularizations, like some like the gradients regularizations, so that you can achieve like a better performance, or you can like selectively imposing the regularizations to select some source examples or some target examples to make this regularization more effective. Yeah, I think there are indeed some advanced techniques to improve the knowledge distillation. Yeah.
Yeah. Thank you. Yan Li is asking, what's the physical meaning of the quadratic regularization in lemma 1 of your slides?
Okay, yes, sure. So the physical meaning of the quadratic regularization in lemma 1 actually to characterize the covariance of the model, the last layers model, in terms of its correlation between the data correlation. So you can think that the quadratic regularization is actually the correlation or covariance between the data and our model, so that you can think of it like a complexity regularization on the last layer. Yeah.
Okay. Any other questions from the audience? Well, if not, thank you again, Professor Wei, for your interesting talk. And we are going to have a short break for about 10 minutes. And we're going to come back at around 10:30 a.m. Beijing time or 10:30 p.m. in Montreal time, whichever you prefer. Okay. So let's have a short break first. Okay. Thank you. Okay, welcome back to our workshop. Let's continue with today's program. So we will have our first contributed oral presentation session. Each talk will have 15 minutes in total, including Q&A. So the first talk is on towards personalized federated learning. So Alisa, please share your screen. Okay, we can see it. Okay, please proceed.
Hi, I'm Alyssa. I'm presenting a survey paper on personalized federated learning. The other authors of the paper are Professors Han Yu, Li Zhencui, and Qiang Yang. Right, a quick review of the vanilla federated learning setting. It comprises 4 phases. First, we have the client selection phase, where we select a subset of clients to participate in each training round of federated learning. There's a global model in the server, which is broadcasted to the selected clients. After that, local model training is performed by each client by updating a global model on its own local data. And finally, global model aggregation of the local model parameters are done. Right, there are a couple of issues with the vanilla federated learning setting, which is also the federated averaging algorithm. It does not perform well when the data is heterogeneous. There's a phenomenon known as the client drift that occurs when the local data distributions are highly different from the global distribution. Sorry, hold on. As a result, the global model does not converge well to its true global optimum. And another issue is that there's a lack of solution personalization because it trains a single globally shared model, which just fits the global distribution. And so if we have a local distribution that is very different from the global distribution, the global model will not be able to generalize well. And so personalized federated learning seeks to address these 2 issues. As compared to the typical standard FL setting that we have, PFL has the assumption that data is more heterogeneous. The model should therefore have good performance on heterogeneous data, and we would also want to have some form of a personalized solution. Right, so we can view personalization from the perspective of taking a trained global federated model and then personalizing it on local data. The idea here is to train a strong global model under a data heterogeneity. And this builds on to the vanilla FL setting that we have been talking about. And the other way to learn is to learn a personalized model using different federated learning paradigms. And each of these approaches enables personalization to be done in a different way. For example, multitask learning, it learns personalized models by modeling client relationships, and clustering allows for personalization at the group level. I'll briefly introduce the personalization techniques. First, we have database approaches. So it approaches the problem from the perspective of reducing the heterogeneity of data distributions, as data heterogeneity is the primary reason for poor performance. And so there are data sharing, data augmentation, and client selection methods. The idea for data sharing and augmentation is to have a more homogeneous distribution at the clients. However, by doing so, they often involve a certain degree of privacy leakage, like the sharing of data samples or data statistics. The idea for client selection methods is to sample from a more homogeneous data distribution. Next, we have regularization. This is to improve the generalization of the global model. We can also, we do this by performing the regularization between the global and local models. This is done by introducing a regularization term to the local loss. For example, FedProx uses L2 norm, and there's also Moon, a recent algorithm that was proposed that's using contrastive learning. So what it does is that it tries to reduce the distance between the global and local models to prevent client drifting. And at the same time, we want to speed up convergence, and this is done by increasing the distance between the local model snapshots. And next we have meta learning, which was covered very comprehensively already in the talk before this by Professor Ying Wei. Meta learning is used to improve the global model, but also with a goal of fast adaptation, also known as personalization on a client. So to do that, we will modify the optimization objective. In standard FL, the goal is to minimize the aggregated local loss across our clients. But for meta learning, the goal is more to perform well, for the global model to perform well after it is updated with a few steps of gradient descent. And so this is the new optimization objective. Note that it is computationally expensive for gradient computation. So we typically make use of gradient approximations. And next we have multitask learning. The idea is to train a model involving several related tasks. And this improves model performance as it leverages domain-specific knowledge across the different learning tasks. So in federated learning, we can treat a client as a task. A personalized model is learned for each client, while modeling the client relationships to improve the model performance. So the MOCA algorithm was like one of the first frameworks that extended multitask learning to the federated setting. It also addresses communication and system challenges. However, it's only applicable to convex models. Since then, there are a couple of multitask learning algorithms that are proposed. We have FedAMP that builds a personalized cloud model for each client in the server. And the cloud model is, each cloud model is a linear combination of the different local client models. So the idea is to try to enforce a stronger pairwise collaboration for clients with similar data distributions. And so the result will be that like related clients will learn more similar models. Next, we have model interpolation, where the idea is to learn personalized models using a mixture of global and local models. This to achieve a balance between generalization and personalization performance. In APFL, a mixing parameter is introduced. It is adaptively learned to control the balance between the global and local models. So in this way, it enables the optimal degree of personalization to be learned for each client. In this sense, if the local distribution is very different from the global distribution, we expect to see a larger weighting factor so that there's a larger contribution from the local model. So the model is more personalized. And next we have parameter decoupling. The idea is to have a set of private parameters. And these private parameters are only trained locally and are not used in federated training. And so there can be personalized layers where we only use the base layers in federated training. And there are a few deep layers for each client that are kept private. There can also be personalized feature representations where we keep the feature representations or embeddings private. So an advantage of doing so, as covered by this paper here, is that it offers some flexibility for us to design more specialized encoders, especially if we are working with different data modalities. It also allows fair representations to be learned. And there's a recent paper that did a study to explore the privatization strategy. So what it did was to use different combinations of network splits for privatization. And next, we have clustering. Clustering allows for group level personalization. So this is good, especially when we have data distributions that are significantly different, when there are inherent partitions that exist in the data. So using this multi-model approach will be more appropriate for this kind of applications as compared to using the vanilla FL setting where we just train a globally shared model. So the idea is that to first use a clustering algorithm like hierarchical or k-means clustering to partition the clients. And then after that, FL model can be trained for each client cluster. Finally, we have knowledge distillation. The key advantage of knowledge distillation is that it allows a personalized architecture to be learned for each client. And it also tackles communication and computation challenges. So knowledge here is commonly represented in the form of like the logic output or class scores. In the standard federated setting, the local and global models are assumed to have the same model architecture due to the aggregation procedure. And so if we try to distill knowledge in other means, we can maintain a different model architecture per client. So in FedMD, learning is done through a consensus result, which is computed on a public data set. So this constitutes the average class scores. And each client trains its model on the public data set to approach the updated consensus and thereafter perform personalization on its private data set. And next we have FedDF. So for FedDF, it assumes a setting where each clients require models of different model architectures as they have different computational capabilities. So model architectures like we have a ResNet, which is a lot larger, and mobile net, which is smaller for each devices that do not have that much computation power. So the idea is that the server first constructs a number of prototype models. These models represent the clients with the same model architecture. So first, we perform federated averaging amongst the clients from the same prototype group. This serves to initialize the student model. And next, cross architecture learning is then performed via distillation. So in this case, each client model is like the teacher model. It distills knowledge onto the prototype model. So we allow distillation throughout the clients in the network to distill knowledge like across the architectures. That's the end of the presentation. Are there any questions?
Okay, thank you very much. Any questions from the audience? Okay, Alisa, is throughout this survey, what kind of evaluation techniques and that people use to evaluate personalized federated learning techniques?
So for personalized federated learning, typically, I guess the most common one would be like just using accuracy. There's not really like a benchmark that I'm aware of for this. So it's more quantitative as of now.
Okay, if there's no more questions, thank you very much. We shall move on to the next talk. So the second talk for this session is on robust federated learning with attack adaptive aggregation. Is the speaker here? Okay, yeah. So I see. Okay, hi. We can see your screen and hear you. Okay, please proceed.
Great. Welcome all to my talk on the robust federated learning with attack adaptive aggregation. This work is done by me, Cheng Pui-Wen, and my supervisor, Chi-Fung Chen. Federated learning is vulnerable to several adversarial attacks, even we use current existing defenses. The attackers may perform the model poisoning. They may launch the nuisance attack, which they multiply the update vector, delta WI, by the negative constant. They do so trying to reverse the training direction of the federated learning. And the attackers can also manipulate directly on the data. They may change the labels of the data to confuse the model, or they may even inject some backdoor, or we call it a trigger, into the data. And once the model encounters these similar triggers, then they will predict it wrongly to a target label assigned by the attackers. So there are many challenges in the attack in federated learning. And to address these challenges, multiple works on the aggregation strategies has been proposed. The most classical aggregation rule, the FedF, is not robust at all because it simply performs the simple averaging. Multiple statistic-based aggregation rules like the coordinate-wise median, RFA, the residual-based reweighting, try to address the issue by using the classical robust statistics. However, in federated learning, we have the heterogeneous data distribution, and this statistic-based method does not work so well. And we also have the clustering-based approach, like the Fusco and Crumb. Fusco assumes the similarity among the attackers. Crumb assumes the similarity among the belied clients. However, the clustering-based approach can be easily bypassed by the attackers if the attackers shift their corrupted update factors towards the belied ones. And on the other hand, there are some interests and there's some works on discovering the specific structures and patterns of the update factors in federated learning. For instance, the work with DP found that by clipping the update factors and by adding some noise into it, certain types of attacks may be cancelled out as we go on our training. The work VAE-based detection found that the belied update factors looks more similar to the unbiased update factor that we obtain in the centralized training setting. And with the challenges of the attacks in federated learning and the recent interest in discovering the specific structure and patterns of the update factors in federated learning, it leads us to the research question on whether we can design an attack adaptive defense strategies for robust federated learning. That is, instead of designing a generic defense, can we do more if we know about the attacks? Can we build a strong defense against a specific type of attacks? And the attack adaptive defense strategies will have certain properties. First of all, it is data-driven. So in order to get the most of the knowledge on the attacks, we collect empirical data by the simulation of federated learning tasks on a data set in server. In practical application, this test set may be some open data sets or a small subset of data samples that we collect from the clients. By attack adaptive, we mean we want to build a model, a defense model, to identify the vulnerable regions of a model under different type of attacks. For instance, for certain types of attacks, maybe the downsampling layers in a certain CNN layers is responsible for the unexpected behavior. Maybe for another type of attacks, the last few fully connected layer is responsible. So we want to build a model to identify these vulnerable regions. And with the attack adaptive defense strategies, we may build our defense incrementally when we are aware of new types of attacks. When we are aware of a new type of attacks, we may just simulate the attacks, and then we build a defense model against these type of attacks. And compared with the previous generic approach, the attack adaptive defense strategies is more interpretable in a way that you can identify which type of anomaly a client is suspected of, so that we provide more transparency when we are trying to reject a client. And to achieve the attack adaptive allocation, our defense model has a primary goal to approximate the robust mean, which is the average of only the belied update factor Xi. And our defense model should take a set of update factors as an input. First of all, yes, to permutation invariance, because the clients may submit their updates at a different order. And also, it should be flexible with the number of clients, because we want that once we have trained our defense model, we want it to be reused when we grow the numbers of participants in the federated learning. And even better, it would be the best if we can use the defense model together with the current existing defenses. And that's how we arrive the iterative form of estimator to approximate the robust mean. First of all, we have the initial guess Q0, which can be computed from the classical robust estimator. For instance, we use the coordinate-wise median. And after that, we compute the probability of whether the update factor Xi is a belied update factors given the previous robust estimate. After we compute the probability, we reweigh the update factor and we get the next robust estimate. If you look closely, we can find that the robust estimator, the QT here, is very similar to the definition of the robust mean. The robust mean is just the average of only the belied clients. We just replace the indicator function here by the probability terms, which we replace it with the previous robust estimate. And to approximate this probability, we use the attention mechanism. Specifically, we fit our robust estimate into the QA encoder, and we fit the update factor xi for each client I into the key encoders. We compute the alignment score to measure the similarity of the previous robust estimate in each of the update vector xi. And we get the alignment score si. We feed it to the softmax with temperature, and we use a large constancy to scale up the alignment score so that the coefficient here can better resemble the coefficient in our robust estimator. And after that, we add a truncation step to remove the contribution of suspicious update vector if they have too small attention weights. And that's the overview of our neural network that is used to defend the several attacks in federated learning. Given a set of update vector, we feed the update vector into key encoders, and we feed our robust estimate into the key encoders. We compute the alignment score and attribute them to the value encoder here. And for the value encoder, we simply use the identity. And so we attribute the weight directly on the update vectors. And the key encoder and the key encoder, we use the two-layer MLP. They have a very simple structure. And finally, we pass through the attention module for multiple iterations to get our final attention rate and our final robust estimate. And we encourage the predicted robust estimate to better resemble the robust mean that we simulate from the simulation in the test set. And here comes the results of our experiments. We perform experiments on different scales of image datasets, like MA, Cyber-10, and Tally image methods. And we perform experiments against combinations attack and backdoor attack. One of them is the model poisoning attack, another one is the data poisoning attacks. And we find that our approach can have almost perfect defense when there are 1 to 2 attackers. And our approach, our data-driven approach, perform the best when there are more attackers. So we can see the potential of the attack adaptive defense strategies when we are trying to defend our adversarial attacks in federated learning. Also, our approach works across different domains. Not only the visual task, our approach works also for the textual task. And we looked at our approach is the only one that works when there are 4 attackers, where we have 10 participants in total. We also investigate on the transferability of our defense. We train our defense model only on the data that we collect from the Cyber-10 federated learning task when there are 10 clients with a fixed backdrop patterns. And then we evaluate our defense on a different data set, the Cyber 100, and on the different numbers of participants, like 100 participants, and different backdrop patterns. And we found that when there are lower fraction of attackers, our approach can generalize pretty well. And our approach can generalize very good to different backdrop patterns. This indicates that our approach, our attack adaptive defense strategies has the potential to defend challenging attacks. And in summary, in our work, we have designed an attack adaptive and data-driven approach to defense challenging attack in the federated learning. And we found that our attention mechanism is effective in propagating the information across different clients. And I hope that our work can inspire more works in the relevant direction. So here comes the Q&A session. Any questions on our work?
Thank you very much. It's a very important area of attack and defense in federated learning. Any questions from the audience? Can feel free to type it or speak up. Okay. Well, I have some questions about this is definitely a very useful tool if we can dynamically determine what kind of attack is happening and deal with it. I'm just wondering, in your experiment, have you thought about distinguishing between attackers, malicious attackers, and people who just have low quality data that can negatively impact model performance?
Yeah. So our approach is attack adaptive approach, and we collect the data from the simulation of a certain type of attacks. So we can adjust like the threshold of how different the update vector has to be in order to flag it as attackers. And this threshold is again we can tune it with the simulation. And now what we found that the patterns that appear in the update vectors with respect to different type of attacks are very different. So I think we can somehow distinguish between the attackers and the clients that have a low quality data.
Okay. Oh, there's a question in the chat. Can this method defend against data poisoning attacks?
Yeah, sure. So in our experiments, we look at two types of data personalization attacks, the label flipping attack and the backdoor attack. And our approach shows promising result and competitive performance.
Okay, much. If there's no more questions, thank you again for coming, and we can move on to the next talk. Thanks.
Thank you.
Okay, next one, the third talk, the third talk of this session. We have a paper on a contract theory-based incentive mechanism for federated learning. Is Professor Liu Yuan, are you here? Are you ready?
Yes. So can you hear me?
Yeah. Yes,
okay.
Yes.
So I cannot share my screen.
Oh, let me set you as a co-host.
Okay.
Okay, can you try now?
Yeah.
Okay.
Okay. So now on behalf of our research group, I will present our recent work on the contract theory based incentive mechanism for federated learning. This work is cooperated by the students of Northeastern University of China and Ze Hui-xiong from Singapore University of Design, Technology and Design, and also Professor Liang and Chunyan Miao from Lily, NTU, and School of Computer Science and Engineering. My presentation will include these 5 parts. So before move on, I will introduce the basic concept of the incentive issues in federated learning. So federated learning is a new machine learning paradigm which can preserve training data privacy. There are 2 roles in this learning platform. So FL server and FL task clients. So they cooperate collaboratively to train a model task. So on a typical procedure of FL platform, a task request will post the task to the FL server, then it will publish to the clients to train the model. After the model is trained by the clients locally, the clients will submit to the local model to the FL server. Then the server will aggregate the local model gradients to get the final model. Then upon the model is satisfied, then it will return back to the task requester. So here, the FL clients are very important for the final model accuracy. So we should provide sufficient incentives for them to participate in this learning process. We will try to promote their incentives on the 2 aspects to promote them to contribute high quality data and high compute power to train their local model. And the motivation of this study have these 2 aspects. So first, the incentive issues have been well recognized by the community of federated learning. And some works have been done on the aspects of modeling it as a adverse selection problem with asymmetric information, but not so lot have focused on the moral hazard problem. So we will, in this work, we will consider these 2 problems in one system. Second one is that there are many types in FL clients in participate in FL tasks. And some of the existing research studies only focus a single dimension, for example, the data size or data quality. And in this work, we will consider multiple dimensions for FIL clients. The contributions of this study are summarized in these 3 aspects. So we have designed a contract theory-based FIL framework. We have improved the traditional platform framework to encrypt the contract in the design of the incentives. Secondly, we propose a multi-dimensional contract model. Here, the participants are modeled with 2 tabs. They are the data quality, data coverage quality, and effort willingness. So they are corresponds with the adverse selection and moral hazard problems. We also solve the optimal contract solutions. Thirdly, a contract-based aggregation scheme is designed to improve the model generation accuracy. So in this figure, we can see the proposed contract theory-based FIL framework. So here we will involve the same rules, the same 2 rules for players, but differently. We will add the tab 3 and tab 6. In step 3, we will cite contracts for the FIL clients to choose. So the contract is shown in this format. A contract option includes 2 components. The first one is the registration fee. It voluntarily registered to the task, and the second component is the reverse. It has a function. And in the step 6, after a local client finishes the task, it will submit to the server. Then the server will reverse the clients according to their chosen contracts. And the 2 private types of clients are listed in this slide. So the first type is data coverage quality. The data coverage quality is modeled as the data site, the summary. The coverage, the data quality of the data samples. So it's measured by each of the samples of the data of a local client. The second type is the data training willingness. So the willingness is reflected by a client as the accent of the client taking the efforts in a task training. It has a very close relationship with the cost of a single client by participating FIL task. Taking these 2 tasks, we model the utility of a client and the server. For the single client, with their utility is closely related with their data coverage type and the effort willingness type. The utility of a server is reflected. So in the cost of a client in training, there are 2 parts. The first part is the registration fee, FI, and the second part is related to the willingness. The utility of a server has the income of the registration fee and the minus the rewards it offered for the clients. And based on the contract model, the types of clients, we formalize the contract model as an optimization problem with the objective of maximizing the expected utility of FIO server with the contracts of FIO clients. So there are two types of constraints. The first is referred to as individual rationality constraints. These constraints aims to ensure all types of FIO clients can achieve positive utility. The second type of constraints are referred as incentive compatibility constraints. It ensures that every type of clients can achieve their maximum utility by choosing a contract which is specially defined for designed for that particular type. So based on the contract model we have constructed, we further propose a contract-based model aggregation. So following the contract they chosen, we will further set the weights for different models submitted by the clients. So their weight is proportional to their rewards. We solve the optimal contract solutions to the proposed contract model. So we will consider we will decrease the number of constraints by considering the monotonicity of the types. So we finally find that the constraints are not so complex. We can only consider the one individual IR constraint and the I type of suppose the number of the types is I, then the IC constraints can be decreased to the same number of the types. Finally, we got the optimal solution of the contract. So we solve the for the first component of the contract FI, and also set the corresponding rewards. We conduct experiments to evaluate the proposed model. We set 10 types of clients in based on the data set, the real data set meanest and C5-10 data sets. The detailed sightings of the 10 types of clients is listed in this table. So the data size in our experiments reflects the data coverage type. Also, the willingness is also set according to maximize their each type of the clients. And we set in our experiments, we set 3 schemes, where the first scheme is the contract-based rewarding model proposed by our model, and we also use the contract-based aggregation. In the second scheme, we use the contract-based rewarding and feed average aggregation protocol. So in the third scheme, we set the rewarding as a consistent rewarding. We also also regard as the same rewarding. And the aggregation algorithm is the feed average. So we compare their generalization accuracy on 2 data sets, meanest and C5-10, and we can observe that our scheme, our model based on contract theory can achieve the best performance in different parameter settings. To further understand the observed results, we also conduct these 2 experiments to observe the reasons behind the performance of our model. We can observe that the server can achieve more significantly higher profit from the clients with high quality, with high type value, and there the optimal contract for each different type is optimized when they choose their design type, the contract corresponding to their type. So this also reflects the IR constraints that satisfied. So in conclusion, so we have proposed a contract model-based incentive mechanism for federated learning and designed a two-dimensional contract model. We also improved the generalization accuracy by designing a contract-based aggregation protocol. Optimal contract solutions is analyzed. Finally, we do experiments to improve, to evaluate the proposed contract-based incentive mechanism. Okay, thank you very much. So any questions?
Okay, thank you very much, Professor Liu. We have some questions from the chat. Brian is asking, why is contract theory being particularly used for designing incentive in this case? Since we see a lot of game theory and economic theory being used before, why did you choose contract theory in this instance?
Okay, this is also very interesting problem. So when we choose the contract theory to design incentives for federated learning, the motivation is that we want to optimize the economics of the system. For the incentive of a blockchain system, they use not blockchain. They use the optimization of the individual rationality and the incentive compatibility to improve the efficiency of the incentives. And for federated learning, the incentives is offered by the FIL clients, or it's offered by the FIL server or all the task requester. So this is also financially critical for the task to be generally used in realistic scenarios. So we think that the contract theory can contribute to somehow the financial efficiency of the FIL incentives.
Okay. Another question is on the privacy aspect of the incentive scheme proposed here. Jinwen is asking about how to ensure the confidentiality of private data under such a scheme.
This is also for in this study, we focus on designing efficient incentives for the FIL clients to contribute their data and contribute their compute power. If you especially consider the privacy, to protect the privacy of our clients, I think that we should design some more mechanisms to do some more in-depth research to solve this question or this issue. This is also very critical for the success of FIL in application.
Okay, maybe one final question. Is there a possibility of extending the two-dimensional contract into 3 or more dimensions?
Yeah. If actually in this work we consider two dimensions of the client's type, but finally we will find a function between these two types with the registration fee. So we will convert two types of the two types in indicator dimension. So if we consider 3 or more types, we will also need to find an indicator to merge these parameters or to reflecting these parameters. So this is also a very interesting research direction that is valuable to be investigated in our future work. Thank you.
Hey, thank you very much, Professor Liu.
Yeah.
Although there are still questions, but I think in the interest of time, we shall move on now. Thank you for a very interesting talk.
Yes. Also, for if you are interested with our work, you can subscribe to our group. This is our WeChat group. Okay.
Okay.
Thank you.
Okay, thank you. Okay, that concludes our oral presentation session number 1. We shall move on to our invited talks again. So the next we have a talk from Dr. Chong Wang from ByteDance. He's the head of the Applied Machine Learning Research Group at ByteDance. The AML research team works on fundamental machine learning and research and its applications for many of their products, such as TikTok and Douyin, among others. So before joining ByteDance, Dr. Wang worked as a research scientist at Google and Microsoft Research. He received his Bachelor of Science from Tsinghua University and a PhD from Princeton University. His research has won several Best Paper awards in top machine learning conferences, and some of them went into widely used products that serve the users from around the world. Okay, Dr. Wang, are you here?
Yes, I'm here.
Yes.
Yeah.
Are you able to share your screen?
Okay, I can do that now. Okay.
Yeah, thank you.
Let's see.
Okay, perfect. We can see your screen.
Work? Okay.
Okay. Thank you. Thank you. Yeah, please proceed.
Okay. So that's weird. So my screen a little bit strange.
So we can see the slides.
Okay. Okay. Sounds good. Okay. Thank you for the introduction. Very happy to present our work in this workshop. So the title of my talk is Label Leakage and Protection in Two-Party Split Learning. Okay. So my name is Chong Wang, and thanks a lot for introduction. So this is a joint work with my many of my colleagues and former interns. Okay. Oops. That's weird. Okay. Okay. So this is how we talk about label leakage in split learning. So split learning is really a part of sort of vertical federated learning, and also is part of federated learning. And since this workshop is really about federated learning, I don't think I need to go to too much details or backgrounds about federated learning. So we'll directly talk about split learning. And specifically, I'll talk about the label leakage problem in split learning. And next, I'll talk about the several protection methodology were proposed, and so how we designed the protocol to mitigate the problem of label leakage. Finally, we'll talk about some results. Okay, so yeah, so label leakage in split learning. Okay, so here is a pretty typical example of split learning case. So we consider a two-party case here, although it can be extended to multi-parties. In this specific case, that we have two parties. So one party is called the passive party, and the other is called a active party. So the passive party, we can think of, like, for example, some media platforms, let's say Facebook or TikTok. And the advertiser could be some third party, like merchandise, like for example, Amazon, or other type of like companies selling products. So a particular case of like split learning is that we want to address is that can we actually train a model without communicating like raw data between the passive party and active party? So in typical case, we sort of generate data like this. So say a user log into a media platform, and then the app shows some ads to the user, and the user may click the ads or may not click the ads. Let's say the user clicks the ads, and then usually this will take the user to the like say company who sell the ads, who actually own the product, sorry. So for this will be the product page, and the user may actually purchase the product or not purchase the product. So I think that's a typo there. So let's say, you know, this usually happens on not on actually on the media platforms. This sort of purchase or not purchase, this action usually does not happen in the media platform. So in order to train a model, say, you know, predict the conversion rate, usually in a sort of pre-federated learning or speed learning era, we usually need, you know, sort of transfer the raw data, for example, the purchase or not purchase, to the media platform, and they sort of train a model and serve the users. So this can be tricky because this purchase or not purchase information can be pretty sensitive to the either to the users or to the company actually sells the product, or regulations, for example. So speed learning is really trying to see if there's a way to use the concept of federated learning to jointly train a model without actually communicating the raw data. Okay, so so there are two types of raw data, of course. So the raw data is, for example, the label data from the active party, which is the company who sells the product, or the user data, the raw data from the media platforms, from, for example, the user history or things like that. So in this talk, we really focus on how to protect label information. We do have another workshop paper in this year's ICML workshop, federated learning workshop, to demonstrate how we can actually protect like the information from the media platform, how we can also protect that part from probable leakage. Okay, so here we really consider a pretty simple case. Consider training a binary classification. This is really very popular in the online advertising. This is sort of the conversion model or CVR model. So mathematically, so the passive party. So let me see. So I'm trying to get a time. Okay, so in particular, like we have a passive party which actually owns the raw feature data X and certain function F. So F is really from the raw data to like say a d-dimensional vector. And so the active party, which is the company sells the product, and they have this sort of label Y. Y means purchase or not purchase. So, and a certain function H is from, like, it's a function defined from RD to R. So the joint model is defined as sort of composition of these two functions, H and F. So in order to build a simple binary classification, we use a logistic regression. So the logic is defined, let's say that L, small l, is the logic. So here is the logic. And then we can actually define the likelihood of the model as a simple logistic function. And then we can just define the entropy law, cross entropy loss for this. So yeah, this is pretty standard. So we can actually calculate the gradient with respect to the actual logic from the loss. So this is actually quite simple. It's really the p minus y, which is the difference between the instance being positive, the instance of probability of being positive minus the actual label. So that's how it basically really defines the sort of how the model thinks is positive and the difference between actual label. So okay. Sorry, didn't work. Okay. Yeah. So the top two lines is just a copy from the previous slide. So the typical speed learning training can be described in this simple figure here. So we have in forward pass, we have x, and then it goes through this function fx, and then communicate the sort of activation information of activations to the same fx to the function h, which is actually in this active party, and then we see the active label y, then we actually started the backward process. this is what we saw here in this right here, the gradient with respect to the logic, and then you just keep going backward. And this stage is like really just here separating the passive party and active party, and then the gradient it goes back to the passive party, and then they aggregate to computer parameters. So there are two observations that this simple splitting training process might be problematic. So first, that we see that the backpropagation is really linear function with respect to the gradient with respect to the actual logic. So okay, oops, sorry, why is this? Okay. So basically this here, I'm trying to use my mouse here. So really this is like the really key part of the why this might be problematic in practice. So really, if you see that the loss with respect to anything, the gradient from the loss with respect to anything, dz, is really a linear function of this gradient with respect to the logic. So another case is like the class imbalance is pretty common in many real applications, for example, ads conversion or even healthcare. So the sensitive information is usually the minority of the data. Like usually the conversion can be pretty rare. So like maybe 10%, 5% is a really small part of the labeled data. So okay. I don't know why this room already. Okay. Okay. So here we will see that. So what could be a possible leakage from the label information? Let's look at the leftmost figure A. So we actually plot the norm of if you remember, P minus Y is really the gradient of L with respect to the loss with respect to the logic. So you can see that it's really so from the label Y is 1 basically positive, label Y equals 0 is negative. You can see that sort of the norm are pretty separated for both for these two classes, positive class and negative class. And you can see that HZ, which is the sort of the gradient of the logic with respect to the certain parameter is really non-separable. But if you consider them together, which is this figure C, which is the actual gradient, so you can see that they are actually pretty separable for different two classes. So usually the positive class has a higher norm. So this is a pretty, it's actually quite intuitive. Why? Because for example, in the say online advertising case, the conversion rate is usually pretty low. That means that if you train a model, it's typically really hard to fit a good model to the positive class. That means that if you look at the P minus Y, which is the difference between being positive and also the difference between the being positive to the actually positive, they are usually higher than the other way. So that's really the reason why you can see the sort of clearly separated norm distributions. Okay. So another possible attack is if you look at the direction of the gradient. So if you remember that sort of P minus Y is so if you look at this, I'm going to go back and look really quick. So if you look at this, P minus Y, if Y equals 1, this is usually less than 0. If Y is 0, this is larger than 0 because P is always positive. So another possible attack, this is definitely more, is definitely like harder. It's sort of a more difficult attack than the previous one, because this one we assume that the attacker may know some positive label. In this case, they can just look at the directions of the gradient to see, okay, which gradient is actually the same or similar to my gradient. So you can see that. So this is, if you look at the figure E here, this is quite separable if we just use a cosine this similarity compute, the sort of similarity between the tech gradient and the gradient, the gradient we want to recover to see if it's positive or negative. So basically you can see that, so this part, I'm not sure you can see my mouse. So the blue part of the figure really here is the similarity of the sort of given a positive label, we compute its gradient, and also given some other possible instance and compute its gradient and see the cosine similarity. So this is almost 0 and this is almost negative. Sorry, so this is 1. This is almost -1. So quite separable. Okay, so let's talk about the problem, and then we'll talk about the protection technology. Oh, sorry, methodology. So there are so one simple thing we could do, we just add noise. And this is basically all we do, I think. And there are different ways of adding noise. We'll explain 2 heuristic ways and perhaps more principled ways of adding the gradient. Adding the noise. So the first one is really just adding some isotropic Gaussian noise. And adding this noise is quite important because, and this type of noise is quite important because this is really zero mean noise. So that means that if you calculate its expectation of the gradient, it's still going to be the same as without adding any noise. That actually ensures the convergence of the algorithm, although if you add more noise, that may slow down the convergence. So the first one is really just adding some isotropic noise. The second one is adding a more sort of a bit more intelligent noise that we call the maximum norm alignment. So basically we want to make sure that if we want to say, find the gradient with the largest norm and then make all other gradients about the same range in it as the sort of largest or I think it's longest gradient. That we just add a sort of scalar multiply a random scalar to the noise, to the gradient, and make sure that is the normal gradient is about the same as the maximum norm, the normal gradient with maximum norm. Basically, that's the basic idea is like we want to use the gradient with larger norm as sort of like cover all sort of the possible gradients. This is still unbiased gradient, because if you take the expectation, it's going to be the same as the gradient without any noise. So this is the 2 heuristic approaches. Okay, and we also propose a sort of optimized perturbation-based method, and this is I would say this is a more principled because is trying to optimize certain metric, and could be useful for more broad type of attacks. So although we don't really know other type of attacks yet. For example, like we mentioned 2 attacks in the beginning, like say a normal-based attack and also the direction-based attack. We haven't figured out like other type of attack yet, but this method might be possible to more effective against other type of attacks. So here's the basic idea. So we're still adding noise, but we sort of so one thing I forgot to mention is that the noise adding part really happens on the active party. So the passive party does not know anything about how the active party adding the noise. So in this case, we separate the positive examples and negative examples and adding different type of noise to the positive and negative examples. So we basically, let's say we perturb the positive gradient as this, and we defined, so after that, we actually obtain a distribution of the perturbed positive gradient. And the same thing applies for the negative gradient. We apply, we add some other type of noise, and we obtain the distribution over the negative gradients. So for arbitrary labeling function, basically a very attack, we can actually define the detection error under the perturbed gradient distribution of P1 and P0 like this. Basically, this is like sort of the error that if we design any attack, and so this is the error we will get from using these two distributions. Okay, so the case is like we want to actually so we want to actually so in the attacker, what we really want to minimize the error because they want to detect as accurate as possible. So what we do is like we really want to make the worst case sort of acceptable, and this is really this max min problem. And apparently the mean problem can be written as sort of total variation distance, which I don't really have much time to explain about it, but it's really according to the definition of total variation distance. So however, this total variation distance is not intractable, so we use this upper bound, which is really a symmetric KL type of upper bound. So instead of we really just optimize this the KL divergence, which is also sort of intuitive. We want to really mess up the sort of the distributions, two distributions, which is first one is the positive gradient, and the second one is the negative gradient. So yeah, so that is the object function. So here's the thing. So if we just want to minimize this KL divergence, it's problematic because because we can add infinite amount of noise, and then this KL divergence will be almost zero. So that's but there is going to be not very useful because you won't be able to train a model. So instead, we need to add some kind of like a utility constraint. So we define the utility constraints like this. So basically, we want to constrain the covariance of the noise and to be less than some upper bound. So and we also tweak a little bit about the proportion. We want the proportion of the noise to be the same as the number of the proportion of the positive instance in the training data. So this is what is it? We have a P here. P is really the fraction of positive examples. So they really a sort of a proportion to the positive examples and negative examples. We want to the sum of their covariance. This really like sort of the power constraint. To be smaller than upper bound. So P is really we can actually tune to balance the noise we add, and this really balance the sort of the protection and also the utility. Utility means the performance. Okay, so. And there were some more details, and I don't think I have too much time to explain it. But you can actually optimize it using. We designed an algorithm to optimize this objective. But there was some a little bit more constraint to compute. We can actually optimize it in an efficient way. We have sort of this diagonal variance constraint for the original gradient, but we can relax it to the noise. But we sort of have this commuting covariance matrix. Okay, so we talk about the results. So we tried out this algorithm in 3 data sets. The first two are two online advertising data sets, and the last one is a sort of healthcare data set. So the common pattern here is they all have pretty biased data, like 25% 70%, 10% of positive examples. Okay, so we first really did a sort of a study. So I omit a lot of results here because we don't have much space. So this is really on the healthcare data. So if you look at it, it might be hard to see, but if we don't add any noise to the training process, we basically can say that we can guess the label information almost 100% by looking. So this is really 100% really looking at the sort of AUC. Like we define a metric called leak AUC. So it's basically how good we can guess about the positive label. It's by comparing the score to the negative label. This is a typical definition of AUC. So, and we can look at it if we can add some noise, then actually that will reduce the leakage information. And this is really against about norm attack and cosine attack, norm attack, cosine attack. We did a bunch of studies about the information that could be, maybe we have a procedure that can protect the sort of the cut layer, which I didn't really talk about much about this term, which is sort of sort of the layer that connects the passive party and the active. Approach is quite robust on different layers. So, and we also did a sort of more large scale study on sort of performance and protection trade-off. So yeah, it might be hard to see here, but so this first row is the test loss against the leak AUC, and the two bottom rows are the test AUC against the leak AUC. So yeah, so loss is really the opposite of AUC. So this top row, if you look at it, is the better way is to look at it is the AUC. So this bottom left are the sort of more useful techniques. So if you look at, if you see dots like in the bottom left, this is a better approach, or more is better than the ones on the like top right. So, and the second and third row is really this way. So if you sorry, let me see. Let's see, test AUC. Yes. So this is like if you we look at the really look at the bottom right is the better protection methodology. So so yeah, so this is the second row and third row the same. So we look at the say for example here and here are the so better trade-off between the performance . So the second approach that we propose is maximum without any optimization. It also performed quite good if you look at this. So for example, so the max norm is really the star here. It's also quite often on the bottom right part of the figure. So it's likely because the two tags we have is very the two tags we proposed here are in this paper are really surrounded, really sort of norm based. So it's likely that this max norm heuristic is quite well, but maybe in some other additional attacks, the optimization based could be better, but we don't know yet. So here's the summary: is that split learning without communication, communicating the raw data could still leak information. Even for example, we don't really to address this issue, to protect the raw data. So of course, this is still an open problem. Like in many scenarios, in many speed learning scenarios, it might be more complex than the setting we consider here in this paper. For example, so this is, we really talk about training. What about serving? So in some case, the active party might not be able to retain the model. So so that in that case, we may need to think about more. So even we don't really, we use this text, for example, we use this sort of approach to protect the label. But when we actually serve the model, if the active party cannot retain the model and really depends on the passive party to do the serving, it might be actually leaking more information. I think that's all. So yeah, we are hiring. So that's really an plug in here. So so yeah, I think, thank you.
Okay, thank you very much, Dr. Wang.
Hopefully I don't really run over time.
Okay. Oh, no, it's okay, yeah. We have some questions from the audience. Shixiang is asking for the part where you do the trade-off between privacy and performance. How is that different from differential privacy? Seems that the privacy metrics are a little bit different.
So yeah, so that's good question. So it's a bit hard to define it from the noise adding perspective. It's definitely related to differential privacy, but it's really hard to define. Yeah, I think that's also the open problem. It's really hard to define sort of differential privacy, metric in this case. We tried pretty hard, but we haven't really come up with a good way. Do you have any good idea how to define sort of differential privacy like formulation? Yeah, I would like to know, but unfortunately, I don't have a sort of direct like formulation that how it is related to differential privacy. Although is the way we add noise is definitely very similar to the differential privacy. Although we don't really know how we can come up with a more rigorous like treatment in this case.
Okay, another of the audience is asking whether the data set and the code in your presentation, are they open source? Can they have access to that?
I think so. I think it's open source. Yeah.
Okay.
Let me double check. I think it is. I forgot to add to the slides.
Okay, thank you very much, Dr. Wang.
Okay, sure.
Thank you for the interesting talk.
Thank you.
Have a great weekend.
Yeah, thank you.
Okay, we shall move on to our next invited speaker, Dr. Zheng Xu. So Zheng Xu is a research scientist working on federated learning at Google. He got his PhD in optimization and machine learning from the University of Maryland in College Park. So before that, he got his master's and bachelor's degrees from the University of Science and Technology of China. During his studies, Zheng has interned and collaborated with researchers from Apple, Adobe, Honda, Amazon, IBM, Microsoft Research Asia, and Nanyang Technological University. So his papers have received Best Paper Awards and Best Student Paper Awards from several workshops and conferences. Dr. Zheng, are you here?
Yeah, I'm here. Thanks.
Okay, yeah. So you can share your screen.
Yeah, thanks for the introduction. Let me bring up the slides.
Okay, we can see it.
Okay,
please.
That's great. Okay, thanks for the introduction again. So I'm Zheng from Google Research. Today I'm very happy to present at this workshop to share our recent understanding of federated optimization. This is joint work with many of my colleagues. As we know, federated learning is a distributed setting where clients collaboratively train a machine learning model without directly transferring or exchanging their private data. Originating from distributed training on mobile devices, federated learning has now been adopted to various different applications. At Google, federated learning has been used to improve the utility and the privacy of many keyboard tasks. If you look at all these papers and applications, it not only provide privacy protection, but also improve the accuracy for a lot of tasks. Similarly, federated analytics uses federated technologies to answer more basic questions about decentralized data. Like federated learning, it applies the data minimization principle, running local computations and only aggregate the results. Federated learning is usually formulated and solved as an optimization problem. Federated analytics can also be considered as an optimization of a small model. They share some common considerations. There are many challenges in federated learning that are different from the main consideration in centralized training or conventional distributed training. For example, this data heterogeneity, the privacy and security consideration. The federated learning system is usually complex because of the server, clients, and all this spread over different places. And we have computation constraints on those client devices, and we prefer communication efficient method in federated learning. In addition, cross-device federated learning can impose extra challenges. For example, the number of clients is usually large, and we cannot control the client availability, and so it's hard to maintain local states. And there can be some more restrictions on computation and communication for cross-device federated learning. Recently, a preprint from 53 collaborators is released, a field guide to federated optimization, which we focus on formulating, designing, evaluating, and analyzing federated learning, particularly federated optimization algorithms in practice. Let's take cross-device federated learning as an example and showcase some of the challenges we have in real-world scenario. This image, this protocol show a simplified view of what happened on the server in a real cross-device system. Let's say a training run usually starts from a process of device checking in. And in cross-device federated learning, the population size, the total number of devices can be quite large. It can easily go up to millions or tens, hundreds of millions of devices. Moreover, the availability of clients is usually determined by some local criterion, like devices can only check in when they are in charge, when they are charging, and are not being used for other applications. And the available clients has a large variance during the time dimension. We also don't save the client IDs. Clients are all anonymous for privacy considerations. Those impose several challenges on how we can design a federated learning algorithm. Let's look back on what a federated optimization objective looks like. This is a general form of an objective in federated learning. Here we define the local objective for each client I, and we then take the expectation of the population distribution. In a real-world federated learning system, this population distribution is unknown. It's not something we will know in advance. And we all know that client data are heterogeneous. And in practice, we often write this as a ERM form, where you take the summation of all the data on one client and you take the summation over the class you know. If we consider the real practice, when we don't know the population distribution, this number of clients can be very large, and it's somewhat unknown in practice, because some clients, even if they exist in the real world system, they may never check in, and their local criteria may never satisfy the training process. And of course, we have, during the training process, we have to sample clients every round. We cannot access all clients in a training step. And all this affects how we design a federated learning algorithm. Let's take an example of this federated algorithm. We consider a generalized form of federated averaging, where we consider use adaptive methods. Let me first explain a little bit what I mean a generalized federated averaging algorithm. In this, let's see in a federated learning process, in a federated optimization algorithm, in each round, we start from the server sent a global model to clients, and the clients will send back its local updates back to, its local updates back to the server, and the server will aggregate these updates and update the global model. Let's consider this. We have two optimizers in this process. One optimizer is on server, and one optimizer is on clients. In the original fed averaging, those are SGDs. Or we can extend those optimizers to like momentum SGD or adaptive methods. Let's see, now we want to use adaptive optimizers on clients. All these adaptive methods, they maintain a certain buffer, or also called preconditioner. A natural question is, how can we estimate the preconditioner on clients? When we have all these constraints, the population size and those sampling process real world constraints, of course, there are various options we can have to estimate a client preconditioner. Considering all these practical constraints, we prefer a restarting strategy instead of initializing from local state from previous rounds. Let's say, because of the large population size, a client may only participate once during the process. And even if it participates multiple times, let's see, and we can make these local states available by some complicated system design and violate some privacy considerations. These local states will quickly become stale during this training process. Okay, let's see. How can we do research when we have all these real world constraints? Even in industry, always running a real system can be difficult for research. In addition to considering all these real world constraints when designing the algorithm, like the example before, we have to rely on carefully designed simulation experiments to verify the performance. When we design simulations, the first question is like, what's the application setting we are considering? One thing that's particularly important for federated learning is that do we support state on clients? A lot of algorithms that have show faster convergence in practice, fast convergence in theory. For example, some method even can match the lower bound of stochastic method, but rely on some control variance that has to be maintained on the clients. Those are relatively complicated to use in a real world cross-device system. And we often prefer real-world large-scale non-IID data compared to designing a toy example. You can always design a toy example that is the worst case. and some of the artificial partitioning of heterogeneous data can be pathological. We want when we talk about our simulation results and our methods, it's better to be precise about where computation happens and what is communicated. This can be important for evaluating the efficiency and the privacy. There are other considerations, like what are the metrics we want to use. There's no general consensus for federated optimization algorithms, but our suggestion is, in general, we should choose one that makes most sense for your applications. And for hyperparameter tuning, since in federated learning system and algorithms, there are considerably more hyperparameters than in centralized training setting. In all this practice, a self-tuned method or automated method is always preferred. And you probably want to control multiple factors like the number of clients and how you sample clients and the random set you use. And all this randomness in your simulation experiments to make sure that your results are reproducible and reliable. Let's look at an interesting question for the metrics. We usually see that we want a communication efficient method in federated learning. How efficient is a communication efficient method? Usually it's hard for us to trust the simulation work log time, because the simulation environment, when you run your experiments in a data center, it can be quite different from the practice. It would be good if we can get some analytical results. For example, if we know two algorithms have the same communication cost per run, then number of runs, like a lot of previous papers, is a pretty good metric for communication efficiency. What if it's not so easy to get all these analytic results? What we hope is that we can have one method to estimate the real world performance based on our simulation results. We provide a very simple model. This model is very simple, and note that it did not consider a lot of practical considerations like stragglers and some check-in time and all these constraints. In this simple model, we decompose the runtime for cross-device training into communication and computation time, and all the algorithm A is your algorithm, and all the other parameters in the equation are expected to be estimated from your simulation results. And this model is parameterized by the bandwidth to estimate communication and the ratio between on-device training time and like a desktop training time to estimate the on-device time, and then some setup time for on-device training. And we estimate those parameters from a real cross-device system. So because this model is so simplified, looking at the scales of these numbers is probably makes more sense than looking at the absolute value. So with this simple model, we can actually estimate the training in real world cross-device system by running some simulation experiments. On the left-hand side, we show simulation experiments, the test accuracy versus the communication runs. And on the right-hand side, we change the x-axis to be the estimated training time based on the simple model. An interesting observation is that if you have a very large local training epochs, the number in the legend are the local training epochs. It may improve your convergence speed at the very beginning if you are evaluated by the number of rounds. But if you look at the time will be spent, because these models are relatively large and slow on mobile devices, it may not bring you many benefits. Okay, let's talk a little bit about another perspective of federated learning. So federated learning itself provides certain privacy protection by applying all these data minimization principles. If we want stronger privacy protection, we often combine federated learning with other techniques. For example, if we want to protect like information leakage from these models during the intermediate models during the training and the final model we're going to release, we want some differential privacy mechanism. And we use central DP to protect models. In this differential privacy, when we use differential privacy in federated learning, all these differential privacy methods, if we want a good accuracy utility trade-off, we often rely on one technique called amplification by sampling. In this method, we assume that for each batch we used, for each round, the clients we used are uniform sampled from the population. If we look at the figure on the right, we have two curves, and the x-axis of this figure is the user level differential privacy epsilon. The smaller means that the stronger privacy protection. The y-axis is the test accuracy. One curve is for amplified results. If we can do this uniform sampling, then at the same privacy epsilon, we can get much better test accuracy, especially when the epsilon is relatively small. But remember that we have a large client population size, and we have minimum control of how clients can connect and how clients can be available. We have talked about a lot of challenges and how you have to design your algorithm and work with this and consider all these constraints in when you want your algorithm to be deployed in practice. Now let's look at a relatively positive example where these challenges can inspire new research. For this to deal with the difficulty of sampling in federated learning, we designed this new algorithm called DPFTRL. What we do is like we rely on a smart way of adding correlated noise instead of independent noise based on this tree structure. Then by doing this, we can provide similar privacy utility trade-offs without sampling. Yeah, if you are interested, I will encourage you to look at our recent paper. Okay, we talk about challenges and constraints in federated learning. We use this number of examples, total number of clients and the client availability as an example to showcase how these real world constraints may affect your decision on designing your federated learning algorithms. More discussions on the problem formulations, how you can use different knobs to improving efficiency and effectiveness, and what's the relationship between optimization, privacy, security, and the other perspective of federated learning, like personalization, robustness, fairness, are discussed in a field guide to federated optimization. We read this in a way that we use a few concrete hands-on examples to showcase how the constraints can affect your algorithm design. The the code is open sourced and it's based on the TensorFlow federated learning framework. There are a lot of tutorials and example projects based on TensorFlow federated learning. We encourage you to take a look. I think that's all from me. Thanks a lot.
Okay, thank you very much, Dr. Xu. Any questions from the audience? You can feel free to type it into the chat box. Okay. Dr. Xu, I think you have mentioned a lot of interesting work in how to select from a large pool of clients to participate in federated learning. I'm wondering, do you know of any work in this area which tries to take into account how to incorporate the concept of fairness into this process when selecting clients?
Yeah, this is a very good question. We know a few works in fairness. They are more considered that if I'm a minority client, can I like will the trained model perform good on my accuracy? I guess fairness is relatively a very open research area. There's no clear consensus on what's the definition of fairness. People see fairness under different considerations. Yeah, that's a very good question. For us, it's a particularly interesting question is like, as I mentioned, these clients, they check in at different frequency. They basically, we have no control on how to sample in clients. Their check-in, their availability is mostly determined by their local criterions. So itself, the process itself may introduce some bias here, and it's a very open question we don't know how to address. If people are interested in this research, we are definitely interested in talk and collaborating on that. Yeah.
Okay, thank you very much, Dr. Zheng, and for a very interesting talk. And have a good night over there in the US. Okay, thank you. Okay, so now we'll come to our last invited talk before the lunch break from Dr. Li Fengbo from JD. So Dr. Bo is the head of Silicon Valley R&D Center at JD Technology, leading a team to develop advanced AI technologies. He was a principal scientist at Amazon for building a grab-and-go shopping experience using computer vision, deep learning, and sensor fusion technologies. He received his PhD from CDN University in 2007 and was a postdoctoral researcher at TTIC and the University of Washington, respectively. His research interests are in machine learning, deep learning, computer vision, robotics, and natural language processing. He won the National Excellent Doctoral Dissertation Award of China in 2010 and the Best Vision Paper Award in Ijcai in 2011. Dr. Bo, I think we are already able to see your screen share. So Dr. Bo, please.
That's nice. That's nice. Thanks, Professor Han Yu, for introduction. Really glad to be here. Today, I'm going to share our work on large-scale vertical federated learning. This is joint work with my colleagues in JD Technology in Silicon Valley. Okay, let me so my talk is organized into 4 sessions. The first session introduces vertical federated learning and its challenges. The second session talks about distributed federated random forests. The third session proposes federated kernel learning. The fourth session introduces our open source framework, FedLearn. I will quickly go to this horizontal federated learning setting. In horizontal federated learning, data are split in terms of samples. Each party owns a subset of samples, and each party has full access to the complete feature set. Usually, there could be quite a lot to say applications. I think also it's it's possible to apply this to 2B applications. In vertical federated learning, data are split in terms of features, or we can call this as attributes. Each party owns different features or attributes, and each party shares a set of same sample IDs. Vertical federated learning is often used in 2B applications, where each party represents a company. For example, if two companies want to build a model jointly, they could actually provide a different set of subset of feature set. So here I'm going to talk about challenges for vertical federated learning for industry applications. So the main challenge here is it is hard to scale up vertical federated learning due to a number of reasons. One is inference and training requires connection and file system to load other parties' data. Secondly, data must be encrypted, for example, using homomorphic encryption, which is computationally expensive. Third, encrypted data causes too much time and space to transfer. In this talk, we are going to talk about two algorithms towards making large-scale vertical federated learning practical. One is distributed federated random forest, and the other one is federated kernel learning. So let's talk about distributed federated random forest first. So we consider random forest because the trees in the random forest are built in parallel, so it's pretty easy to be distributed. So we did a number of optimizations to speed up a single tree on a single machine. So here, we show a few tricks. Firstly, we transfer only HE encrypted labels to protect privacy, which reduce the size of transfer data to 10%. We also use multi-sensor processing to handle bin sum calculation and achieve an average of 5 times speed up on a 8-core machine. Thirdly, we optimize homomorphic encryption and achieve an average 70 times speed up on basic operators. With these optimizations on a single machine, we can maximize the potential to use this federated random forest on a single machine on a larger data set. So here we show our approach actually to distributed federated random forest. It's quite intuitive. So basically, for each tree we have a single machine. In this case, in this setting, the number of machine is equal to the number of tree. So we achieve an average 5 times speed up on a 5-tree random forest models. So in our setting, in this case, it is linear scale to scaling to this the number of machines. So for the inference, in our distributed framework, we also build each tree. So we also did a number of optimization for this inference process. We optimize inference, we optimize the transmission and encrypted value operations. the trick is that inference instance visit each client only once, and this leads to 5-time inefficiency with a regular 10-depth random forest model. We also compile the data transfer so that transfer data shrink to 20% in size. In our cases, this actually speed up our inference quite a lot. Here we compare distributed federated random forest with secure boost, which is another tree based on vertical federated learning algorithm. We can see that distributed federated random forest has similar accuracy with secure boost for small data size. When trained with more data, distributed federated random forest achieve higher accuracy. On the left, we show the results on real industry applications. One task is risk evaluation, which is quite critical in finance industry. The other one is digital marketing. In this slide, the number of training sample is up to like 5 million. So in our in our experiments, we also tried much more training data, up to like 50,000. So basically, this federated, distributed federated random forest also works quite well. So second algorithm to handle this large data size is federated kernel learning. It has two, so basically it has two main loops. One is to calculate the inner product in the kernel space, so for each client or each worker. The other one is to calculate the coefficient of kernel features using doubly stochastic gradient descent. Because of limited time, I'm not going to go to too much details for this algorithm. For more information, please check our paper. Here we show the result for our federated kernel learning algorithms. We compare our algorithm with some sort of algorithms. So we can see our federated kernel learning converge quickly compared to other kernel based on privacy preserving algorithms. And it often achieves similar or higher accuracy on benchmark data set. So in these slides, we show our simplifications for this algorithm. As we mentioned earlier, we have two loops, which actually make algorithm quite complex. So here our idea actually to use additive kernel to simplify this algorithm. Each party has, in our setting, each party has its own kernel, which is independent with other parties. We can prove, in this case, we end up with an additive kernel. So basically, the number of kernel we sum up is equal to the number of parties in this setting. In this slide, we compared the results. So as we can see, algorithm converge quickly in practice. Also, we compared federated kernel learning with secure boost and distributed federated random forest. After tuning kernel parameter on training data, it achieved higher accuracy than tree based on federated learning. It also takes less time to train and to do inference. In this specific task, actually, we compared those two algorithms on more data sets. our finding is distributed federated random phrase is more robust to the different types of problem. But for some problem, with carefully tuned parameters, federated kernel learning can be better. So in practice, we can use either algorithm depending the task we are handling. So to contribute the federated learning community, in particular for industry applications, we have released our open source framework. It has few appealing features. The first one is faster deployment with light Java framework. Secondly, we provide docs so that the beginner can learn the software quickly. It is easy set up due to a small number of dependencies. Also, we monitor training process and track the intermediate results to make the debug process easier, which is quite important for in practice for the modular. Yeah. Here we show the algorithm our open source software supports. For federated learning, it includes secure both distributed federated random forest, federated kernel learning, and federated average. We are adding more algorithm in our framework. For secure multi-party computation, it has gobbled circuit, secret sharing, a secure inference private set intersection. So we have easy to use fundamental module which can be shared for developing the different algorithms. So that our framework supports faster development and efficient function calls. Here we show the module in our framework. It includes like message transfer, homomorphic encryption, network topology tools, multi-machine communication, and so on. So not only federated random forest and federated kernel learning we mentioned, more algorithm and framework and dams and construction. Particularly, we are putting quite a lot of efforts on developing a neural network, which actually has quite a lot requirements for applications. So in these slides, we show our software. Our software can be downloaded in the address show here. Welcome me to try. Thanks. That's my talk. Yeah.
Thank you very much, Dr. Bo. Maybe later on you can also share these links in the chat in this Zoom session so that our participants can have access to.
Yeah, I will do that.
I'm just wondering if we were to use this platform, do we need to set it up on our own machines, or is it provided like a cloud service from JD?
So currently we haven't released a cloud based on software. So basically, when we download this machine, we actually have simulate environment for a single machine. That you can simulate different parties. In the future, we also plan to release a software that can be directly used in the popular clouds. Yeah.
Right. Yeah. Okay. Any other questions from the audience? Well, if not, Thank you again, Dr. Bo, for a very interesting invited talk. And have a great weekend. So Dr. Bo's talk actually concludes our morning session or others for other time zones. Maybe other we call it different ways in other time zones. So our first session for this workshop is now ending. So we'll have a longer break in between. We'll be back after around 30 minutes. And we'll kickstart the afternoon session in Asia time. Okay. Thank you very much and enjoy your lunch, albeit a short one. Hello, everyone. Welcome back. Our afternoon session, or the second session, will be chaired by Dr. Tu Weiwei from 4 Paradigm. Okay. Dr. Tu, please.
Hello, thank you. Hello, good afternoon, everyone. I'm Weiwei Tu from 4 Paradigm. It's my great honor to co-host the first session in this afternoon. Welcome to Federated and Transfer Learning workshop, Ijcai 2021. Okay, so please keep your audio and video off during this talk. As you can see from the website, we will have 8 oral presentation talks. Each talk will have 15 minutes, including QA time. Then we will have 4 wonderful invited talks. Each invited talk will have 20 minutes, including QA. Then we will have an award ceremony and a poster session. You could type your questions in the chat. The speaker will answer your questions after his presentation if he had any time. Okay, let's begin the first oral presentation session. First, we will invite authors from WeBank to present their paper, Fed IPR, Ownership Verification for Federated Deep Neural Network Models. Okay, is there any author here? Please open your camera and mic and share your screen.
Yes.
Okay, then let's welcome Bowen.
Okay.
Oh, it's your time.
Can you see my screen?
Yes.
Yes, okay. Hello, everyone. My name is Bowen Li. The talk title I present today is Fed IPR, Ownership Verification for Federated Deep Neural Network Models. This work is completed by Li Xinfan, Bowen Li, Hanling Gu, Yan Kang, Jie Li, and Yang Qiang from WeBank AI Lab, SJTU, and HKUST. The background of our research is that deep neural network training is a resource-intensive task. High human labor and computing costs make high business value in trained deep neural network. Adversary may illegally copy the deep neural network with non-technical means. So we study how to design technical methods to verify ownership and identify plagiarism of federated DNN. The overall ownership verification paradigm can be divided into 2 stages. In the first stage, the owner embeds signature into the model during the training process. And the second stage, the owner extracts the prescribed signature and claim ownership of the model. There are 2 types of signature verification manner. Black box manner means verify without access to model parameters, while white box verify with model parameters. First, the owner verify with suspicious API with black box verification. If the API output the target label, the owner call the raw false, open the model parameters, and conduct white box verification from the model parameters. Previous work provides ownership verification for deep neural networks. Black box manner watermarking approach was proposed by Eddie. He designed specific image as trigger set and then conduct backdoor training task. When verification, the trigger set is input into the neural network. If the model outputs a design net label, like a cat, horse, frog, the ownership is verified. White box manner signature verification approach was approached by Wachida. In training process, the owner simultaneously embed the secret binary string into the model with a secret matrix. When verification,
the owner extracts the feature-based signature with the prescribed matrix, then compile the signature with the prescribed one. If they match, the ownership is claimed. Previous work focused on deep learning. It remains a challenge how to embed the signatures for each client in federated learning system. Specifically, we consider a semi-honest horizontal federated learning setting. Each client embeds his own private signatures into the federated global model. So each client independently can extract his own signature from the global model and claim ownership. That's the goal of our job. The first stage of verification is embedding signature via training. The client conducts multitask training to embed signature into the local model. They adopt backdoor training to embed the trick set-based watermark and the design regularization term to embed his own private signature string into the model parameters. As a result, each local model parameters are embedded with private distinctive information. However, it remains open problem for signature aggregation in federated learning. Each client embeds his own private signature BI and TI into the local model. But in the end of communication round, those local models are aggregated into a unified global model, like algorithm fed average. Those different signatures from local model may conflict with each other in the unified parameters. It may be a mismatching problem. So how to address this issue? We propose our Fed IPR scheme. In our scheme, each client embeds private signature into targeted parameters in the model. As you can see in the above panel, in a convolutional neural network, the convolution block includes the parameters WK. Then the output goes through a batch norm layer. Then the output was scaled by parameters W-gamma. In our Fed IPR scheme, both WK and W-gamma can be embedded with our private signature BI. When it comes to the implementation of signature embedding, the local model adopts two regularization terms. For private trigger set TI, the client adopts backdoor training loss function LT. And for feature-based signature BI, the signature client design appropriate regularization term LT. The client simultaneously optimizes 3 loss in the overall training time to embed the signature. But while our Fed IPR scheme can guarantee that signature can be aggregated without conflict, we provided theoretical analysis in our paper. We indicated that in an n-client federated learning horizontal system, the total sum of bit length of each signature, if it is less equal to available channel number, the signature in the global model do not conflict with each other. We provide a detailed proposition and proof in the paper, and we conduct numerous empirical studies to validate our theorem. For verification scheme, our Fed IPR scheme provides independent verification capability for each client. Each client can input his own private trick set into the model. If the model output as his targeted label, the owner can call the raw force, open the model parameter, and extract his signature with her secret matrix. We conduct empirical study to validate our Fed IPR scheme. We evaluate our scheme from 3 dimensions. Fidelity measures the main task accuracy and the signature embedding scheme. Figure 1 and Figure 2 respectively illustrate CIFAR 10 with AlexNet and CIFAR 100 with ResNet, where clients embed varying bitlength signature. The result shows that main task accuracy in different settings drop at most 2%, which means our Fed IPR scheme almost doesn't affect the main task. The second dimension is reliability. Reliability measures the signature detection rate of the trained model. Here is the reliability of white box signature. Figure 1 and Figure 2 respectively illustrates AlexNet and the ResNet 18 model signature detection rate. The vertical line notes the theoretical bound. If the sum of the signature bit length is within the theoretical bound, as you can see, the detection rate is nearly 100%. Signature can be reliably embedded into the model. When the bit length is slightly over the theoretical bound, the detection rate drops. But note that over 60% detection rate can also cast high probability of ownership. We also evaluate our black box watermark detection rate in varying settings. In our CIFAR 10 classification experiments with AlexNet, we test our trick set-based stick protection method and the defensive methods like treat-mean, clone, boolean. Our method guarantees 60% detection rate, which claim almost 100 probability of detected plagiarism. Detection rate twice higher than 1/C is enough to prove plagiarism. The third dimension of our evaluation is the robustness of our signature. Firstly, in federated learning, technique can be adopted to improve privacy or efficiency. Figure 1 illustrates the performance of signature and the differential privacy. We adopt Gaussian noise to protect the model privacy. In the concrete way, when the DP noise sigma equal to 0.003, as the green and blue line indicate, our classification accuracy and the detection rate keep a high performance. We should demonstrate the robustness of signature and the trigger set. Figure 2 illustrates the performance of signature and the client sampling. When the friction ratio is larger than 0.2, or the classification accuracy and the detection rate in the green and blue line keep almost unchanged, which means signature can be effectively embedded and verified. Also, after adversaries steals the model, they may try to remove the signature within the model parameters. Pruning attack and the fine-tuning attack are common used methods. Figure 1 shows signature detection rates as increasing proportion of parameters upfront. It was observed that the detection rate of signature is stable when pruning rate is lower than 70%. Figure 2 shows signature detection rate as increasing fine-tuning epoch. It was observed that detection rate of signature remains higher than 90%. It shows that if the model are fine-tuned but keep high utility, its robustness is robust to see high probability of ownership or verification. So our signature embedding scheme is very robust to remove attack. To conclude, model intellectual property right protection is important as data privacy. We design highly reliable signature scheme to provide verification for federated learning models. And we evaluate our scheme on various computer vision tasks and model architecture. We also extend our work in transformer-based models with NLP tasks. Thank you. Do you have any question?
Okay, thanks, Bowen. I'm sorry that we do not have enough time for the QA. So if there's any question about this presentation, please contact the authors privately. I'm sorry. There's a question in the chat, so I think you could have a discussion. Okay. So please turn off your screen sharing, and let's welcome the speakers from Tencent to present their paper, A Federated Multi-View Deep Learning Framework for Privacy Preserving Recommendations. Okay, so please open your camera and mic and share your screen. Is there any authors from Tencent to present your?
Yes, I'm here. Please wait a second.
Okay.
I cannot share my screen. Can you?
You can send your slides to me, and I help your screen sharing.
I already made you a co-host. Can you share now? You try to share now.
Let me try again. Yes, it's okay. Okay, hello everyone. My name is Xinhua Zhu. I'm from Tencent. Today I'm presenting our paper, Federated Multi-View Deep Learning Framework for Privacy Preserving Recommendations. First, we'll briefly go over the background of our paper and review related works of federated recommendation systems. Then we'll lay down the formal definition of the multi-view recommendation problem. The proposed solution for multi-view federated learning will then be elaborated. Finally, we'll present the experimental results and conclude our presentation. Now, recommendation systems are central to the success of many contemporary internet-based applications. For example, in e-shopping applications, video streaming, and the very popular short video communities, recommendation plays a very important part in user experience. But building a precise recommendation system requires a large amount of detailed information about users' behavior towards various items. This often involves highly private information about an individual. Therefore, privacy protection in recommendation systems has received broad attention from the public. In the literature, the recommendation community has applied federated learning to alleviate the privacy concerns. Most conventional federated recommendation systems are collaborative filtering based. For example, the federated collaborative filtering FCF method and the secure matrix factorization method. The problem is CF inherently suffer from cold start problems, and so do their extensions in federated configurations. On the other hand, content-based recommenders do not have the cold start problems. Microsoft has applied the vanilla fed average algorithm on a deep neural news recommender, but still, there lacks a generic federated framework that addresses multi-view content-based recommendation. In our paper, we proposed the FLMV-DSSM framework. The proposed framework avoids cold start problems by utilizing the inherent features of users and items. It also boosts recommendation performance by learning from multiple data sources. With the new federated multi-view application setting, new challenges also emerges in data security protection. The contributions of this paper are threefold. Firstly, we propose a generic content-based federated multi-view framework. Secondly, we extend the vanilla fed average to a multi-view setting, and correspondingly propose a novel approach for learning and aggregating multiple local models. Last but not least, we study the challenges of the proposed federated multi-view setting and present a solution to guarantee its security. Now, before introducing the federated multi-view recommendation algorithm, we lay down the formal definition of the proposed problem. Our goal is to learn a model over data residing on m distributed nodes and n isolated views on each node. Here, a view is the user behavior on a distinct app. The multi-view dataset on the distributed node M is the collection of view-specific user behavior and locally shared item data. We define semantic mapping functions FW that map user and item features to a vector in the semantic space. The parameters of the item mapping function WI is globally shared, while each view has its own parameter set WUI. The objective of training is to maximize the similarities between semantic vectors of positive user item pairs over all possible pairs on each client. In conventional federated learning, we require that the FL clients must not expose their raw data. In the proposed multi-view framework, there's additional requirement that raw data must not be communicated or intercepted between different views. Therefore, the threat models of the multi-view framework also include attacks from malicious views. We assume that each view's dataset UI and the model WUI are protected by TEE and accessible only to the process of the ICE view. But even so, the view-specific datasets are susceptible to malicious view attacks. For example, a malicious view may monitor the network interface to intercept another view's network traffic. It may also make null updates to shared local item submodel in order to infer another view's model updates or even its raw data. In this paper, we propose a federated multi-view semantic recommendation framework based on the classic DSSM. DSSM extracts semantic vectors from users' queries and candidate documents by one user tower and one item tower, respectively. The proposed FLMV DSSM extends DSSM in a multi-view federated learning setting. In the proposed framework, we have one shared item tower, but also n view-specific user towers. The protocol of a training iteration of FLMV DSSM is as follows. Firstly, within each distributed node, the gradients of the user and item submodels are computed separately. The item submodel are then locally and globally aggregated using the secure aggregation primitives. On the other hand, the view-specific user submodel updates are aggregated optionally. The difference of the user submodel aggregation will be explained a little bit later. Finally, the local item and user submodels are updated with the aggregated gradients. In the prediction phase, we retrieve the top K items for recommendation for a user U. The prediction is computed locally in a distributed node. First, the semantic vectors of all items are computed from the mapping function FWI. Then we compute the user semantic vector as well as the posterior probability of each item in all views separately. The posterior probabilities of an item are securely aggregated across all views, which sum up to the score of that item for user U. Finally, the items with the highest scores are returned. In the above training and prediction protocols, we have applied two secure aggregation primitives. Remote secure aggregation is used to aggregate user and item submodel updates globally in training. In our implementation, it follows the secure aggregation protocol proposed by Google. And the second primitive, local secure aggregate, is used to aggregate item submodel updates in training, and also the posterior probabilities in prediction. The local secure aggregation primitive is to protect data security among local clients, where the number of participants are often small. Therefore, multi-party computation techniques is not suitable in this situation. Instead, we apply differential privacy protection to the aggregated counterparts and select the proper noise level according to the required privacy budget. The proposed FLMV DSSM is a general protocol. Therefore, we can have multiple variations from this generic framework. When the number of views n equals to 1, the proposed framework degrades to FLDSSM. And when we configure not to aggregate the user submodels globally, we have the semi-FLMV DSSM. In this variation, only item submodels are globally shared, but each client has its own user submodel. Our experiments are implemented on TensorFlow Federated. The dataset used is movie lens. We simulate the two-view dataset, where the first view contains static user features such as age, gender, and occupation. The second view are embeddings learned by SVD from the interaction matrix. Note that the two views are orthogonal. The item features are title and genre of the movies, coded with 3 grams. We first experimented the proposed framework with cold start problems. Generally, FLMV DSSM achieves good cold start prediction performance for new users. It is worth noting that the performance of co-star items and user items are lower than that of co-star users. The reason might be that in our datasets, the differences between users is less significant than that of items. Now let's compare the performance of different recommendation algorithms and variations of FLMV-DSSM. From this table, we can see that among FLMV-DSSM variations, the multi-view versions achieve better performance than the single-view FLDSSM. Also, among all federated algorithms, semi-FLMV-DSSM achieves the best performance, which aggregates only the item submodel rather than user submodels. It is because the local user models fit better to the individual user data. Therefore, it is more individualized. In conclusion, we propose FLMV-DSSM, which is a generic content-based federated multi-view recommendation framework that could address co-star problems. As experimental results show, the proposed methods improve recommendation performance by leveraging multi-view source data. We also address the threat models and security measures raised by the multi-view framework. The efficacy of the proposed methods is demonstrated by empirical evaluations. That's all of my presentation. Thank you.
Thank you, Xinhua. So we do not have enough time for the questions. So please connect the users if you have any questions about the presentation. So let's welcome the speakers from WeBank to present their paper, Privacy Preserving Federated Adversarial Domain Adaptation over Feature Groups for Interpretability. Okay, so is there anyone here? Okay, yeah, okay.
Let me show my
So
screen.
please open your camera and mic and share your screen.
Okay. Cannot share my screen. How to share my? Okay.
How about now?
No, I see it. Okay. You see my screen?
Yeah, we can see your screen.
See my slide.
Yeah. Your slides, please.
Okay. Firstly, sorry for my voice. I have the cold. I have got a cold, but I will try my best. Okay. My talk today is privacy preserving federated adversarial domain adaptation over feature group. We calling it PRADA for short. And I'm Yan Kang from WeBank AI Group. So in this paper, we investigate a understudied but practical vertical federated learning problem. So let's say we have a party A from the target domain. It is a financial institute, but party A has very limited amount of labeled samples and features. Thus, it is unable to train a useful model. So to extend the sample space, we turn to a party B for help. Party B is another financial institute, and it has a large amount of labeled samples. However, both party A and party B have a limited amount of features. Thus, we extend the feature space with the help of a party C through vertical federated learning. We can consider party C as an internet giant. It has rich features. It provides complementary features for samples of both party A and party B. Since party A and party B are from two different domains, thus the party C locally perform domain adaptation between samples of party A and party B to bridge the domain divergence. Note that we only perform a domain adaptation on party C because we assume that party A or party B has insufficient amount of raw features to conduct effective domain adaptation. And more importantly, these raw features that are maintained by party A or party B are business related, and their contribution to the model should be interpretable. Therefore, we directly put those features into the classifier or local or label predictor, as I will describe it in the next slides. So our approach involves two stages. The first is the pre-train stage. The second stage is fine-tuning. So the pre-train stage is performed collaboratively between party C and the source party B. The goal is to train feature extractors to learn feature representations that are both discriminative to the task and invariant to the divergence of the source and the target domains. So to achieve this, the party C and the source party B train local extractors and the label predictors. The label predictor is on top of those feature extractors. The party C train the feature extractors and the local and the label predictors to let the feature extractor to learn discriminative feature implementations. Then party C also locally perform domain adaptations on feature extractors to let feature extractors to learn domain invariant feature representations. The second stage, fine-tune stage, follow the similar steps, except that the fine-tune stage does not involve feature extractor. So let's first go over the pre-train stage. For each training sample, we first group the raw features of sample into multiple groups, that each group contains highly relevant features. This is done based on domain expertise. We mainly have three purposes for grouping features. One is the dimension reduction, and the second one is transform no predictive and no interpretable features into higher predictive and higher interpretable features. And we want to perform finer grained domain adaptation. So after feature group, we put those feature group of features into feature extractors, and we assign pair of feature extractor and domain discriminator to each feature group to perform a finer grained adversarial domain adaptation. Then we aggregate all the outputs of feature extractors to form a intermediate result. We call it mu here. So this one, mu here. Sorry, this one. Then the intermediate result mu is transferred to party B to perform vertical federated learning to train the label predictor of party B. Party B is a source domain. And also in this process, we also train the feature extractor. So in the fine-tune stage, basically they follow the same steps, except that the fine-tune stage there is no need for party C to perform local domain adaptation because we just want to leverage the pre-trained feature extractors. So as I described in previous two slides, the vertical federated learning is performed when we train the label predictor, either in the pre-train stage or fine-tune stage. The label predictor involves data from both from two parties, from party C or party A, or party C or party B. So therefore, it should be performed in a privacy-preserving manner to prevent data leakage. So now let's take the fine-tune stage as an example. So to this end, we treat the computation of the output or logic of the label predictor as two parts. The red part is computed collaboratively by party C and party A in privacy preserving manner. and the blue part is computed locally at party C in plain text. So we do not need to do any encryption on the blue part. So it was mentioning that all the parameters of the label predictor model are maintained by party A. Party A knows the real value of the WA here, but it does not know the real value of the WC. We will add noise to the WC to prevent party A to infer the data from party C. So, so during training and the testing, this slides show how the privacy preserving vertical federated learning is actually performed. I will not going to go over the detail because it little bit involved and the time is limited. So if you are interested, you can go over the paper to read the details. But the key point here is that the privacy preserving is achieved by leveraging the hybrid of partial homomorphic encryption and random noise. And the party C and the party A cannot infer data and the models of the other party. And the encryption also only happens when we train the local predictor model or other model like the feature extractors, domain discriminators that are located in party C is trained in plain text. So that will save time. So for the experiment, we perform the experiment on two data sets. One is a census income data set, another is PPD law known default. Two data sets are both binary classification problems. The census income data set, its task is to help target party A to predict whether a person's income exceeds $50,000 US or not. And the PPD no default is to help the target party A to build a no predictor to predict whether a no will be default or not. In party C, we transform all raw features into feature groups as I described in the previous slides. While the party A and the party B, they will use just their raw features. And we have 4 settings for our experiment. The first is a local. It means that the party A, the target party, only uses its local data to train models. And VFL is that the party A only use the target domain data of both party A and party C to train models through vertical federated learning. AB VFL is that it assumes that the privacy is not a concern. For example, the party A and the party B are from the same organization. Therefore, the party B can use the data of both source and target domains to train models through vertical federated learning. So the AB VFL setting serves as a strong baseline for our approach to compete. The B2A is excuse me. B2A is our proposed approach. We perform federated adversarial domain adaptation from party B to party A with the help of the party C. So we have 3 obligations of our model. One is Prada. This is just our model. The second is Prada without feature group. So the third is Prada without domain adaptation. So from the 2 tables, we can see that the performance of the models consistently improves from a local setting to a VFL setting and then to a BVFL setting. This demonstrates that leveraging additional features and samples actually improves the model performance. And the Prada outperforms the Prada without domain adaptation. This demonstrates that the effectiveness of our Prada approach on bridging the divergence between source and the target domains. And if we compare the product with the product without the feature group, we can see that the product outperforms the product without feature group approach. This demonstrates that our product approach with feature-based domain adversarial training can improve the transferability of the feature extractors. So we demonstrated the model interoperability by visualizing the impact of features on the target label predictor. We do not for this paper we do not care about the interpretability for the local predictors, local feature extractors and domain discriminators. We only want to say if the target party it has a label predictor. If the target party can interpret the label predictor. So we use SHARP, a tool which is a tool widely used to explain black box models to explain the label predictor model. So the vertical axis represents feature importance, which is ranked in descending order. The color represents the feature values. The red is high, the blue means low, the value is low. The horizontal location shows whether the feature value is associated with a high, with a high prediction value or low prediction value. So from the table, I can see that the employment, gender, stock, dividends, capital gain, and household are the top 5 most influential features. And the first 4 features are positive impact, have positive impact on the label prediction, while the household is negatively correlated with the prediction. Okay, so we also run our model using FATE 1.6 standalone motivation to see how many times it takes to run to train the model and fine tune our product model. So from table we can see that the product without domain adaptation cost for approximately 4 hours, which is twice the training time spent by the secure boost. The product approach takes almost 6 hours to train because it involves the domain adaptation. But once the pre-train is finished, we can say that the product approach only takes half an hour to perform fine-tune stage. So this shows that our product approach is actually practical in solving real-world problems. So that's all for my talks today. Thanks.
Okay, thank you, Ken. I'm sorry we do not have enough time.
Okay,
and yeah. Okay, you can turn off your screen sharing.
Okay.
Yeah. Okay.
How to turn it off?
Just turn off your screen sharing.
Okay.
It is on the top of your screen.
Okay. Thanks.
Hello, everyone. Can you see the screen? Share the screen?
Yeah.
Okay. Let's get started.
Okay.
Okay. Hello, everyone. My name is Chen Guangzhang, and an MPhil student from HKUST. Today, I'm going to introduce our recent work, Ijcai's trusted, automatic, and accurate verification framework for vertical federated learning. Here's the co-author of this work, Junxue Zhang, Chai Di, and Professor Kai Chen. Okay, here's the rundown of today's presentation. First, I will introduce the background and motivation of this work. Then I will go through the design details of Ijcai. After that, an evaluation including security and overhead analysis will be delivered. Finally, I will conclude the work and give a takeaway list for this presentation. First, vertical federated learning. What is vertical federated learning? Which is also known as feature-based federated learning. It offers a feasible solution which enhance models capability with different features from various parties via the designed secure protocols. VFL participants share the same DEMPO ID space, but different feature spaces. For example, data from financial institutions like Party A and hospitals like Party B can use user ID part number as ID, but have totally different features. They can follow a particular VFL algorithm protocol to achieve model training without privacy leakage. For example, to train a privacy-preserving decision tree, participants have to follow the protocol defined in maybe Secure Boost. As shown in the right figure, when we start a VFL job, the job can be described as a directed acyclic graph, DAG for short. Between each component, the DAG, there are control flow messages to deliver the control command, such as submit a job or cancel a job or report the job progress. Each component of the DAG is a subtask, such as intersection and secure boost. Inside the component, there are algorithms flow messages to synchronize the variables as is shown in the figure. And the most fine-grained message is the data flow message, which transfers the encrypted data between parties. The common VFL algorithms are based on the following assumptions. First, semi-honest assumption, which is the most common used assumption in VFL algorithms. The semi-honest adversary follows the protocol, but may try to learn more than allowed from the proto transcript, like intermediate results. Secondly, the malicious assumption. The malicious party can run any attack strategy to compromise the VFL participants. So here's the question. Given that there are plenty of semi-honest assumptions-based VFL algorithms, what if the semi-honest party turns to malicious? Let's take a look at some potential threat models. As we mentioned above, the transmit messages in VFL process can divide into 3 levels. When semi-honest party turns to malicious, the adversary will not follow the secure protocol. Therefore, we propose 3 types of threat model based on the message flow of VFL process. First of all, the control flow attack. The malicious party can send specific command in the control flow to attack the VFL jobs. For example, the malicious adversary can prohibit the model from conversion to the best performance by sending any early stop. And secondly, the algorithm flow attack. The malicious party will not follow the algorithms and modify the transmit message to perform an attack. For example, the malicious party can send extra message that contains the DEMPO's labels, which is the most private data in the party. And thirdly, data flow attack. Apart from violating the predefined protocol, the malicious party can also attack the system through model poisoning and data poisoning. The malicious party can use the poisoning attack to perform a targeted attack, for example, misleading the model to predict green cars into birds, or untargeted attack, simply poison the model such that performance in each label is reduced. Before we go through our challenges and design, I want to clarify that the function of verification framework is different from secure protocol. A verification framework can detect and prevent the attack from VFL, but cannot keep the job running under a malicious assumption. However, there is no once-of-all secure protocol as well. In this case, a verification framework can enhance the secure protocol in real-world industry. Our goal is to design a trusted, automatic, and accurate framework for VFL job verification. Thus, we mainly face the following challenges. When there are malicious attackers on the end host, how to ensure that the framework is still trusted and difficult to hack? With the rapid development of federated learning, various algorithms are proposed, such as FedAVG, FedVision, Secure Boost, and so on. How to ensure the framework automatically adapts to these different algorithms? And last but not least, various random algorithms are used in the federated learning to ensure randomness. Machine learning algorithms bring randomness, and encryption algorithms bring randomness as well. How to overcome the randomness and verify the VFL job accurately by reproducing it. To overcome the challenges, we have the following 3 design choices. First, instead of designing the AGIS as a pure end-host solution, we design AGIS as a gateway plus end-host solution. The gateway can be controlled by a trusted third party. Such design is practical in real-world scenario. Secondly, although VFL algorithms vary from each other, the whole process can be represented by a finite state machine, FSM for short. Thus, we used an FSM to decouple the VFL algorithms and the verification. Last but not least, the randomness in the VFL algorithms is provided by the random variables, such as random seeds, random masks, which means if we fix the random variables, the VFL job can be perfectly reproduced. For data flow verification, we store random seeds for data sampling, shuffling, encryption, and decryption to reproduce the VFL job and provide accurate verification. Here shows a simple deployment in real-world industry. For the security of the internal servers, all messages will be forwarded through the gateway. We assume that the gateway is secure and cannot be accessed by the VFL parties. From this observation, AGIS is designed to integrate with the gateway, and we collect messages from the gateway. In this way, we not only make AGIS trusted, but also convenient to collect the data. Secondly, let's see an example to generating an FSM from a VFL algorithm. Let's take RSA intersection as an example. Participants' behavior can be abstracted as transactions among different states. The transition between states is triggered by sending or receiving particular messages. For example, on the host side, we begin with the state 0, and if we send a public key to the guest side, the state will transit to the state 1. And step by step, if the VFL job run as expected, we will finally end to the end state. However, if the FSM detect any unexpected messages, it will transit to alarm state and trigger the emergency plan of the user. The situation is similar at the guest side. The core idea of reproducing based verification is to reproduce a VFL job in a trusted execution environment and compare the data with the original job. It contains 3 phases: data collection, task reproduction, and signature comparison. First, during the original VFL task training, AGIS is in the data collection phase. 2 parts of the data are collected: data for reproducing a task and data for signature comparison. The second phase is the task reproduction. AGIS analyzer will launch a reproduction task. The participant can be verified using the collected hyperparameters and random factors to start a VFL task. The VFL task interactive with the multiple VFL participants. All signatures of transmit message will be stored. Third, in the signature comparison phase, all signatures of transmit messages in reproduction will be compared with the previous collected signatures. Here's the testbed setup. We use the most widely adopted algorithms in a real-world application to evaluate AGIS, logistic regression, and secure boost. And we use three data sets from medical domain and the financial domain. And let's just go to the evaluation part. Let's see the security analysis first. We proposed and implemented 9 types of threat models, and the majority of them can be detected. However, the poisoning attack in local data sets cannot be detected because currently we do not have a trusted environment technique to support the storage of large training data sets. Therefore, malicious party can always modify the data set to cheat the verification. And the overhead analysis shows that the FSM-based verification can be conducted with a very short time and enough for real-time verification. While for the postponed verification by reproducing the VFL job, first we analyze the time saved in communication by using Ijcai. Figure shows that first Ijcai can reduce more communication time when the data set becomes larger, which shows that the Ijcai is scalable enough for a real-world deployment. Second, Ijcai's behavior varies with different algorithms. The reason is that the communication of LR is related to the sample size, and while the SBT is related to the feature size. Second, we focus on how Ijcai reduce the computation time. We define the ratio of feature dimension owned by host to guess SR. The result demonstrates that when host side has more data, Ijcai can reduce more time when performing reproduction tasks. In conclusion, the fact that semi-honest party could turn to malicious is a common concern in real-world industry. And making the VFL process verifiable can promote the convincingness of VFL algorithms and secure protocols. And there's still some future work for this framework. How to improve the efficiency of reproducing VFL job is still challenging, and how to detect the data poisoning attacks is also worth to investigate. We also can try lifelong verification for training and inference in the future. Okay, that's all for my presentation. Is there any questions?
Oh, sorry, we don't have enough time for the question and answer. So thank you very much, Chengguang. So please stop your screen sharing. And the next is our first invited talk this afternoon. It is Federated Learning for Industrial Video Recommendation. It is presented by Hao Li from Tencent. Please allow me to introduce Hao Li to you. Hao Li is the tech lead of privacy computing at Tencent VC. VC is an app for users to create and share their short videos. As a principal researcher and engineer at Tencent, since 2018, he has been focusing on data security and privacy by distributed and decentralized cross-silo and cross-device federated learning, and privacy preserving machine learning by program analysis and secure multi-party computation. Before Tencent, he worked as a software architect at Intel. He received his PhD from Peking University and a postdoc from Columbia University. He has published several papers in top system conferences. Okay, so let's welcome Hao Li. Please start your screen sharing. It's your time. Thank you.
Thanks for the great introduction. Let me share my screen. All right. So hello guys, I'm Li Hao. It's a pleasure to have a chance to contribute to FTL Ijcai workshop. So the topic of my talk is federated learning for industrial video recommendation. All right. So here is the agenda. So first, I will give a brief introduction about Tencent Online Video Business Unit, OVB in short, where I come from. Then I will explain why OVB needs federated learning. Next, I will introduce the current status of Tencent data soils and federated platforms. Then I will share 3 federated learning applications within Tencent OVB. So finally, I will summarize with takeaways of my talk. All right, let's get started. So the Tencent OVB is a newly established video business unit within the Tencent PCG. The Tencent PCG stands for the Platform and Content Group. The 2 main products within the OVB is a Tencent VC and Tencent Video. So other than VC and video, OVB also includes 应用宝, sports, and also TV. So as you may have already known, that Tencent VC is a short video creation and sharing platform. So while the Tencent Video is a leading long-form video platform. So why does Tencent OVB need federated learning technology? So first of all, it's all from the business requirement. So the OVB, so for example, VC, has a strong user growth needs. It has multiple business indicators, including DAU, PV, UV, CTR, CVR, LTV, and also user duration and retention. Second, Tencent itself is rich in user data, thanks to Tencent's fruitful products and services. So briefly, Tencent has multi-dimensional user profile, including social networks, entertainment, and news behaviors, apps, consumption records, browsing data, healthcare data. Oh, sorry, someone just pinged me. All right. And the second reason that why OVB needs federated learning is that Tencent itself is one of the FL evangelists. And there are multiple business units already adopted federated learning to solve the real business problems. So for example, in financial risk control or online advertising. But unlike existing FL applications, the OVB FL is unique in several ways. So for example, the OVB FL is the first FL guest within the Tencent. Second, the OVB has some specific requirements. For instance, OVB needs to identify welfare sensitive users, which is important for OVB business. In addition, both explicit and implicit user profiles are equally valuable to OVB. So what's more, the OVB FL targets internal usage only. So which means that OVB has less concerns over data leakage comparing to other Tencent's FL applications collaborating with outside companies. So this uniqueness of OVB FL leads to several challenges. As a FL guest, the OVB FL is result driven. So unlike other FL hosts merely doing the data collaboration services, OVB FL cares about the business indicators like user duration, DAU, etc. So similarly, OVB also cares about performance. So for example, they care about the online efficiency and offline accuracy. And since we care about the results and performance of cross-domain data collaborations, so we strongly realize that FL itself is a tool that should be used in the second step. And the first step should be data preprocessing, algorithm designs. Now let's take a look at the Tencent data soils and the federated platforms. So as mentioned earlier, the Tencent PCG has multi-dimensional user data in sectors like video, social, entertainment, and news. And for federated platform, other than the Fate platform that Tencent co-worked with the WeBank, we also have Tencent Android Power FL, which is totally developed in-house. And comparing to the generic Fate platform, Power FL is fully optimized towards Tencent's platform, and it has optimized cryptographic primitives, including the homomorphic encryption and also TEE. Now I will share 3 cases of OVB FL. The first case is that we want to leverage cross-domain user profile for OVB new user video recommendations. So concretely, in this case, we realize U2U2 tag for new user recommendations. So in this case, OVB works closely with Tencent Ads, and we leveraged a vertically split federated dual tower model. The Tencent Ads provides static user features X as input to the user tower. For example, the X might include sex, age, education, marriage, work, life, status, etc. The OVB provides video consumption history X and also label Y as inputs to the item tower. The Y might be short video categories, tags, etc. So for samples, so we take users like follow, share, or comment as positive samples and take users' fast sleep, short playing time as negative samples. Since it's a federated neural network model, and we follow the traditional federated ways to train the model. So precisely, we take user tower and item tower as our bottom models and use the inner product of the item and user embeddings as a top model. And for the interactive layers, we conduct direct communication and protected by the differential privacy. And we use cross entropy also as our loss function. And there are several implementation details. And since this is the first case, so I will elaborate on the details. So in the training phase, the Tencent OBB dominates the data sampling, feature selection, and the feature engineering process. So in addition, OBB also selects the key users. The private federated ID mapping is conducted during the PSI step. And we train the federated DSSM model with PowerFL to obtain both user and item embeddings. So as mentioned earlier, that OBB-FL cares more about online efficiency, and we are less worried about whether the embeddings will reveal the raw user data or not, since it's used internally. So in our online inference phase, so we simply indexed and cached the key users embeddings for online U2U retrieval of key users tag for new users. And also there are some strategy designs. For example, we figure out that we should select 10 tags of 10 similar key users as new users tag. And the results are significant. So we achieved more than 3% increase in average playing time per user. This is the case one. So the second case is advertising strategy co-modeling with Tencent Ads. So in this case, we worked with Tencent Ads as well. And we want to work out an advertising purchasing strategy that will give OBB high quality customers with high next day retention rate. So we leveraged the vertically split federated single tower model. And similar to the case one, the Tencent Ads provides some static user features, X, as input to the user tower. But for item tower, the Tencent OAB provides next day retention rate as user label Y. So again, we use the traditional federated neural network model. The bottom model is user embedding from Tencent Ads, for example, fully convolutional network model. The top model is Tencent OAB's labels, and the interactive layer is direct communicated between OBB and Tencent Ads, also protected by the differential privacy. And loss can be cross entropy, etc. And for implementation in details, so in the training phase, OBB dominates the generation of user labels. So while the ads dominates the user sub-model design and feature selections. What's wrong? Should I go on?
Okay, sorry, I just muted him.
Okay. So the federated file ID mapping is conducted during the PSI phase. And in the inference phase, Tencent Ads periodically generates the predicted probability of next day retention rate for all users. Then OBB formulates the advertising strategy based on the predictions results from the Tencent Ads. And for results, we achieved over 7% gains, which means under the same or even lower cost, we could achieve a better retention rate. This is the second case. So in previous case one and case two, OBB leveraged cross-domain static user profiles and features. And in the third case, OBB conducts cross-domain implicit user behavior modeling and transfer learning for OBB's new and co-user recommendations. So the business scenario of this case is that we knew it would be difficult to profile new or co-users with OBB's limited and sparse interaction data, which will lead to overfitted models. So we instead take a transfer learning way for cross-domain user behavior modeling. So precisely, we pre-train a backbone network utilizing the rich user interaction data in a source domain. For example, Tencent Video for implicit user profile. And then we fine-tune the implicit profiling network with the data from the target domain, which is VC. Of course, we need to conduct PSI between the video and VC users to obtain the intersected users. So in this way, we can acquire both the user embeddings and item embeddings. The user embeddings reflects the short-term interest from VC users. And for item embeddings, it stands for VC video embeddings. And for serving strategy, we generate and store the both user and item embeddings offline and conduct U2I offline online retrieval for recommendations. So this is the U2I case. It's a result. All right. Okay. Okay. So the results are acceptable, and we are still optimizing them. And we took 30 days of video data as source domain data, and took 7 days of VC data as target domains. All right, finally, as takeaways, so we want to share some of our observations. So first, the positioning of federated learning, or broadly privacy-preserving computing. So we want to emphasize that the law goes first. So it means that we should only do data collaborations between institutions with data collaboration permissions. And then it comes to federated related techniques. These techniques are promising tools for cross-domain data collaborations. And the second, we want to emphasize is that the business requirements and data requirements are the true motivations for data collaborations. And FL and related techniques will be appealing in that respect. And as a FL guest, I think from our FL guest experience, we would recommend that we should first verify the effectiveness of data and algorithm in a non-federated settings, and to obtain some gains, the business gains. And then after obtaining the business gains, then we do it federatedly. Third, we believe federated learning or privacy-preserving computing will be the trend. And as a trend, the techniques are still evolving. And personally, I am confident that the data markets will be coming in the future. So that's my talk. Thanks.
Okay, is there any questions for this talk? Many thanks to Holly. Okay.
My pleasure.
Yeah. Is there any question? So I have a question. You just mentioned your team just developed a new framework for federated learning. Is there any plan for your open source plan or something like that?
The PowerFL framework or platform was developed mainly by Tencent TEG and CDG, and we as customers of PowerFL use that for applications. And for outside collaboration, we use Fate. And I think from what I know, they will have plans for open sourcing the PowerFL platform.
Okay, many thanks.
Yeah, my pleasure.
So is there any questions?
All right, good.
Okay, good. Thank you very much. And
sure.
Okay, so let's welcome our next invited talk. Okay, so I see. Yeah, next talk is federated continual and semi-supervised learning from Songjun Huang. Please allow me to introduce Songjun Huang. Songjun Huang is associate professor in the Graduate School of Artificial Intelligence and the School of Computing at the Korea Advanced Institute of Science and Technology. It's CAST. Prior to working at CAST, Songjun worked as a postdoctoral research associate at Disney Research and as an assistant professor at UNIST. Sunju received his PhD in computer science at the University of Texas at Austin under the supervision of Professor Christian Groman. Okay, so let's welcome Sunju Wang for his presentation. So just turn on your mic and camera. Oh, it's your time. We cannot hear you, Sunju Wang.
Thank you for a nice introduction. Yeah, so the title of this can you all hear me?
Yes. Please start your presentation.
Okay, so the title of this talk is Federated Semi-Supervised and Continual Learning. And I'm an associate professor at Ijcai and also a CTO at a medical AI startup called AI-Tricks. Okay, so there are, as you already know, there are many challenges, practical challenges of federated learning, such as dealing with various heterogeneities, such as systems heterogeneity, statistical and architectural heterogeneity, and ensuring data privacy and making the communication to be efficient. But however, many of the existing works on federated learning mostly consider standard learning settings where the local model is trained on like a fully labeled data for a single fixed task. Okay, yeah. So some of you might disagree because there are methods that there are cases where we train the model in an unsupervised manner for like language model. But what I'm considering here is the case where where we are trying to predict the label, right? For when the ground truth label is available, right? So if you consider such a scenario, if you consider a realistic scenario, then this may not hold, because for some cases, it's not really easy to obtain the label data. For instance, suppose that you are training like a posture recognition model to evaluate whether you are doing the correct posture for your exercise routine. Then obtaining those labels at each each local user is almost impossible, right? Because we don't know which of the postures are correct, right? So in many cases, the local models need to train on partially labeled or even unlabeled data, right? Even if your goal is to predict the label. So because of the difficulty in acquiring the labels at the client side. And moreover, each of the local models could continuously train on the new tasks. So instead of just evaluating estimating the posture for the squat, we can estimate the posture for many different exercise routines, right? So today I'm going to introduce methods for tackling these two new problems for federated learning, which are federated semi-supervised learning and federated continual learning. Okay, so I'll first introduce the work on federated semi-supervised learning. So as you have seen, the data acquired at the local client could be often partially labeled due to the difficulty in obtaining the ground truth labels at the user or the client side. So now we have to solve a new problem of federated semi-supervised learning, where each client learns from a partially labeled or even unlabeled data. And I'm going to describe you two practical scenarios for federated semi-supervised learning. So the most common scenario for federated semi-supervised learning is where the end users intermittently annotate a small portion of their local data. So it's not difficult to label the data, but due to the amount of the time and effort that goes into the labeling process, we're going to end up labeling only a few of them, right? So for instance, for face albums, so they ask you to label the faces, but you cannot label every face, right? In your photo album, right? So you only label some of them, and the rest of them are going to be given the labels using some kind of semi-supervised learning method. So we call this scenario as the labels at client scenario. So where both the labeled and the unlabeled data are available at each local client. So in another case, annotating the locally generated data may require expert knowledge, as we have seen in the case of the posture recognition, or for like annotating medical images. So the end users at the local client may not be able to do the job because of the lack of the expertise. So we may only have the labeled data available at the server side, right? And the client could only work with the unlabeled data obtained at the local client. Okay, so we can naively combine the federated learning algorithm with an existing semi-supervised learning method to solve this problem. For instance, we have like a state-of-the-art semi-supervised learning method such as fixed match, which works in this way. So given some unlabeled example, we can transform the given image by using two different augmentations, like weak augmentation and strong augmentation, and enforce their predictions to be the same, right? So this is called the consistency regularization, and this is a very popular method for semi-supervised learning models. And after that, we can also use the predicted labels. So the class label with the highest probability as the pseudo label to train this for this example. So we can train the model using the pseudo label. But the problem is that when we aggregate the parameters that are trained on unlabeled data, they actually contain unreliable knowledge, and they could have like a wrong pseudo labels, right? So aggregating such knowledge by the model aggregation could actually hurt the performance. So we propose a novel federated semi-supervised learning method called FedMatch that enhances the reliability of the unlabeled data via two different techniques. Okay, so the first technique is inter-client consistency loss. So for the conventional semi-supervised learning method, we use the consistency regularization between, so that enforces the predictions to be similar across two differently augmented samples, right? But for federated learning, we have models from other clients, right? So what we do is that, so we select the helper agents, which are the models that are close to the local model, and we can select them by their functional similarity. And measuring the functional similarity could be done by injecting some noise and measuring and using the output class probability as the functional embedding of the model. So if the two models have similar output class probability for the same random noise, then we can use them as we can consider that they are similar and obtain those helper agents and enforces the consistency across the predictions, across their predictions. And we can even use the agreement. So we take the class with the highest probability as a pseudo label for this example, and then use it to train the model. Okay, and we further decompose the model parameters into the parameters for supervised learning and unsupervised learning to further alleviate the effect of the negative transfer happening from the unlabeled data to the labeled data. So given the parameter data, we additively decompose it into the part for the labeled data and the unlabeled data. So for labeled data, we only train this part, sigma. But for the unlabeled data, we train both part. We use the parameter from the labeled data and also add the parameter for the unlabeled data to it, and then use them both. So this actually can prevent the unlabeled data from negatively affecting the reliable knowledge that's captured in the parameter for the labeled data, because the labeled data only use this part, but do not use any of the knowledge from the unlabeled data. The unlabeled data can use both. Okay. And the actual experimental results show that if we just train the model on a sequence of unlabeled data, then as the model trains on, the model may obtain poor performance on the labeled data, or the forgetting could happen. And this parameter decomposition effectively does away with that problem. Okay, so the training objectives are very simple. For the labeled data, it's just a regular cross entropy term. And for the learning on the unlabeled data, so we minimize the interclient consistency regularization loss and the sparsity regularization term on the side. So we make the parameter for the unlabeled data to be sparse because they have to be communicated. So to reduce the communication overhead, they are made to be sparse. And we also have a regulator which prevents the parameter for the unlabeled data to be drifting away from the parameter for the labeled data. Okay, so there are two different scenarios. For at the label set client scenario, we have the labeled data and the unlabeled data at the local client. And for this case, we just obtain the helper agent based on their functional similarity, and then use them to enforce a consistency regularization on their predictions. And for the label set server scenario, the parameter decomposition becomes really handy because we can just train the supervised the parameter for the supervised learning at the server, right? At the server, and at the local client, we can only train the parameter for the unlabeled data. So each local model receives the parameter for the labeled data, and then add the parameter for the unlabeled data and train the parameter for the unlabeled data. So this is the only part that are being trained. So this allows disjoint learning. So we train for the labeled data and the unlabeled data at the server and the client separate manner. Okay, so everything else is the same. So we validate our method under conventional IID and non-IID settings for the batch data, but also consider the streaming non-IID setting, where each local model trains on an unlabeled data stream, okay, or a partially labeled data stream. So this is a more realistic case because I mean, each of the devices will gather more and more data as the time goes on. And it shows that our method outperforms both the local semi-supervised learning model and the naive federated learning SSM models. So the yellow line and the blue line shows the naive base size. And we can see that this red line, which shows the performance of our fed-match algorithm, largely outperforms them. So the gray line shows the performance of the model where we assume all the unlabeled data are labeled, right? So these are like the upper limit. So both at the label set client scenario and the label set server scenario, the fed-match largely outperforms the naive combination of the federated semi-supervised learning and the federated learning and semi-supervised learning method. And on the streaming non-IID setting, using the naive model combination of the federated learning and semi-supervised learning actually underperforms the local semi-supervised learning at times. But our method obtains highly improved performance at a smaller client to server communication cost due to the sparsity of the parameters. And the further evaluation study shows that both the interclient consistency term and the parameter decomposition are effective in improving the performance of the method. And I'm going to also introduce the federated continual learning. So this is the second work. This considers a scenario where each local model trains on a sequences of tasks. So this is different from the data different from the sequence of the task for the other local models. For instance, if we might want to train the model to diagnose of some virus, right? Virus infection. And first, it could be adenovirus. Then if we have like a COVID outbreak, then we might want to reuse the model for the diagnosis of the COVID symptoms, right? But when doing so, we can make use of the knowledge that obtained from the previous task to better learn on the new task, right? So that is what continual learning does. So it performs the knowledge transfer across the task, mostly from the earlier tasks to later ones. And but if we can transfer the knowledge across the client, then that could be even more helpful, right? So if we have a model that's trained for SARS or the MERS virus detection, then we could somehow use their knowledge to better learn at this hospital, right? So we can transfer the knowledge across different institutions or devices. Okay, so again, naively combining an existing continual learning with a federated learning algorithm is going to be highly suboptimal because of the problem of inter-client interference. So if you average the two models that are trained on completely different tasks together, then they can negatively affect the performance. So for instance, if we have a model that performs a digital recognition on the MNIST, then it can actually obtain positive knowledge transfer from the model that's trained on SVHM for scene digit recognition, but it might not obtain good knowledge transfer from a model that's trained on a general object recognition. So this is the performance of the model that's averaged with the model trained on SVHM. And this is the performance of the model that's averaged with the model trained on CIFAR-10. Okay, to prevent such inter-client interference, we propose an algorithm where each local model selectively leverages knowledge of the relevant task from the other client. So each local model has the task shared parameters that are shared across different tasks. So everything here is the same with the conventional federated learning. So these task shared parameters are sent to the server and aggregated and redistributed to the client. But we also have the task adaptive parameter. So we additively decompose the model parameters into the task shared and the task adaptive parameters, and the latter contains the knowledge of the specific task. For instance, when we train to recognize like a lion or the tiger, then this parameter is going to be specific to the tiger recognition. And we also have a sparse mask for obtaining the task relevant part of the parameter from the task shared parameter. And then these task adaptive parameters, because they are separate from the task shared parameter, they are sent to the central server. So we have some kind of knowledge base that contains the pool of the task adaptive parameters. And they can be reused when each local model trains on a new task. So for example, when you learn about the lion, it can obtain the parameter for recognizing like tigers and the rabbits. But instead of just using all of them, we can actually learn the weight to obtain a weighted combination of the task adaptive parameters. So this way, it's the indirect experiences that are relevant to the target task. Okay, so the learning objective is as follows. We learn the decomposable parameter data T for each client C at the arrival of the new task T for the following objective. First, we have the spatial inducing regularization term. We have the loss. We have the spatial inducing regularization term for tasks between mask and the task adaptive parameters because they need to be sparse to reduce the server to client communication cost. And we have some retroactive update term, which allows the parameter for the past task to be similar, even if the task shared parameters changes. Okay, so this is how the communication is done. Each client sends the specified task shared parameters by applying the text-specific mask and send them to the server, and they are aggregated and sent back to the client. And also the task adaptive parameters are also sent to the central server and is contained in the knowledge base and is used by the other clients when they are learning on the new task. So we consider two different task configurations. First is a case where we have some overlapping set of clashes across different clients. And the second data set, in the second case, the older data sets that are older task sequences that are trained on each client are completely disjoint. And the experimental validation results of the Fed weight against the naive base size show that it largely outperforms this base size with a reduced client to server communication cost. And when we plot the accuracy as a function of the communication cost, our method outperforms the baseline at different communication cost. And the Fed weight effectively prevents a catastrophic forgetting with almost close to zero backward transfer. This is the amount of the accuracy loss on the previous task, and we can see that it's almost zero. While the baselines suffer from some of the loss or the catastrophic forgetting due to the interclient interference. So examining the allocation weight, the attention mask, actually shows us that the Fed weight obtains the parameters from the relevant task. So for example, when learning on the MNIST data set, it obtains the parameters that are trained on the traffic sign data set and the SVHN data set. So for the traffic sign data set, because the traffic sign contains many of the numbers, they are definitely relevant for the digit recognition task. Okay, so in conclusion, in many real-world scenarios of the federated learning, the local models may need to train on a sequence of tasks as well as on partially labeled data. And we proposed two different methods for tackling those problems. Okay, so this is the end of the talk.
Okay, many thanks to Sanju Hong. Is there any questions about this talk?
Oh, okay. So Yang Li Yuan just asked how to calculate the functional similarity between the clients. Okay, so at the server side, we inject some noise to each of the local model that are obtained at the server. And then use the output class probabilities to measure the functional similarities across the client. Use the output vector, the class probability vector, to compute the similarity for just random noise.
Okay, thank you for your presentation again. And so we do not have enough time for the second question. So let's move to the second session. Let's welcome Yang Liu from Tsinghua University. She will take the host. Yang, please take the host.
Okay, thank you.
Okay, thank you, everyone. Thank you, Vivi. Can you hear me? Okay. So it's a great pleasure to be here and host the next section. So now we have, for the next section, we have Professor Ming-Sheng Long. Professor Ming-Sheng Long is an associate professor with the School of Software, Tsinghua University. And his research is dedicated to the theories and algorithms of machine learning with special interest in transfer learning, deep learning, and learning with the scientific knowledge. So let's welcome Professor Ming-Sheng Long to give us this great talk. Professor Ming-Sheng Long, are you there?
Yeah, I'm here, but yes, so I'm not a co-organizer, so I can share the screen. Hello, so could you see my screen? Excuse me?
Yes.
Okay, thank you. So good afternoon, everyone. First of all, I would like to thank the Professor Yang and all the co-organizers for giving us this very wonderful workshop. Today, I will talk about the transfer learning from the theories, algorithms, and the open library perspectives. Okay, so as we know, supervised learning has a very solid theoretical guarantees under the IID setup. So this is a very well-known generalization bound, and we are very familiar with it. In the case of transfer learning, however, it deals with the learning problem across domains of different distributions P and Q. For example, the source domain follows distribution P and the target domain distribution Q. The distribution may be different, and this is called out of distribution problem or OOD. So from IID to OOD, a principal question is how to bound the generalization error of the target domain because the target domain is fully unlabeled. There are many representative approaches to transfer learning. Basically, they aim to learn to match distributions across OOD domains such that P could be made approximately similar to Q. There are three cases. The first is covariance shift, also known as feature distribution mismatch. It is the mainstream work of this field. The second is prior shift, and there are still very few work on this, and it's very challenging. The third is conditional shift. It is also very challenging, and we only see very few work on this. Also, there are two sets of representative approaches. The first is kernel embedding, and the second is adversarial learning. But basically, there are no theoretical guarantees for most of these approaches. And we would ask a question. So why can we bridge the theory and the algorithms and close the gap in between such that our algorithms can work in general cases? Now comes to the theories and algorithms part. First, we would review some classical theory in this field. We are always familiar with the statistical learning setup, and we have a data set, sample ID from some distribution P, and we learn a model by minimizing the training error on it. And we expect this model to generalize to the test data. And we have this very general result. But in transfer learning, we know that the source distribution P and target Q are different. And the principal problem is, can we control the target distribution Q? So in this field, there is a very basic idea. It's about the disparity. It is the disagreement of two classifiers, H1 and H2, on some data set B. So this idea is widely used in many fields, such as semi-supervised learning. We try to train two classifiers and make them consistent on the unlabeled data. And so we believe that this classifier can generalize to the unlabeled data. And in ensemble learning, we also see this disparity notion. So why we need it? That is because the computation of the disparity does not require the labels. You can see that it is defined based on the classifier itself, but does not need labels of the target. So potentially, we can compute this disparity on the target and on the source. So the basic idea is to relate the task risk, target risk, ipsum Q, and the source risk, ipsum P. Here it is in the population setting. And by using the very simple triangle inequalities, we can break the target risk into three parts, which can bound it. The first part is the source risk. And the second part is termed the ideal joint error. It is defined when all the source and target data are labeled. so we can estimate it. But actually we can't. The third term is the disparity difference. You see that the first term is the disparity on the source P, and the second is the disparity on the target Q. So in this field, a very basic assumption is the small ideal joint error assumption. That is, if the source P and target Q are fully labeled, then there exists an ideal hypothesis H star such that the joint error is small. This is an assumption. We are not sure whether we can hold this assumption, but based on our practice, in many cases, this assumption holds, especially when this hypothesis is a deep neural network, such that it can simply feed both the source and target data. So this is assumption. So based on this assumption, we will see that if we can bound the red term, then we can bound the target risk. However, in this term, both H star and H are unknown. So we can only consider the worst case. The worst case is that we traverse all the possibilities of H and H star such that the maximum or supremum of the disparity discrepancy can be computed. So this is the well-known H delta H divergence. You can see that given a source P and target Q, both are unlabeled, we can compute this supremum in the worst case sense. So this is a good news. Okay, based on this H delta H divergence, we will have this generalization bound as this. And this one is assumed small, and this is the 1 over square root n sample rate, which is identical to the IID setup. So we only need to control the source error and the target and the source target divergence in the empirical case, then we can bound the target risk. However, we can see that this divergence is hard to compute and optimize for real algorithms. For example, for binary hypothesis H, we can further derive this divergence into this way. We first use the definition of 0-1 loss, and then we try to expand this hypothesis space H delta H into a bigger one. So this bigger hypothesis space can either be a neural networks or a kernel spaces. That is a function space that can be approximated by kernel machines. So we only need to bound this last term. Okay, so this comes to a very famous work of this field, the domain adversarial neural networks, or known as adversarial domain adaptation. So we try to learn a domain classifier such that it can best discriminate the source from the target. So we minimize the classification error of this domain discriminator D. It is equivalent to this taking the supremum, right? Because it differs by a minus sign. So maximize this is equivalent to minimize the error of D to classify the source from the target. So the red term is to approximate the upper bound of the divergence. And so the blue term is to minimize the source error. So by formulating adversarial game such that the features are learned to minimize the right-hand side of all these terms, and the red terms to approximate the supremum as this red term, we can achieve domain adaptation in some way. Also, we can replace this D from a parametric neural network into a non-parametric function class as widely used in the integral probability metric, such as maximum mean discrepancy and versus distance. And we will come to another algorithm called the deep adaptation network as this. For example, we compute the distance between P and Q using this MND formulation. it used the function in kernel space to embed our features into high dimension space, such that when matching the expectations of P and Q is equivalent to matching all the moments of the statistical distributions. And we also try to find an optimal kernel K such that this distance is maximized. This is also take the spirit of this bound. We need to find the worst case such that this distance can best characterize the differences between the source and target. And then we try to find the feature to minimize such a worst case distance to yield a bound. Okay, so this is one work I done in ICML 2015. Now comes to the second theory, the margin theory we did in ICML 2019. We find there's still a gap between the theory and practice. The first is that existing theories focus on binary classification, but in practice we need multi-class. And the theory focuses on discrete classify, but in practice we need a scoring function classify. And third, this discrepancy, although does not need a label to compute, but in practice is still somehow hard to optimize. So how to bridge these gaps? Our first step is very simple. We just modify the previous discrepancy by a very minor point. Just to see this red one. In the original H delta H divergence, this supremum is defined by taking all the hypotheses H and H prime over the hypothesis space. But we find that this H can be used as a reference classifier, and we don't need to change it. We only need to traverse this H prime in the hypothesis space. So this turns into a new disparity discrepancy or DD metric. We can also prove using this DD, we also have a generalization bound taking the similar forms as the classical theory. But it's very important to see that this discrepancy is definitely smaller than the previous one because it only takes the supremum according to one hypothesis space instead of two. So the bound will be tighter. Okay, so from an illustration, we see that the previous H delta H is this, and the DD is this. We have a reference hypothesis, and all the DD is computed based on this reference hypothesis. Someone will notice that we can simply use the source classifier as this reference hypothesis. It is good enough. So we further break this DD into a new upper bound, and we can see that we can integrate the prediction of the source classifier H into this upper bound. So we can use a conditional domain discriminator, which is conditioned on the source classifier prediction into the training of the discriminator. We can also use in IPM to approximate this supremum. So this comes to another two-settle method. The first one is conditional domain adversarial network, or CDAN, which I presented in NIPS 2018. We can just plug in the classified prediction G into the domain discriminator training, and we will get much better result. This can be seen as an approximation or implementation of the DD discrepancy instead of the traditional H delta H discrepancy. We can also use IPM or integral probability metric to yield or to approximate the supremum or the worst case. So this is a very traditional cross-covariance operator studied in kernel embeddings technologies. And I just use it to compute the discrepancy between joint distributions of the feature representations and the classified predictions. Okay, so we can also formulate this minimax game in order to make to approximate the upper bound. This is called a joint adaptation network, which I presented in ISML 2017. There is a recipe. When should I use this domain discriminator, and when should I use the discrepancy-based method? The answer is simple. This IPM-based method usually works better than the F divergences. So domain discriminator use F divergences when domains are less overlapping. Just imagine when the two domains are very far away. If you train a classifier, the classifier can simply discriminate both domains. So it is very hard to confuse the domain classifier. In this case, the F divergence will degenerate, but IPM will not. Our experiment validate this finding. For example, in the larger scale domain net vision data set, we find that such IPM-based method may work better than the domain discriminator-based method. Okay, so we still have a problem of multi-class classification. In multi-class classification, we usually use scoring function. It is a real value function. And the labeling function can be induced by the scoring function by taking the class that yield the highest score. So we have a scoring function space F and a labeling function space H. We can also define the margin of a hypothesis as this and the margin loss as this. Both are standard in statistical machine learning theories. Okay, so based on these definitions, we'll have the well-established margin theory. So this is the margin error defined based on the margin loss. And we'll have this bound. We will see that in the ID setup, our bound can be improved by this rho, a factor of rho. So this rho is the margin. It is the confidence margin. When rho is bigger, our confidence about a class prediction is certain. So we will see that confidence margin is bigger, our bound is tighter. So we can use this result and extend it to the OOD setup. So we also do some minor modifications to previous theories and introduce this margin idea into the previous defined disparity discrepancy. We get MDD. That is, the supremum is taken over only one hypothesis space, but the loss function is changed from the 0, 1 or L2 to the margin loss. So we'll get this new MDD metric. We can verify that it is a properly defined divergence by check the non-negativity and sub-additivity. Based on the MDD definition, we can also derive a margin theory for transfer learning. You can see that the target risk can be bounded by the source empirical error in terms of the margin loss of margin rho and the discrepancy, the MDD, also the empirical one based on the margin loss of margin rho. And the other terms, we can see that the bounding is improved by a factor of rho. When the margin is bigger, the boundary will be tighter. We can also prove the sample complexity order of this bound and see that it is also 1 over square root n. So it is the same as the ID setup. We can use this margin theory to derive a new algorithm we also call the MDD. It is very simple. We find the auxiliary classifier F prime to reach the supremum of the MDD. And then we find the feature representation phi to minimize the source risk and the MDD. So in practice, we can also minimize this according to the source classifier because we need to minimize the source classification error. So it potentially bridges the gap between the theory and algorithms from binary class to multi-class, from discrete function to scoring function, and with a tighter bound with only one hypothesis space. And the bounding is informative because we have a computable margin. Okay, I will speak very quickly of the last theory, the localization theory. we find there is still a gap to close. That is the asymmetry phenomenon in transfer learning. Suppose we have a simulation data set which is easy and a real data set which is hard. So the forward is hard transfer, but the backward is easy transfer. So we would expect that the forward should have a higher generalization bound, but the backward a lower generalization bound. But you can check our generalization bound is inverse, is just implies the inverse, right? The harder transfer case will have a lower bound because the source error is low and because the discrepancy is symmetric. So this should be addressed. So we further try to improve some localization techniques for this discrepancy. And we see this is the classical one, this is DD, and this is a localized one. We will see that many of the hypotheses in the space are irrelevant and we need to discard them. So when discarding this irrelevant one, we'll get a more tight discrepancy, and it can also explain the asymmetry transfer phenomena. Okay, the definition is very, very simple. We just constrain that the hypothesis space should be the one such that the source error is smaller than some radius r, and we define the other discrepancies accordingly. We can derive some generalization bound based on this result, and we are working currently we are working to turn these generalization theories into an effective algorithms. Okay, finally, I'll talk about the open library. This is the transfer learning library open source at GitHub. We support transfer learning in many different tasks such as segmentation, image translation, adversarial learning, domain adaptation, fine-tuning, and some key point detection, open set, domain adaptation, and etc. Support many cases. And we find that existing implementations for transfer learning are not very user-friendly. So we take some design patterns such as reproducible, stable, extendable, ease of use, touch region style, and well-documented. So this makes our library easily reproducible. So we also try to give some standardized implementations for many other transfer learning setups. This taxonomy was initiated by Professor Yang, and until now, most setups are still open because many setups are lacking a feasible approach. So this taxonomy 10 years ago looks very far into the future, and we still have a lot of work to do. And this is the result. We can see the origin is the result reported by the original papers. And this is ours, and we can get a very sharp improve compared to the original implementations. It is worth noting that we only use the standard implementations. We don't use any tricks. We only use the very standard data augmentations and learning rate strategies. But because this is a high standard, high quality implementation, it can get better results. Actually, this has overrides many existing results. Okay, so finally, I would like to thank my advisors, Professor Jiaming Wang, and my advisor, Professor Michael Jordan at UC Berkeley, and thank my students and colleagues. And I would also like to thank Professor Yang and Professor Sino. When I was a PhD student, they gave me very, very valuable help. Thank you.
Okay, many thanks to Professor Long again for this great talk. Do we have any questions from the audience? Okay, if not, let's say, oh, we have a question. Wu Xuyang asked, will the slides be available?
Yes, the slide will be available. I will send this to the organizers. Thanks.
Okay, thanks, Professor Long again. And because we are running a little behind the time, so we are going to move on to the next section. So the next section is another contributed oral presentation, which has 4 great talks. The first talk is titled A Novel Approach to Simultaneously Improve Privacy, Efficiency, and the Reliability of Federated DNN Learning, which is from WeBank. Will the speaker show your slides?
Yes. So let me share my screen.
Okay.
Okay, can you see my screen?
Yes, yes. You may approach.
Okay, hello everyone. Welcome to listen my talk. Today I will share my work about a novel approach of the federated DNN learning. So this method could simultaneously improve privacy, efficiency, and reliability. It also includes the Han Gu, the Li Xingfan, Bo Wenli, Yan Kang, Yuan Yao, and the Professor Yang Qiang. So there are many 3 key considerations in federated learning. One is reliability in terms of the model performance. For example, in the classification problem, we hope to improve the classification accuracy. The other is the privacy preserving. A good method in federated learning needs to protect privacy, especially people think more and more of the right of the privacy. So under this environment, privacy preserving method is needed. The final is efficiency. Not only your method achieve high performance, but also need to be efficient applying in the different techniques. In particular, the parameters of the popular deep learning method is huge. So applying the deep learning method into the federated learning may consume some time. So it is necessary to consider efficiency in federated learning method. Here is a comparison of the different approaches in the 3 considerations. In the left figures, horizon x-axis is the reliability, vertical y-axis is the privacy preserving. The definition of the details of the privacy preserving we will discuss later. We could see only our method FDR-PP we will discuss later, and the red star and the homographic encryption, the HE, the gray star, could reach high reliability and privacy at the same time. The orange and the green star is the differential privacy in federated learning. Difference is for orange star, the adding noise is large, so we could see the privacy is preserving, but with sacrificing the model performance. Otherwise, for green star, the noise is little, so the privacy is leaked, obviously. So there is the trade-off between the privacy and the reliability in differential privacy. In addition, the blue star is the distributed learning, and the green star is split-fed. Both of the 2 methods leak the privacy. And in the right figures, we calculated the log running time of the different methods when achieving the same accuracy. We could find the distributed learning split-fed differential privacy and our method FDR-PP is comparable in efficiency. But the running time of the HE exists other methods greatly. It is not on the same order of the magnitude. So in short, we could say our proposed method FDR-PP could simultaneously persist reliability, privacy preserving, and efficiency. Before I introduce our method, I firstly introduce how we calculate the privacy preserving ability. In federated learning, because the model and other information may be leaked, the attacker, such as the curious server, may take use of the leaked information to reconstruct the local data of client. Then we calculate the reconstruction mean square error between the reconstruction items and the original items under the different attacks. And the privacy preserving ability is inversely proportional to the successful rate of attacking and the reconstruction MSE. That is, the less the reconstruction MSE is, the higher the privacy preserving ability is. And also, we do a transform, we scale the reconstruction MSE, the range of the privacy preserving ability to 0 and 1 as this formula, the function f shows. Then I will give the two types of the attacks in white and black box setting. One attack is a semi-honest adversary want to reconstruct the local private data based on the gradients models. Many papers are proposed to attack input based on this idea, such as the Hanson's paper. Under this setting, the weights and gradients are known, so it's a white box attack. So if the weights and gradients are not known, that is another attack, model inversion attack. In this attack, we assume the weights and gradients are not known, and only the output is known. The semi-honest adversary reconstruct the original input only based on the output information. So in particular, in federated learning, the attacker, such as the server, may conspire one or several clients to use their models to replace other unknown clients' models to reconstruct the original input. Let's look at the results against the two attacks. These two figures are the privacy preserving in different methods against the two attacks. Y-axis is the privacy preserving ability. We could see our method, FDLPP, and the DP with large noise. These two methods could protect the privacy best. Other methods will leak the information, obviously, because the privacy preserving ability is known. So then I introduce our method, the federated deep learning with private passport, FDLPP. So which is motivated by the split fed. So we split the DNN model into the private and the public model paths. And firstly, training all network for the local client, and then only exchange the public model, the blue points in this figure, and learn a global public model. And finally, fix the public global model and train the private model, the green points in this figure. Additionally, the private models and the input data are not linked to others. Based on this split-fed architecture, we embed the passport into the passport layers, which blocks the information leakage to semi-honest adversaries and guarantees the privacy of the training data. Specifically, different clients have their own passport and not linked to others. You can understand we add a key into the private layers to protect the local data more strongly. We implement the experiment in MLIS and CIFAR10 while trying the LINET and LXNet, these two architectures. Figure A and B are the MLIS results with 5 and 10 clients participate in the federated learning. Figure C and D are the CIFAR10 results with 5 and 10 clients participating in the federated learning. By the way, the privacy preserving in these figures is white box duplicate attack. We could see in all the 4 graphs, our method red star, FDLPP is on the top right position, meaning our method reached the high reliability and privacy at the same time. And this table is the numerical details in the different method. I want to highlight that our method FDLPP is robust against both the white box and the black box attack, because the privacy preserving ability is highest among the other methods. Also, the classification accuracy only degrades only no more than 1.5% for split fed, and our proposed FDR-PP compared to the standard distributed learning. But the classification accuracy of the DP decreases more than 30% in safer-turn dataset when adding noise is large. You can see the when adding noise in DP is large, the classification accuracy from the 88% drops to the 57%. It drops a lot. Finally, the order of the magnitude of running time among the distributed learning, split fed learning, FLDP are comparable in efficiency except the crop lapse. This is HE. You can find only the HE, the crop lapse, the HE methods. The time exists the 1000, and the other methods time is less than 100. So to conclude, the federated deep learning with private passport FLTP could simultaneously possess privacy, efficiency, and reliability. FDR-PP is efficient since the public layers are directly shared with the service aggregator without using the computational demanding encryption. And also the private passport layers blocks information leakages and to guarantee the privacy of the training data. And finally, the learning of the federated DNA models with FDR-PP is reliable because from our experiments we can find low noticeable performance degradation are incurred. Okay, that is my talk. So, do you have any questions?
Okay, thank you, Han Lin. Any questions from the audience? Okay, I have a question. So, will any kind of the data be discovered or reconstructed from transferring a GAN-like model? And will that kind of data be similar to the original data?
Actually, here our setting is the ID and the horizon federated learning. Yeah, and we are researching the non-ID data to researching the different types of data.
Okay, so that's a future work.
Yeah.
Okay. Thank you. Thank you again. So then next, let's move on to the next talk. The next talk is titled "A Novel Attributed Reconstruction Attack in Federated Learning," which is presented by Chen Chen. Chen Chen, can you host your web?
Sure. Let me share my screen. Okay, good afternoon, everyone. I'm Chen Chen from Zhejiang University, and it's my honor to present our work, A Novel Attribute Reconstruction Attack in Federated Learning, collaborated with Dr. Lingjuan Liu, a senior research scientist and team leader from Sony AI. This is the paper outline of our paper. First, let me briefly introduce federated learning. Federated learning offers a privacy-aware paradigm of model training which does not require data sharing and allows participants to join and leave a federation freely. It has been widely investigated in the recent years. As shown in the left figure, we can see that the federated learning papers has skyrocketed over the past 5 years. However, recent works have demonstrated that FL may not always provide sufficient privacy guarantees. Existing FL protocols designs are vulnerable to either a malicious server or a malicious participant. A malicious server aims to infer sensitive information from individual updates over time, tamper with the training process, or control the view of the participants on the global pioneers. while a malicious participant infers other participants' sensitive information, tempers the global parameter aggregation, or poison the global model. In federated learning system, the model updates of the participants can be used to infer a significant amount of private information from shallow to deep leakage. For example, the class representatives, the membership, and the properties of a subset of the training data. Even worse, an attacker can infer original training inputs and labels from the shared gradients. One may ask why gradient cause privacy leakage. It's because the gradients are derived from the participants' private training data, and the learning model can be considered as a representation of the high-level statistic of the dataset it was trained on. So we can infer a lot of private information from the gradients. We also remark that the deep leakage means the leaking original data level private information. For example, the most recent work called Deep Leakage from Gradient and Improved Deep Leakage from Gradient have investigated how to infer original training inputs and labels from the shared gradients. However, these two works can only be applied to gradient computed on mini batches of data. In DLG, the batch size is at most 8, and in IDLG, the batch size is only 1. Additionally, these two works adopt expensive second-order optimization method, LBFGS, and use untrained models, neglecting the gradients over multiple communication rounds. These assumptions are less practical in federated learning, in which gradients are normally shared after at least one epoch of local training, like in FedAVG or FedSGD. We empirically find that the exact reconstruction of the training data from epoch average gradients seems quite hard. So in this work, we relax the problem and ask the question, is it possible to reconstruct only the sensitive training data attribute rather than all the attributes? Because not all attributes are sensitive. Motivated by this, we propose a novel attack called Attribute Reconstruction Attack, or ARA. In particular, we consider a more practical and interesting scenarios in which participants share their epoch average gradients, which are the shared gradients after at least one epoch of local training, rather than the per example or small batch average gradients as in the previous work. In ARA, the malicious server can infer some sensitive attribute from the gradients of any participants, such as the gender information, age information, location information, and genetic information. Attribute inference has been investigated in other domains such as NLP. However, none of the previous work systematically investigated ARA in federated learning. We also consider the attack under different scenarios. For example, we consider both the active server and the passive server. The active server can isolate the participant and create a local view of the model for it. By contrast, the passive server strictly follows the federated learning protocols. We also consider whether the prior knowledge of the membership, label, attribute, and label distribution are known or unknown. The intuition behind ARA is that the observations of the local model gradients can be used to infer sensitive attributes, which are in turn based on the participants' private training data. The snapshots of the gradients across communication rounds can also be exploited to generate different views of the participants' local training data, thus inferring the exact value of the sensitive attributes. Then we introduce the main algorithm. We develop a more effective and efficient gradient matching-based method called cosine matching to reconstruct the training data attributes. Demographic-related attributes are normally binary or have few values. So we assume the sensitive attribute has k candidate values, which k is a small number. The algorithm is shown in the left. In the first step, we generate the multinomial distribution for the sensitive attribute and compute the predicted attribute value. We adopt the Gumbel softmax to compute the multinomial distribution parameter over all the potential attribute values, where gamma is the Gumbel softmax hyperparameter. Afterwards, in step 2, we concatenate the predicted attribute with other non-sensitive attributes to get the virtual inputs x prime. Then in step 3, we feed these virtual inputs into the participant's model and get the virtual gradients. Then in step 4, we match the virtual gradients with the ground truth gradient in order to update the sensitive attribute. The ground truth gradients are received from the victim participant. This can be viewed as an optimization problem. When the virtual gradients become closer to the original gradients, virtual attribute also become closer to the real training data attribute. Then we introduce our experimental settings. First, we introduce our baselines. The first baseline is random guess. Suppose there are k potential values for the sensitive attribute. Then the reconstruction accuracy for random guess is 1/k. The second baseline is L2BFGS, where the sensitive attribute is optimized by minimizing the L2 distance between the virtual and real gradients. The third baseline is to train an attack model on a public data set and use the attack model to predict the sensitive attribute. The fourth one is to directly infer from the statistic. Our experiments are conducted on 3 data sets: purchase, location, and genome. These are 3 real-world data sets with privacy concerns. Then we show our experimental results. We first report the results when the membership is known. Our cosine matching method outperformed all the baseline on all data sets. We also investigate impact of the different factors in ARA. First, we investigate the impact of the attribute distribution. We found that the attribute with lower variance is harder to attack. Second, we investigate the impact of participant isolation. Compared with using the isolation, without isolation generally delivers slightly lower reconstruction accuracy. Third, we show the impact of the local batch size. We vary the batch size from 8, 32, and the number of the whole training data. We observe that smaller batch size make it harder to conduct ARA due to that more randomness are introduced. Fourth, we show the impact of training phases. We consider gradients from different epochs. We observe that the gradients of previous epochs outperform the gradients of later epochs. Then we investigate the impact of local data size. We found that ARA becomes less effective when the victim participant has more data. Last, we investigate the impact of model complexity. We adopt models with different hidden layers and show that the model with higher capacity is more vulnerable to ARA. Another case is when the membership is unknown. We launch a membership inference attack by applying a Gaussian mixture model with 2 components, including the member and non-member, on the last layer gradient variance of all the candidate records to distinguish the member from non-members. Thereafter, we derive the membership information from GMM. The problem becomes similar as the scenarios when the membership is known, and then we can just conduct ARA on the members' records. We report the results when the membership information is unknown. On purchase 100 dataset, membership inference attack results based on the last layer gradient variance significantly outperform the accuracy of the previous work. Moreover, we consider the case when the prior distribution is unknown. We initialize the virtual attribute value from a random distribution. And we find that ARA still outperforms the baselines. In addition, when the true label is unknown, we can initialize the virtual label either from a random distribution if the label distribution is unknown, or from the prior label distribution if the label distribution is known. In these scenarios, the attacker needs to optimize both the virtual attribute and the virtual label. And our ARA can still achieve a higher performance on all the data sets. To conclude, in this work, we initiate a more practical and interesting attack against FL system called attribute reconstruction attack, in which participants share their epoch average gradient instead of small batch average gradients. We propose a more effective and efficient method called cosine matching, which utilizes the cosine similarity to measure the angle distance between the true updates from the victim participants and the virtual update. Our method exhibits significantly improved performance compared to the most existing baselines in all settings. We also conduct a systematic exploration on the factors that may affect ARA. However, our work still exists some limitations, and we are going to investigate them in the future work. The first one is we found that compared with the attribute with two possible values, the attribute with wide range seems harder to be attacked. So this may need further investigation in the future. The second one is the correlation between the sensitive attribute and true label play less important roles compared to the attribute histogram variance. The third is for data set with small classes, how to exactly reconstruct the true label from the epoch average gradient is still very difficult. We want to remark that our ARA is different from model inversion attack, which aims to learn the private attribute distribution, while our ARA aims to learn the exact value of the private attribute. Another question is it possible to reconstruct multi-sensitive attribute at the same time? Or is there any theoretical bound for ARA? And what if the attacker is one of the participants in the FL system? We also consider some potential defenses, like adding noise to the gradients or use gradient compressions. And this is all for my presentation. Thank you for listening. Sony AI is hiring research scientists, engineers, and interns. If you are interested in our work or Sony AI, please feel free to contact us at our emails. Thank you.
Okay, thank you, Chen Chen, for this great talk. Any questions from the audience? So you mentioned some defense mechanisms. Can you comment more on, what kind of defense do you think might be effective to this type of attack?
For example, add the noise to the gradient. Definitely it will work, but it will affect the performance. So it depends on there's a trade-off between the performance and the privacy. And similarly to gradient compression, you can compress the gradient. And of course, you will lose some accuracy on that, but it depends on, there's a trade-off between it, and it depends on what you really want.
Okay, and this attack works whether the feature is continuous or discrete, correct?
In our work, we do not consider a continuous attribute, but actually you can convert the continuous attribute to the discriminate attribute.
Okay, thanks. Okay, thank you again, Chen Chen. Next, we have Xiao Diancheng and co-workers who will present a paper titled Half-Low GPU-based acceleration for federated logistic regression. Xiao Diancheng, are you here?
Yes. Okay, let me share my screen. Good afternoon, I'm Xiao Diancheng from the Hong Kong University of Science and Technology. Today, I will introduce Half-Low, a GPU-based acceleration system for federated logistic regression. This is an outline of my presentation. In the first and the second part, I will talk about the motivations and challenges in GPU acceleration for federated learning. Next, the design of our system will be introduced. Then I will show some preliminary experiment results. And the last part is a discussion of our future works. So first, why do we need GPU? Before answering this question, let's briefly go through the workflow of federated logistic regression, which is also known as federated LR. In federated LR, there are several isolated participants, which are also called the parties. They cooperatively train a model with their local data set. First, the parties individually train a submodel. During this progress, the parties may need to exchange intermediate training results. Then, an arbiter will aggregate the submodels from different parties and return the updated model back. To protect data privacy, homomorphic encryption is required before data transfer. However, homomorphic encryption is a key bottleneck in federated LR. Let's take Parallel crypto system as an example. After encryption, the plain texts, which were floating point numbers or small integers, are converted into large integers, which will increase computation time. We perform a test on heterogeneous LR, which is a quite common model in real-life applications. We can see from the testing result that training time will become far longer after data encryption compared with unencrypted training. A possible solution to this problem is heterogeneous system, which is popular in recent years. It refers to a system in which computing tasks are offloaded to hardware devices like GPU, FPGA, and ASIC. These hardware devices share the feature of high execution parallelism and perform better than CPU in many calculation scenarios. GPU is one of these devices with wide applications, including graphic processing, scientific computing, and so on. This comes from high programmability and flexible resource allocations of GPU. Therefore, GPU is a good choice for accelerating federated LR. However, there are several challenges to overcome in order to efficiently implement GPU acceleration. First, the algorithms for federated LR is complex, and different federated learning frameworks may have different implementations. So it is not realistic to individually accelerate every instruction with GPU. Second, most of the raw data in federated learning frameworks are stored sparsely. In the meantime, it is common in federated learning frameworks that a single operation is only executed over a small amount of data. These facts will lead to low utilization of GPU resources. Third, in federated learning, data exchange is quite common, which means that we will frequently read and write data to GPU memories. Large data transaction overhead will be introduced in this way. To achieve high performance and reduce the complexity of implementations, we summarize a set of performance critical operators used by federated LR and do a joint optimization of storage, I/O, and computation to accelerate operators on GPU. Therefore, we proposed HeyFlow, a heterogeneous acceleration system for federated learning operators. The overview of HeyFlow is displayed in this page. It is a system that connecting federated learning frameworks and a GPU device in order to achieve high computation throughput. Most of our implementations is done on Fate, which is an open-sourced federated learning framework, but it can also be applied to other frameworks. HeyFlow works on the granularity of operators. In other words, federated learning framework can leverage our systems by calling the APIs to execute a single operator, like encryption or multiplication. HeyFlow is basically composed of three parts: a computation optimizer, which increases computation throughput, a storage optimizer, which optimizes data storage structure, and an I/O optimizer, which leads to an efficient hardware interaction flow. Next, we will introduce these components. First, the computation optimizer. Instead of accelerating each of the instructions in federated LR, we summarize a set of operators with high computational complexity from the algorithms and build corresponding GPU kernels. The kernels in our design are efficient because of suitable algorithm selection and parallel calculations. They can easily component most instructions in LR training, including the calculations of gradient and loss. Based on the kernels, we designed operator binding, which transfers data with GPU and invokes the kernels. The execution of operator binding achieves high throughput with proper GPU resource allocation and workflow management. For example, we overlap CPU calculations, GPU calculations, and data transaction in the operators. Since we already have these high performance operators, how to call them efficiently? First, we need to perform data pre-processing on the raw data, which includes data aggregation and serialization. In this way, we can improve the utilization of bandwidth between CPU and GPU, as well as the computing resources in GPU. Some storage management works are also important to support data pre-processing. As we already mentioned, ciphertexts are large integers. In addition to computation time, serialization of ciphertexts is also slow. In such cases, we only execute data pre-processing on raw data, which are floating point numbers or small integers, and then we perform GPU encryption on these serialized numbers. Furthermore, we allocate page-locked CPU memory for pre-processed data because such memory can be directly accessed by GPU, which will reduce transaction time between CPU and GPU. However, allocation of page-locked memory is a time-consuming work. In order to reduce such operations, we introduce an allocation scheme for memory reviews. We use a table to record all the memory space that has been allocated. When there comes a new allocation request, we search for recorded memory space, which has the suitable size. If such memory is available, we just reuse it to store the data. Of course, we also have a garbage collection mechanism based on the LRU algorithm to avoid memory overflow. Apart from optimizations over CPU memory management, we also implement optimization on I/O. We note that in the workflow of federated LR, there are several consecutive operations whose calculation results are just required by the next few steps. Therefore, to avoid unnecessary data I/O and data copy, we propose a scheme to cache intermediate results in GPU memory until they are no longer needed. We designed two modules for this work, operand management and GPU memory management. In brief, GPU memory management allocates and releases memory on GPU, and operand management prepares the operands for GPU operators according to the instructions from federated learning framework. By leveraging these two modules, we will be able to manage GPU memory space from federated learning framework and then implement result caching. Next, let's see how this system performs. Since the GPU operators are the fundamental components of our system, it is essential to test their performance. We compare the performance of our GPU operators and the CPU operators. The result shows that the performance of GPU operators outperform CPU, especially for operators like homomorphic or multiplication, which are more computational complex. GPU achieves even higher acceleration ratio compared with CPU. In addition, we implement our system on the federated learning framework, FATE, to test the improvement over practical training tasks. The result shows that for both two kinds of LR models, our system provides remarkable performance increasement compared with open source FATE. For heterogeneous LR, Hayflow achieves an acceleration ratio of about 50, and for homogeneous LR, which is more computational intensive, Hayflow achieves an acceleration ratio of about 90. This result verifies the compatibility between our systems with federated learning frameworks. In the last, I will talk about future works of Hayflow. First, in addition to federated LR, there are many other popular federated learning algorithms, including secure boost. They also suffer from the performance bottleneck of homomorphic encryption. We will focus on the generalization of Hayflow and implement more hardware-based operators according to the algorithms. Second, as data size for machine learning keeps increasing, the demand for distributed systems is gradually increasing as well. It is the same for federated learning. The application of Hayflow in distributed systems has other challenges, like the scheduling of hardware devices and communication among different nodes. In the future, we will also investigate heterogeneous acceleration for distributed systems. This is the end of my presentation, and thanks for your listening.
Okay, any questions? Any questions from the audience? Okay, cool. Then let's thank the speaker again. So the next presentation is a federated XGBoost, a privacy-preserving XGBoost for federated learning. Since I can't pronounce the name of the presenter, I'll ask him or her to introduce herself.
So hi everyone, may I share my screen right now?
Yeah, sure.
All right. So good morning, everyone. My name is Khan. Currently, I'm enrolled at the master's degree at Technical University of Munich. Today, I would like to present our research project about the adaptation of a well-known machine learning model, XGBoost, under federated learning settings under consideration of privacy preserving. This is a joint research project between researchers and doctoral candidates at Technical University of Munich, the ByteDance company, and Massachusetts Institute of Technology. And here are the contacts of our research partners. So let's start with our what we did in our study. So as you already know, federated learning is a distributed machine learning framework, and which allows multiple parties to collaboratively conduct machine learning models. And thanks to the high variety and high quantity of the data, these models offer the high quality prediction. So it also accelerates the training process because it reduces the heavy workload of a centralized computer. And yeah, so it brings a lot of benefit to machine learning. But there are still many challenges in federated learning that we have to handle. And one of the most important is the privacy preserving concern. In 2018, the European Union passed the law of GDPR to enhance the privacy of data, of personal data. And that is the main challenge because federated learning have to handle the data transmission or sharing data between multiple parties. So the recent study focuses on how to handle the privacy preserving in the federated learning algorithms. There are several approaches. Data anonymization, which cover the identities of personal data, is shown to be insufficient. On the other side, data encryption is offer high privacy preserving, however, costs high communication overhead. So in practice, it's not so efficient for large data set. And there are also another approach is as differential privacy. Due to the nature of the algorithm cause accuracy loss. I will present this later in details in the preliminaries part. So from the short summary, we are motivated, or in general, the federated learning algorithms are motivated to find a compromise between privacy preserving, accuracy, and efficiency. And what we did in our research is we bring the benefits of a well-known machine learning model, XGBoost, so studied by Chen in 2016 under the federated learning settings, and our protocols propose a privacy preserving mechanism to handle this criteria for the federated learning XGBoost. Our two protocols don't apply data encryption, so avoid communication overhead and expect to be more sufficient. So here are the related works. The study by XGBoost can be found in this paper. The studies with a similar configuration can be found by Chung in 2019. They proposed SecureBoost applying homomorphic encryption for XGBoost. And also these two papers proposed using differential privacies for federated learning XGBoost. Okay, so let's start with the preliminaries of the XGBoost model. And here's the a figure of a decision tree, a standard decision tree in machine learning. So in decision tree classification. And to construct a decision tree, the data, we will analyze the database and then propose some splitting candidates such that the tree can be constructed, and also the weight parameter of the tree. So what XGBoost does is it proposes a robust optimization procedures such that the tree can be analyzed, can be trained well from the database, and then obtain the optimal parameter as shown here in the figure. Our aim is to bring the benefit of the XGBoost into the federated learning settings. So here you can see multiple parties jointly contribute to the performance of the XGBoost from their high quantity and variety of the data. But the challenges of federated learning XGBoost is that the transmission, the data sharing between database is not that straightforward. There must be a mechanism to handle the privacy concern between the sharing data of the multiple parties. So there's still many various settings considered in federated learning and privacy preserving in general. So we recommend this paper proposed by Yang in 2019. It provide a really informative information of federated learning and different scenarios about privacy preserving in federated learning. So our study mostly focus on the vertically partitioned data. So which means the settings can be categorized into two types of parties, the active party and the passive party. This concept was also proposed by Chung in 2019. So the active party, only the active party will have the information of the label, of the class label, while the passive party will be the data provider, which means they don't have access to the class label. And what XGBoost does is that we want to evaluate the process to construct the tree model. And what XGBoost does is that it optimizes this equation as shown here in this slide. Here we can see better the roles of the parties in our settings. So because the passive parties has the personal data, a lot of data, so they can perform the data binding and propose several splitting candidates such that the tree can be constructed. But in order, so to evaluate the splitting candidates such that we can find the optimal one, the active party will use the gradients and the Hessian value from the class label, so which can only be computed from the label, such that the splitting score can be evaluated. And the problem here can be seen is that this information of the passive party and active parties are confidential. So there must be some mechanism to handle this, to tackle this problem. And our approach is that we analyze the role of the two parties and we reformulate them mathematically such that it's more convenient to design the protocols. And then based on the concept of the splitting matrix, we design the two protocols that fulfill the criteria and also provide the thorough analysis about the privacy preserving of the two protocols. So, but first, so here is the splitting matrix. Let's make a short recap of the role of the passive party in the XGBoost. So the passive party, as I mentioned above, it analyzed the data distribution of users and then proposed several splitting candidates. And then because the splitting candidates must be evaluated, so it will receive or request the homomorphic encrypted gradients and the Hessian from the active party. And then the splitting score can be evaluated from the encrypted data. However, this causes a high communication overhead. So we are motivated to reformulate the role of the passive party by introducing the splitting matrix. So what the splitting matrix does is that when the passive party study the data distribution of the users, it will also construct its own splitting matrix. It will label the users as 0 or 1 if they belong to the left or the right node or vice versa. And by this way, the passive party construct a matrix, a categorical matrix, which represents the distribution of the users. And this matrix is also confidential. But by this way, we are successfully introduce the private data of the passive party by using this matrix. And if you look back into the evaluation function of the splitting candidates, this is equivalent to the computation of the result of the matrix multiplication between matrix M and the gradient and the Hessian vectors. So that is how we reformulate the problem into an equivalent problem such that enables various protocol in secure multi-party computation can be taken into account so that they can handle this challenge. So what we want to do is just to find the final result of the matrix multiplication securely without revealing the information of another parties. And this is defined by the secure multi-party computation here. In our study, we assume that the participants are semi-honest. So they must follow the protocol, our desired protocol honestly, but they are curious and they will try to reconstruct data of another parties. So it is the responsibility of our protocols to ensure the privacy preserving criteria. The protocol we applied in our study is the secure matrix multiplication studied by Carr in 2007. And for more information, you can look at the slide and to understand how the algorithms work. But basically, they jointly find the final result without revealing their private information. Even the two parties know the final result. And this is the concept. This figure illustrates how everything works. So the passive party construct the private splitting matrix, and then the active party with the label can compute the gradient and the Hessians. And they jointly apply the protocols so that the final result can be obtained. And from the final result, none of the one party can reconstruct the data from the other from the another. And during our protocols design, the Fed attributes SMM. So for Fed attributes SMM stands for federated learning attributes and secure matrix multiplication. So there's also challenges which need modification to enhance the privacy preserving, because what we realize is that the matrix here is categorical matrix. So there are some risks that it may reveal the confidential information. So that require more handling to fulfill the privacy preserving criteria. And this is a really challenging and interesting problems. What attributes SMM achieve is that the lossless property, and it avoids the communication overhead. So it is expected to be more efficient in practice. On the other side, we also provide another algorithm applying differential privacy. So differential privacy or local differential privacy is studied by Drock and Ellingson in 2014. I can intuitively explain, like informally explain the algorithm as that there are some randomized mechanism so that it will perturb the real data of the users and to make them indistinguishable. So under this term of differential privacy, the data can be, let's say, be denied. So the private information can be protected. And the concept is straightforward. We perturb the gradient and the Hessian vector, the G and H, and then we use the perturbed data with some small modification to reduce the accuracy loss. So because these two vectors are perturbed, so there must be some noise inside the real data. And we provide some small modification to show to reduce the impact of the noise at the final result. But we have to claim that there must always be a trade-off between the accuracy and privacy preserving budget, because this is not the nature of differential privacy. However, these algorithms are robust. There are no communication overhead, low complexity, and in the evaluation part, it can be seen that it achieves like a desired or acceptable particle result. So this is a real motivation why we would like to propose this heuristical design protocol. So here you can see when the application of federated learning attributes using LDP into a training data set. We also try with multiple privacy budget. The epsilon is the privacy budget. And when we zoom into the training trajectory, it can be seen that there are accuracy loss in comparison with the planned XGBoost without the data being perturbed. But however, these injected noise cause negligible accuracy loss. So we expected that this also offer equivalent performance. And also another different data set when more instances and also varying parameters, the practical result yield the similar convergence. So, but the real motivation is when we look at the training time evaluation here, using ADP is always 6 to 7 times much faster than using data encryption. So we say that the protocol is much more efficient. Okay, so to this end, I would like to conclude our studies. So in what we did is that we adapt the XGBoost model into a federated learning settings, and we propose 2 protocols that handle the privacy preserving. The 2 protocols avoid communication overhead, so expected to be more efficient. And we look forward to providing more performance analysis and practical verification such that the 2 protocols can be deployed in practice. So thank you very much for your attention.
Okay, thank you very much. Any questions from the audience? Okay, I have one question. Can you comment on the scalability as more parties are participating in the collaboration? What is how is the algorithm scale?
Sorry, can you repeat the question?
Yeah, the question is about the scalability of your algorithm. So how many parties are in your experiments, and how do your algorithm scale as more parties join?
So our 2 protocols, the Fed XGBoost SMM and the Fed XGBoost ADP. So basically the Fed XGBoost SMM, even though it avoids the communication overhead, but it requires some additional procedures, and it increased the model complexity because, for example, in the protocol we applied the secure matrix multiplication, also required some computation efforts. So for large data set, there also must be some mechanism for parallel learning or parallel computation. For example, in the QR decomposition, when looking into our research paper. But on the other side, the Fed XGBoost LDP is basically similar to the planned XGBoost. But what it was to say is that when for a large data set, it is expected from our proof, it is expected that the noise injected will make a negative impact on the final result because we are going to aggregate more noise and it causes high variance and it will degrade the performance of the model. But because so from our like short from our simple evaluation, this yields acceptable practical results. So we are still under the process to evaluate on more different data sets to see how the model performs.
Okay, thank you. Okay, if no further questions, let's thank the speaker again, and also thank all the speakers who contributed to this session. So after the this talk, we are gonna have another invited talk, which is by speaker Professor Sugiyama. So Professor Sugiyama is a professor at the University of Tokyo, and he also is a director of Riken Center for Advanced Intelligence Project. He co-authored many books, including Machine Learning in Non-Stationary Environments, Density Ratio Estimation in Machine Learning, statistical reinforcement learning, introduction to statistical machine learning, and machine learning from weak supervision. Today, he is gonna talk about rethinking importance weighting for transfer learning. Let's welcome Professor Sugiyama.
Okay, thank you very much for the invitation. Can you hear me?
Yes, yes.
Okay, good. So first of all, I would like to thank all the organizers for inviting me to this great workshop. And actually, the previous invited speaker, Min Shen Long, gave a very nice talk about transfer learning. And his talk was about domain matching. But today, I focus on another approach called importance weighting. So this is a bit classical approach, but I want to rethink the importance weighting approach here today. Okay, so then let's just recapitulate the problem of transfer learning. So we are given training data, so input X and Y, output Y, and paired data. So then our goal is to train a predictor Y equals f of X that works well in the test domain. So our risk is now defined as the expectation over the P test. So it's different from P train. So that's the challenge. We want to overcome the changing distribution. So that's the problem set up. And transfer learning has been a hot topic for many years. We don't have to say, like very nice survey paper by Pan and Yan. So the number of citations is really growing every year. And there was also a very nice book about transfer learning recently. And also we had some classical books on this topic. Okay, so in the most general case, we consider full distribution shift. So P of X, Y, both changes. But there are some sub-scenarios, like covariate shift only changes P of X, or class barrier or target shift only changes P of Y, or output noise or class conditional shift. So we have various different scenarios. But today I focus on one of the simplest ones, covariate shift. And finally, I will talk a bit about full distribution shift. But the main part of my talk is about covariate shift today. All right, so then let me spend some time to review classical results on this topic. So let's consider the covariate shift problem, as I said. So in this covariate shift, Y given X remains unchanged. So it's the same. So that's the setup of covariate shift. And typically, we consider a regression problem like this. So there's a target function here, and we have some data. But the input density changes from P training to P test. So training data points we have is coming from like this density. Then we have training data in the left-hand side of the graph. But the test data comes from this P test. Then we have test data coming from the right-hand side. And it's a kind of extrapolation problem. So that's a typical illustration of covariate shift problem. Then, so for learning, we usually use empirical risk minimization. So it's just a minimization of the sum of loss over training data points. So that's the most standard one. And generally, this empirical risk minimization is statistically consistent. So this means that the learned function converges to the optimal solution when the number of training data goes to infinity. So that's a standard general result. But under covariate shift, unfortunately, empirical risk minimization is no longer consistent. So this quantity, so empirical risk, converges to the expected loss over P training. But by the covariate shift assumption, so input distributions are different. So this is not different from our target risk. So it's not consistent. And in reality, for this simple regression problem, we end up in just fitting training data points, and it doesn't fit test data at all. So that's the situation. So then to cope with this problem, importance weighting can be a standard technique. So in this importance weighted empirical risk minimization, we have importance weight here. So it's the ratio of P test over P train. Then, so this actually gives a solution like this. So this importance weighted empirical risk minimization is statistically consistent, even under covariate shift. So indeed, this quantity converges to the expression over P train, but now we have the importance weight here. And this P train and this P train are cancelled under the covariate assumption. And it agrees with the loss expected over P test. So that's a true target risk we wanted to minimize. So this is how consistency can be recovered by importance weighting. But then how can we know the importance weight? Because we don't know P test and we don't know P train. So that's a problem called importance weight estimation. And in this problem, so Vapnik's principle actually plays an important role. So in his famous book published more than 20 years ago, so he said, when solving a problem of interest, one should not solve a more general problem as an intermediate step. So this is a kind of philosophy of support vector machine, but we try to apply this idea to this importance weight estimation problem. So in our case, so if we know two densities, P test and P train, then we can naively compute the ratio, but not the other way around. If we know the ratio function, we cannot decompose it into P test and P train uniquely. So this means that estimating the density ratio is substantially easier than estimating both densities. So we should directly estimate the ratio. So based on this idea, various direct density ratio estimators were developed, and we had a book already long time ago. So let me briefly introduce one method that is the simplest, called least squares importance fitting. So now we are given training and test input data. It's like a semi-supervised classification regression problem. So we have input from training distribution, and we have unlabeled data from test distribution. Then, so we try to directly fit a density ratio model R to the true ratio R star by least squares, meaning that, so we minimize function Q with respect to the model R, and Q is the square difference between our model and true density ratio R star squared and P train. And this quantity Q can be easily empirically approximated. Indeed, if we expand this squared, we have R squared and 2 times R squared, R star. But because of this definition of R star, the P train are cancelled, and only we have P test here and some constant here. So then we can naively apply empirical approximation, and we can approximate this QR only from training input data and test input data, and just solve this minimization problem empirically. So that's least squares importance fitting. Okay, that was a kind of standard solution to apply importance weighting for covariate shift. But still, it's not satisfactory. This importance weighted empirical risk estimator has no bias, but it has large variance because of this importance weight. On the other hand, the ordinary empirical risk estimator, so without importance ratio here, it has small variance. Actually, this is statistically efficient, so it has the smallest variance, but it has large bias, as shown in the beginning. So we want to somehow control the bias variance trade-off in a nice way. How can we achieve this? So to cope with this problem, so flattened importance weighting has been discussed already more than 20 years ago. So it's quite simple now. So there is gamma factor here. Gamma is the value between 0 and 1. And if it's 0, the weight is all 1. So it is reduced to the ordinary empirical risk estimation, minimization. And if gamma is 1, so it just becomes a standard importance. But if gamma is somewhere in between 0 and 1, so we have a slightly flattened importance. But by that, we can control the balance between bias and variance. It's like this. When gamma is 0, so it is the ordinary estimator. If gamma is 1, it is consistent, unbiased, but large variance. And in this illustrative example, gamma equals 0.5 gives a very nice solution like this. And in reality, this gamma, flattening factor gamma, has to be chosen carefully, maybe by importance weighted version of Ijcai information criterion, or importance weighted version of cross-validation and things like that. But still, this flattened method is somewhat problematic because even with direct methods, reliably estimating the importance weight is quite hard. This is because R star could be highly fluctuated because of this ratio definition. That means, so flattening an unreliable importance estimator, R hat. R hat is rather unreliable. Then if we have a power factor for this R hat, the entire solution is still unreliable. So that was the problem. To overcome this problem, another approach called relative importance weighting has been discussed. So in this paper, this definition of importance weight was used. So now part of PTE is also included in the denominator. Again, if beta is 0, it is just an ordinary importance weight. And if beta is 1, so it becomes uniform weight. So again, it interpolates between ordinary empirical risk estimator and importance weighted risk estimator. But the difference from the previous flattened approach is that this R beta can be directly estimated for each beta by relative LSIF. So there's no problem of this unreliability. Okay, that was a kind of classical results we have worked on long time ago. And after that, I was a bit away from this topic, but recently we had some small progress, and I want to quickly present some of the new results. Okay, the problem of the previous classical approaches are actually two-step nature. In the first step, we estimated importance weight, for example, by least squares importance fit, and obtained R hat. Then in the second step, we applied this importance weighted prediction training. So R hat is plugged in here, and F is obtained like this. So the question is, so can we integrate these two steps and somehow avoid the two-step nature? And we had some nice results recently. The first approach is joint upper bound minimization. So under some condition, our risk function, so it's defined like this, same as the previous ones. Now it's squared and divided by half, by 2. It is upper bounded by JL prime. So L prime is another loss function. That upper bounds the original loss function. And we assume that loss function, oh no, sorry, this is L should be less than equal to 1. So L is upper bounded by 1, not lower bounded. And R is larger than or equal to 0. Then, so this squared risk is upper bounded by this quantity, so 2 terms. And actually, interestingly, the first term is the same as importance weighted empirical risk minimization with loss L prime, but it's squared. And then second term is exactly the same as the criterion of least squares importance fitting. So then by looking at this upper bound, we see that the previous approach, two-step approaches, the least squares importance fitting followed by importance weighted empirical risk minimization is actually suboptimal. So this second term is minimized first, and then the solution is plugged in into this first term, and then first term is minimized. So that was the previous approach. So then based on this upper bound, we can naturally propose that, okay, let's minimize the upper bound with respect to R and F at the same time. Then we can really minimize the upper bound of the squared risk. So by the way, these assumptions, the inequality is flipped. So this condition is specified by, for example, L is the 0-1 loss, and L prime is the hinge loss, softmax cross entropy in the case of classification. Or if L, in the case of regulation, L could be the 2-key loss like this, and L prime is the standard squared loss. Then, so this assumption, this condition is satisfied. And for this problem, so suppose F hat is the empirical solution. So that J L prime is empirically approximated like this, and it's minimized as F hat. Then we can show that under some mild conditions, the risk of the empirical solutions, RL of F hat, is upper bounded by this quantity. So we have another risk term here, and the convergence is a bit slower. So it's 1 over, so minus 1, it's 1 over minus n quarter. So it's a bit slower, but we can minimize this one. And then in practice, so we may implement this idea with the alternating minimization idea. So first we estimate the importance weight, and then so estimate the predictor, and this is repeated until convergence. Then we can minimize the upper bound. Then as usual, so for some experiments, if we tune the parameters carefully, so the proposed method works quite reasonably well. Okay, that was the first idea of joint upper bound minimization. Then finally, I will briefly talk about dynamic importance weighting. So this is actually quite simple. So in deep learning, we use iterative optimization. So like stochastic gradient like this. So then let's use this idea. So try to learn the importance weight and predictor dynamically in the mini-batch wise manner. So that's actually quite simple. And this is possible if we assume that so we are given both training data and small number of validation data. I call it test data here, but it's basically validation data. Suppose we have two data sets like this. Then for each mini batch, so I added the bar for the mini batch data. Then importance weights are estimated by matching the loss values. So left-hand side is the importance weighted training error. And the right-hand side is just the test error or validation error. And we match these two by learning RI. For example, we can use kernel mean matching for this solution. And actually, in this process, we don't have to assume covariate shift assumption anymore. So even if the joint density changes, joint distribution changes, we can apply this mini batch wise loss matching technique to cope with the distribution change problem. Again, this can be very simply implemented. So we first compute the loss for both training data and validation data and match the loss to obtain the risk or obtain the weight. Then so train the neural network based on this weight. So again, empirically, this method seems to be quite promising after some careful tuning. Okay, so that was all. So in transfer learning, so importance weighting is actually quite promising, I believe. But so far, the classical approaches are two steps. So it's quite important to combine importance estimation step and prediction step, predictor training step. And we showed this is promising. But what should we do if the training and test distributions are very different? Maybe the importance weight is quite fluctuated and there's no chance that we can really transfer something. So we had one idea in the previous year. So that's called mechanism transfer. So suppose, so these are training data from different domains, and this is a test data in test domain. Suppose, distribution of data points are quite different, but some mechanism behind data is shared. So mechanism basically mean structural equations like this. And okay, we can somehow transfer the shared mechanisms from training domain to test domain. So this is out of scope of today's my talk, but by applying this kind of idea, even if the observed data have quite different distributions, we can still somehow transfer some knowledge from training data to test data. So we want to explore this kind of direction in the near future to further improve the performance. Okay, thank you very much.
Okay, thank you so much, Professor Sugiyama. Any questions from the audience? So I actually have a question. So I'm very interested in your talk about, how to train or learn the covariance shift weight factors. So the important weight factors. So recently there's a trend to use machine learning or meta learning to perform such tasks, such as learning to reweight, which I believe also maybe a recent SML paper. So can you comment on, the differences or the potential, implications of using that particular approach to, theoretically guarantee whether or not it's actually transfer learning approved?
Okay, thank you very much. So the voice was actually not so clear, but so okay, recently so there are a lot of like domain matching ideas, and actually many of the methods are essentially quite related to density ratio estimation. So when we worked on this problem, still deep learning was not so popular, and we didn't work on this problem in the context of deep learning. But basically, so the methods are independent of choice of models. So at that moment, we just used kernel model or linear models for learning the ratio. But the same technique can be basically applied to deep networks or whatever model. So then, for example, GAN is actually a special case of this density ratio estimation mathematically. So in a sense, the approach is quite the same, but now the context is more modern and the performance is much improved. So that's my understanding.
I see. Yeah, thanks. Okay, if no further questions, let's thank Professor Sugiyama again for
Thank you very much.
And yeah, thank you again. So after his talk, I believe the next section is the award ceremony, which I will hand over to Dr. Fan Lixin to host this section.
Thank you.
Dr.
Thank you. Yeah, thank you, Dr. Liu, for hosting the session. And thanks everyone for staying with us for the whole long day. I will start to share my screen for the award ceremony. Okay, so everybody see the screen, right? As some of you have stayed with us from the early morning, and Dr. Yu has shown this Gartner hype cycles for both federal learning and the transfer learning. As from this cycle, we can see both research about the transfer learning and the federal learning has been undergo a rapid development, and in near future probably they'll reach its peak. So basically, this rapid development of this research, it doesn't come by itself. Actually, we have to mention a lot of important contributions made by researchers. So in recognition of these important contributions in this workshop, we would like to give a word to some very important papers. But here, let's see, in this workshop, we will give 4 awards to each of these best papers, best student paper, best applications, and test of time award. During my presentation for winner of this award, please turn on your video to show your face to the audience to make people remember you. So the first award is given to it's the test of time award given to Professor Ming-Sen Long for their very important work on transfer learning, learning transferable features with deep adaptation network. This work has been published at ICML in 2015, and it has been cited over 2,500 times since then. Professor Ming-Sen Long, are you still, can you please show your, yes, great, yeah. Thank you for your great contributions to the community, and this award is in recognition of your contributions. Hopefully, we will see your more important contribution in near future. Thank you.
And many thanks to their committee. It's my great honor. Thanks.
Yeah. By the way, this award will be later on sent to your address.
Okay,
yeah,
got it.
Yeah,
Thanks.
got it. Thank you. And then next award is Best Paper Award of the workshop. This is the paper entitled By Robust Federal Learning with Adaptive Aggregation, authored by Wang Qi-pu and Chen Qifeng from HKUST. Are you there?
Yeah, here.
Wang?
Thank you so much for that award.
Thank you. Congratulations for your great work. And I hope this is the Best Paper Award, and we see your face again in near future in upcoming events. Congratulations again. Yeah. And then next award is the Best Student Paper Award. Is given to the title, the paper entitled Contract Theory-Based Incentive Mechanism for Federal Learning, co-authored by Tian Meng Meng, Chen Yuxin, Liu Yuan, Xiong Zehui, and Liu Siri and Miao Chunyan, from Singapore and China. It's a joint work from Singapore and China researchers. And who is there? Tian Meng Meng or any authors? I'm Liu Yuan. Oh, great. Yes. Congratulations to your great work.
Thank you very much.
Okay, great. And we hope to see your face again in the near future. Yeah, sure. Thank you. And then next is the Best Application Paper Award, given to, actually this talk has been presented in just in the afternoon session. Just a trusted, automatic, and accurate verification framework for vertical federal learning, from co-authored by Zhang Chengguang, Zhang Junxue, Cai Di, Chen Kai, from HKUST and Clustra. And Zhang Chengguang, or any co-authors, are you there?
Hello, I'm here. Thank committee for giving us this award. We'll continue to work harder in the future research work. Thanks.
Congratulations. Thanks for your great work. Yeah. Okay, then last but not least, don't forget, we still have upcoming poster sessions in which we have very interesting 8 papers, and you may access this this meeting room in the green 2, so you can discuss with the authors of these poster papers. For people who probably you don't have access to these meeting rooms, you may check our website, on which you will find the poster slides of these talks. So hopefully in this way, everybody can at least get an idea about this excellent work. And so that's not end of today's workshop, but thank you everyone for staying with us for a long day. And I hope you still enjoying the post session in about 1 hour time. So thank you again. Thank you everyone. And also thanks Dr. Yu and all the organizers, helpers for the excellent workshop today. Thank you, and see you in the poster sessions.
Thank you very much, everyone. Just a quick announcement. I have already updated the website for the award winners. You can go onto the website to download the electronic certificates. And for the poster session actually begins now, but we need to move to the Gather Town room instead of using Zoom. For those who have registered for Ijcai, you can go there and interact with the poster authors. They are supposed to put up the posters in the around the room, but somehow I don't see them yet. But anyway, you can refer to the posters from our website and try to find the authors of those posters and interact with them in the virtual space. Okay. Okay. With that, we can end this Zoom session here. Thank you very much for everyone participating, and have a great weekend.
Thank you. Thank you, everyone. Okay.